Yeah, all right. So welcome back, everyone. And so it's my pleasure to welcome you to the third session about deep learning, kernel methods, and GP. So here we try to have a common session between these three concepts just to bridge the gap and to explore connections. So our first speaker is Benedict Leimkuhler, and I will be talking about thermodynamic algorithms for neural networks. Yeah, thank you.
Okay, thank you, Hamzi. Can you hear me okay? Is everything fine?
Yes, thank you.
Okay, great. Okay, thanks a lot for organizing the session. I think it's interesting. It'll give me quite a lot of material to study in the coming weeks when I finally find a moment to recover from the start of classes. So I'm going to give just a 20-minute talk here, and this is going to be a synopsis of a bit of the work that we've been doing in neural network training algorithms. The starting point, normally I would give an introduction. Since this is the first talk in this session, I would give an introduction to deep neural networks. Oh, there it is, okay. Can you see the second slide now, deep neural networks?
Yes. Yeah.
Okay, great. This is the only introduction we're going to have, okay, in fact. Because there's just 20 minutes and I have to move rather rapidly. So the setting here is high capacity model families that have been found to be flexible and trainable for many different tasks. And there are some brilliant successes in this field, like AlphaGo Zero for learning to play Go or chess from essentially scratch, just by providing example games. And other things like medical image analysis, where there's been some real breakthroughs, and it's allowing rapid screening of medical images. But there's a lot of questions that remain, and particularly for mathematicians, there's a huge opportunity here to find new approaches to these problems. In particular, the neural network families that people are using are not always generalizable. So you may find that a method works well for in one domain, but doesn't work well in another domain, and the reasons for that are not always clear. There are really no error estimates that are practical, or even sensible accuracy bounds. They often have coefficients in them that are so large, if you tried to actually pin them down, they wouldn't be useful. So in fact, what happens is that a lot of the mechanism of using neural networks, and in particular the training, which I'm going to talk a little bit about, it remains a bit of a black art. So people have a large number of techniques, some lore that they've developed over the years, and they put this together into a kind of a scientific approach. But it's certainly, there's plenty of room for improving the foundation of neural network training. There are a lot of questions related to regularization choices, how you actually schedule learning rates, the smoothness of classifiers and neural network outputs, and the stability of these processes, both in two senses, both in terms of the stability of the map that you create. Typically you're parameterizing a map, but also in terms of the process, the iterative process that you use in training. And there are other questions as well, such as the significance of depth in deep neural networks. They certainly work well when we have large numbers of degrees of freedom, but actually, is it necessary? There's no proof that we actually need to use such large model families. And of course, if we could get rid of some of the depth, we could actually improve the efficiency of neural networks. So that's one of the things that I'd like to get to eventually. I'm not quite there yet. This talk will just sort of be opening up the subject, in particular of how we use thermodynamics to try to improve training. So the starting point here you can take is the paper by Welling and Tay, which modified stochastic gradient descent by introducing additive noise. So the G of theta that appears there, theta is parameters of some model, typically a neural network, and G of theta is the gradient, typically will be approximated by subsampling, some sort of random subsampling, so that this sigma of theta that appears here is a model for the error that's introduced in that subsampling, the error in the gradient, so the random component, which indeed will depend on the parameters themselves. The idea of adding additional constant additive noise to the constant amplitude additive noise to the gradient descent process was suggested by Welling and Tay, and they had a number of reasons for doing that. And in particular, they found that it could improve the training of neural networks. It could give you more robust algorithms and procedures. And in fact, their idea was originally that you would take the step size in the algorithm, and the step size is actually appearing in this description here. So this is kind of a model. The gradient noise has an H dependency in the framework that I've been developing. And you can actually see that as H goes to 0, that term disappears. So you get the correct results. It's sort of, it's more clearly explained in the paper of Welling and Tay. But you don't actually have to take the step size to 0. If you had to take the step size to 0, this procedure would be very inefficient. And you also don't actually have to introduce any direct dissipation mechanism. You can include a stochastic perturbation, which is constantly shaking up the system, shaking up the parameters, and still get really interesting and useful results. So you can imagine this as a kind of Bayesian posterior sampling, but it's one in which we've modified the Bayesian posterior so that there's a temperature which is relatively low. So I like to think of these as cold posteriors. And there's a nice paper, How Good is the Bayes Posterior in Deep Neural Networks, really, which came out this year in ICML, which describes some of these kinds of approaches and the results that people have been getting with them. So this is sort of the starting point for our work. We wanted to improve this framework, so adding additive noise into the stochastic gradient algorithm, the gradient descent algorithm, in order to enhance the convergence to good parameterizations. There are lots and lots of reasons to do this. We have actually a paper which lays out some of the philosophy of this and also describes software for doing it based on TensorFlow. So that's coming out in JMLR, and you can find this as a GitHub package. It's a GitHub site on the Allen Turing Institute's website. So this is the Thermodynamic Analytics Toolkit, or TATI, that we've been developing. So the paper describes some of the motivation for this. So we're trying to ameliorate barriers in the training landscape and increase diffusion rates, so exploration rates. We're trying to address a fundamental degeneracy in the SDE model, which allows us to talk about the ergodicity and hypocoercivity properties of the exploration algorithm. It also allows us to bring in concepts of statistical mechanics that rely on ergodicity, and which allow us to use a wide variety of tools that have been developed in the context of molecular modeling over many years. And we can design new enhanced sampling strategies, which can also have potential to improve neural network training. There's possibilities for doing better uncertainty quantification based on these kinds of algorithms, because you actually have a distribution that you're working with. You can calculate uncertainties. And this also provides additional tools for generative models and variational autoencoders, which take as their target a probability distribution. So what we're doing in our methods is effectively sampling a probability distribution. That's the foundation for the algorithms I'm going to talk about. And so this is also the core task in these other methods. And there's some surprises. It seems that thermodynamic approaches can actually accelerate the convergence to near minima. So I'll just sort of show that briefly. So we work with typically second order dynamics. So this is underdamped Langevin dynamics. The corresponding model that I presented earlier, the Welling and Tay, was an overdamped form of this. So we just had the parameters present. Here you can think of as X as the parameters and P as an associated momentum. And this is a well understood SDE model if we have no gradient noise. When we add gradient noise, of course, it gets more complicated. There's a central limit theorem and geometric convergence of averages for a wide range of test functions. So there's a lot of useful mathematics that we can employ to understand these types of dynamics. so that this, of course, is an SDE system, and these dW here is a Wiener increment. So you have to interpret this in the right context. And there are a number of discretization schemes that are available for solving these systems. And in particular, we've developed a lot of methods in the context of molecular dynamics based on splitting up these SDs into parts. The use of momentum in stochastic gradient descent is well known. But in stochastic gradient descent with momentum, we get locking states, so we get trapping. And here I'm showing spiral data, which is two spiral arms we're trying to separate. So what we should be seeing here is a high contrast background for the points that are indicated there, which represents two separate spiral arms. And this type of spiral data is a nice challenge for training classification algorithms based on neural networks. So a question we set ourselves was, can we eliminate or circumnavigate these locking states and improve the training of neural networks? And indeed, just introducing the temperature, the additive noise perturbation into neural network training can improve that process. So you can get much better conversions. And here you can see tau is representing the temperature. So that's the scaling of the noise that we're adding in, the additive noise. And at low perturbations, we're in a cold situation. We don't get very good results. In the high temperature case, we don't get very good results. There's sort of a Goldilocks regime, not too hot, not too cold, where the training is rapidly, is dramatically improved. Okay, so that's now sets the stage for finding other methods and understanding exactly why these schemes are working so well. And so we have a lot of experience with SDEs and with studying distributions and convergence to distributions, for different SDE systems. And this has all been done in the context of molecular modeling. So we're now trying to explore how these different schemes might be used to enhance neural network training, because we now have a framework for doing that, because we've used underdamped Langevin dynamics to do training, and we know it can work. So the question is, can we get better methods by using some of these other techniques? And it turns out that we are getting some results that look very promising using different schemes that are shown here. And in particular, I'll say a few words about constraints in this talk. And we're also using this thing in the bottom, which is the adaptive Langevin algorithm, which is a very useful tool for removing some gradient noise from the systems that we get when we set up the neural network training algorithm, so the SGD type framework. And this has been sort of reinvented in the machine learning literature as SGNHT, but we had actually discussed it much earlier in the context of molecular modeling. And what we're doing with that now, lately, we've been doing some work on the convergence in distribution of the adaptive Langevin algorithm. And then we've been combining that with Langevin dynamics to make a powerful training algorithm. I'll just say a brief word about this, but obviously there's not enough time to go into details. So the basis for these combined methods that use the adaptive Langevin algorithm is that you have this problem of that you can enhance dramatically the convergence of sampling algorithms by using anisotropy. And we'd like to take advantage of that. So this is the starting point. So you can think of this in a very simple way as just training different degrees of freedom differently. And there's a long history of this kind of method in machine learning. AdaGrad, ARMAS, Prop, AdaDelta, and Atom are examples of schemes that do this kind of thing, although often they have an ad hoc foundation. You can also see methods of this type based on Newton type approaches, so where you transform the variables using Hessian information. And in particular, we looked at some sampling algorithms where we construct an approximation of the Hessian from a system of walkers and use that to rescale the dynamics on the fly. You can use this kind of thing to enhance optimization. So I'm just showing here a picture. I'm not going into all the details. This is for the Rosenbrock banana. The star in the upper right-hand corner is the minimum that we're trying to find. White is overdamped Langevin dynamics. Green is an underdamped Langevin process. And the black here is a preconditioned SDE system. So it's sort of adaptively and on the fly preconditioned. That method turns out to be expensive in practice. And so we look for simplifications of that kind of approach. And one of the things that we settled on was just to use the partitioning, the natural partitioning, according to layer structure in deep networks in order to build processes that actually are doing a kind of anisotropic optimization. So there's a paper in Foundations of Data Science, that's a new journal in fact. So it's a mathematical journal on data science, and it's also covering machine learning. And the idea here, the fundamental idea is that we can partition systems into different parts and apply different integrators to the different parts. So this is a kind of anisotropy based on, and we use a partitioning according to layer structure. So it's anisotropy based on layer structure. I'm not going to even present the equations. They get a bit messy, all the numerics and so on, but you of course can read about that in our papers. I'll just show you an example to try to convince you that actually this can be really a powerful idea. For this spiral data, the state-of-the-art method would be Atom. And this is just showing a comparison between Atom at 60,000 steps and Ard Louis, which is one of these partition schemes. So it's a scheme that's combining adaptive Langevin in one layer with Langevin dynamics in another layer with different parameters, so that we're actually doing an anisotropic process. And you can see with the same amount of work that Ard Louis is getting much better accuracies in this problem. And so this is just a simple example to show this. There are many other examples in our paper. Now, in the last 2 minutes or so of this talk, I just want to very briefly say something about constraints. So, you know, that's something we've been looking at recently, and we have a paper on the archive on this. We noticed that one of the problems in training neural networks is this instability that comes when we have large weights, when we generate large weights. And when you get large weights, you can see that in classification, it leads to steep interfaces between the domains of classification. So you can see that in this picture. And it also leads to some instability in the boundary, in the appearance of the boundary. And I think that we can probably demonstrate, although we haven't done this yet, that the idea of using a smooth representation like this will have a lot of benefits in neural networks. We're still trying to give a good foundation for this idea of smoothness in classifiers. But there are a number of people looking at similar things, and the foundation is starting to gel. But I'm just going to describe a little bit how we can control weights in and classifier smoothness in neural network training. So there are a number of different schemes for this. One is to use penalty functions, for example. Another one is to introduce configurational constraints. That's constraints on the parameters using Lagrange multipliers. And that's really the approach that we've been using. A lot of people just introduce constraints at the beginning and let it roll. And so the parameters do what they want after that. So there are very many schemes depending on how much taste one has for doing a lot of computational work. And so in a neural network, you have the sequence of layers. You generate these matrices, which are Jacobian matrices of the different layers. And we can control the growth of these weight matrices that appear in a deep network using constraints. I won't go into all the details of that. We have seen some examples, like in the spiral data here, where we can actually get away with even very small numbers of hidden layers using the constraints in order to control the process, and we can get more accurate classifiers from that. So that's all I have time for now. And I just finished up with this summary. So SDEs can improve the training of neural networks. And I showed you about partitioned methods, seem to work very well, and constraints, which seem to give us some new approaches for improving the training with SGD. So thank you for your time.
Yeah, all right, thanks a lot. So if there are questions, as we mentioned before, you can write them on the chat, and then we'll try to answer them during the break in about 1 hour. Yeah, and next speaker is Dimitrios.
You 1 second. Can everyone see my screen?
Yes, yes. So, so we are seeing the Lorentz attractor. Is this what you want?
Yes,
you want to start with? Okay,
yes.
all right, thank you. Yes.
So I'd like to start by thanking Boumediene and the organizing committee for putting together this exciting event. So I'd also like to start by showing a movie to illustrate the results I will be summarizing next. So this movie is going to show how two different kernel feature extraction techniques behave when applied to a prototype chaotic dynamical system, namely the Lorentz 63 system. So here on this panel, top left panel, what is being plotted is the leading principal component from principal component analysis as a scatter plot on the Lorentz, on a data set sampled near the Lorentz attractor, where basically what you can see that there is a sort of linear progression in the values of this principal component, which arises from the fact that principal component analysis is based on a linear kernel, and the result, and this feature is basically a projection of the data points in a three-dimensional space along the direction of highest variance in the data set. So when the movie plays, basically there will be an integration, numerical integration of the Lorentz 63 equations, and the dot here is basically going to sample that feature on the attractor, and it's going to create a time series plot here. And we're also going to look at a two-dimensional representation coming from the leading two principal components. Now, in the bottom panel, I want to contrast this with a different kernel feature, which is obtained by applying delay coordinate maps to the data, as I will describe later on, which leads to this different pattern, which is sort of manifestly nonlinear as a function of the data, and also sort of qualitatively tries to follow, in some sense, the orbit of the dynamics on the attractor. And let me start by playing it. Basically, what you see here is that the principal component evolution, as it corresponds to basically a simple linear projection, has comparable complexity to the basically chaotic Lorentz 63 dynamics. You have this characteristic sort of signal with different frequencies appearing and sort of chaotic transitions between the two lobes of the attractor. Whereas here, what you see is that despite the underlying mixing that takes place in the dynamics, you have a highly coherent observable in time. Over several Lyapunov time scales, this evolves effectively as a simple harmonic oscillator with some mild amplitude modulation. And this basically behavior arises because of the structure of this kernel feature. So the goal of this brief presentation, so let me move to the actual presentation, is to give some mathematical interpretation about how delay coordinate maps in conjunction with kernel algorithms allow one to extract such coherent features from potentially chaotic dynamical systems. Just to check that my slides are now visible.
Yes, they are. Yeah, can you move to the next one just to check?
Is that?
Yeah, that works. Yeah, thank you.
Okay, so yeah, so this is, I'm going to give a brief summary on some work we've been doing in this area of extracting coherent features of dynamical systems with kernel methods. And the main theme here is that the role that delay coordinate maps play in recovering coherent observables, the results I'm going to present should be applicable for a number, for a variety of kernel-based feature extraction techniques, including singular spectrum analysis, Hankel DMD, which are based on covariance kernels, and other approaches that are based on nonlinear kernels. So just very briefly to set the assumptions, we're going to be looking at measure preserving ergodic dynamics. If you want to have a concrete mental example of the systems that I will be talking about that satisfies all of the conditions shown here rigorously, the Lorentz 63 system is one, but the basic setup here is that we have a dynamical system with some ergodic invariant probability measure, which is supported on some subset of the state space. You can think of the Lorentz attractor, for example, as being the support of the invariant measure in the previous movie. And we observe the system by some observation map. Again, in the Lorentz 63 example, this could be the identity map on R3, if you wish. When we're going to use an operator theoretic description for the evolution of observables. So the sort of main tool here will be the Koopman or composition operators acting on the L2 Hilbert space associated with the invariant measure of the system. These govern the evolution of observables in L2 under the dynamical flow. And there is an associated infinitesimal generator for this unitary group of evolution operators that we're going to be using. So the general class of techniques we're going to study here is based on, as I mentioned previously, on delay coordinate maps. So the idea is that one starts from a time series that contains snapshot data, and out of it creates a higher dimensional time series by concatenating snapshots over some delay embedding window. So this is a very popular technique, a classical technique, I could say, used typically for state space reconstruction of partially observed dynamical systems. Here, the main intent here is not so much on recovering the state space in a topological sense, but rather in creating coherent features from kernel algorithms. So in particular, what we do, we take our delay coordinate map data and we create from it some kernel matrix, which we compute its eigenvalues and eigenvectors. So this would be some type of kernel PCA, if you wish, and that gives us certain the eigenfunctions here would correspond to features. So there are different choices that one could use for this kernel, including linear kernel, linear covariance kernels used in SSA, and equivalently in Hankel-based DMD, or also nonlinear Gaussian kernels. This class of kernels basically corresponds to the results I showed in the previous movie. But the main aspect here that I'd like to focus on is the use of this delay coordinate in constructing the kernel. So in previous work with my former postdoc, Shutho Das, we had studied this problem, the asymptotics of the behaviors of these kernel matrices in the limit of basically long delays. So the first thing to note is that as the amount of data that one has, and here is the number of samples, increases, basically one can think of these kernel matrices as approximating in a spectral sense some kernel integral operators on the acting on observables in L2. So this is sort of the object that we are approximating by our kernel matrices, and this converges by ergodicity in a spectral sense. But more importantly is what happens as the number of delay increases. So the main result here is that the integral operators that one has converge in operator norm and therefore in spectrum to a limiting operator that has the property of commuting with the Koopman operator of the dynamical system. So when you have two commuting operators, as is well known, these operators have common eigenspaces. And because this operator here, this kernel operator is a compact operator, its eigenspaces corresponding to non-zero eigenvalues are finite dimensional. And these are actually Koopman invariant subspaces where the Koopman operator is diagonalizable. So that what that means in practice is that if you take an eigenfunction of that limiting operator, it basically, as an observable, evolves using based on only, its evolution is based on only a finite number of frequencies. So in that sense, it has temporal coherence. In fact, in most typical applications, so unless there is very high symmetry present in the problem, these eigenspaces, one can, with some arguments, deduce that they will be two-dimensional in general, and they will capture a single, they will be associated with a single Koopman eigenfrequency, so they will evolve as periodic, as purely periodic observables. So in fact, if one takes an orthonormal basis of this two-dimensional, of a two-dimensional eigenspace of this operator, you can think of that as being the real and imaginary parts of a Koopman eigenfunction which satisfies this eigenvalue equation. So this gives some interpretation on the success of these kernel-based delay coordinate map techniques in extracting temporally coherent features whenever the system has these non-trivial solutions to this eigenvalue problem. But the kind of like the issue here is that when one is dealing with chaotic dynamical systems that have mixing, Koopman eigenfunctions are in fact, in L2 at least, are not an appropriate sort of theoretical paradigm, basically because there are no non-trivial Koopman eigenfunctions for such systems. So there is no non-constant eigenfunction in L2 that will satisfy this equation. So we have to look for some appropriate relaxation, or at least one approach would be to look at an appropriate relaxation of this problem. And what we're going to do here, instead of requiring that we recover elements of the spectrum of the Koopman operator or eigenfunctions of the Koopman operator, we're going to focus on the epsilon approximate spectrum and require instead that seek rather observables Z that satisfy this, in some sense, approximate eigenvalue problem out to some tolerance, epsilon. So this idea here of looking at the approximate spectrum came up during some discussions I had with Igor Mesic a couple of years ago. So I'd like to thank him for those discussions. Also, some recent collaboration with Gary Froiland that we've been having that led to some of these results, which I also like to acknowledge. So the sort of intuitive goal here is that we want to find observables that satisfy this type of equation with a small epsilon, so with a small tolerance, and for times lying in a large interval. So if you are able to find such observables, then they behave to a good approximation like Koopman eigenfunctions that should be characterized by essentially a coherent temporal evolution. So the movie that I showed is an example of such an observable for the Lorentz 63 system. Okay, so I'm just going to give a brief outline here of one result in the available time. So basically what we do here, we try to cook up an observable from eigenfunctions, or from kernel features of these kernel integral operators based on delay coordinate maps that is sort of preconditioned in some sense to behave like a Koopman epsilon approximate Koopman eigenfunction. So based on the previous, so the intuition from what happens when there are actually Koopman eigenfunctions, namely that the real and imaginary parts of these eigenfunctions can be found from kernel eigenfunctions, we're going to here just assemble two kernel eigenfunctions that correspond to two eigenvalues, kappa and lambda, and build this complex valued observable. Now, the other thing to note is that if we take an observable and look at its time autocorrelation function, this can be expressed as this inner product here with the Koopman operator. If this was actually an exact Koopman eigenfunction, this alpha sub t, this time autocorrelation function, would give you back the corresponding Koopman eigenvalue. This is not going to be the case here, but we nevertheless can compute this object even empirically. And likewise, if we have the generator act on these functions, this function psi, and they take the inner product with phi and take the inner product with psi, this would give you the corresponding eigenfrequency if this were exact, the real and imaginary parts of an exact Koopman eigenfunction. Here, this is only going to be approximate, but nevertheless, these are computable quantities we can evaluate using phi and psi. So kind of like the result here is that if you have an embedding window of physical time, capital T, so there are Q steps taken at an interval delta T, so long as these eigenfunctions phi and psi remain sufficiently isolated in the spectrum of KQ, so there are these parameters here that basically this gamma here measures how isolated are the eigenvalues kappa and lambda in the spectrum of KQ, and these deltas measure how close, mutually close kappa and lambda are. We're looking for eigenspaces that are close to one another, but separate from other eigenspaces. Then so long as these things exist, so you can find these bounds here, this is large and these are small, then basically you can guarantee that as the delay embedding window increases, you stay in the epsilon approximate spectrum. So this is an epsilon approximate eigenfunction with a bound that is basically inversely proportional to the length of the embedding window, and increasing linearly with the time interval, with the time evolution that you're observing a system, and some additional corrections. And similarly, you can verify that these approximate eigenfrequencies are related to the autocorrelation function, this alpha t, in this way. This tells you that the autocorrelation function evolves approximately as a periodic signal. So it has a sort of coherent, nearly monochromatic evolution at the frequency nu, right? So that's the so theoretically this is what is expected. Here I'm glossing some of the details. There is some additional errors having to do with here that you have a finite sampling, sort of discrete sampling in time, which I don't have time to discuss here. But let me just show some of the numerical results related to the movie I started with. So here are the spectrum of this kernel matrices, the leading eigenvalues computed either using no delays. So this is basically taking some type of like Gaussian kernel on the Lorentz attractor and without any delays. And this is using a delay embedding window, which is approximately 8 Lyapunov times. And what you can see here is that here, first, if there are no delays, there is no apparent spectral gaps or twofold degenerate subspaces, whereas when in the delay case, there are these two leading non-constant eigenfunctions. So I should say that these kernel matrices are all normalized to be Markovian. So the leading eigenvalue is always 1, and the corresponding eigenfunction is constant. So the first pair here of non-trivial eigenfunctions is well separated. There is a spectral gap, and it's nearly twofold degenerate, and it's also reasonably, in some sense, separated from the rest of the spectrum. So these are the two eigenfunctions I showed in the movie. This is showing in scatter plots what happens if you don't do any delay. So you get basically kernel features that look pretty much, they're not too different from what you get from principal component analysis. This is showing the evolution on as a function of time acted upon by the Houman operator, where you see that, again, there is this chaotic behavior manifested by mixing of the sort of the eigenfunctions, the level sets of the eigenfunctions on the attractor. On the other hand, when you do delays, you get this highly coherent feature, which basically retains its structure under the action of the Houman operator. So these are these leading to eigenfunctions, also shown in the movie, retains this characteristic shape over basically several Lyapunov times. And you can see this in this time series plot, which is again like a nearly monochromatic sinusoidal. This is showing that the autocorrelation function compares well with this theoretical expectation of it evolving as e to the I omega t. I was using nu in the slides as opposed to omega. At the frequency that one can numerically estimate using the generator. I didn't explain how this is done here. And so finally, just very briefly to close, I just want to mention that, besides these very idealized examples with the Lorentz 63 system, we're using these techniques to study aspects of climate dynamics. This is a joint work with Gary Froiland, Ben Lindner, Max Pike, and Joanna Slawinska that we're currently working on to study the El Nino southern oscillation of the climate system. I don't have very much time to discuss this here, but the sort of the kind of like punchline is that this approach using this kernel-based features leads to a representation of the El Nino southern oscillation with a sort of significantly higher dynamical coherence that one recovers using traditional approaches. These are so-called Nino indices for people who may have worked on related topics, which are much more noisy compared to the representation we obtain here. And there are some interesting consequences when it comes to reconstructing the mechanistic aspects of the El Nino southern oscillation.
Sorry, time is up.
Yeah, I'm done. Okay, I'll just leave this slide, and yeah, thank you very much.
Yes, and now I can move to the next speaker. Thank you.
Okay, I believe that's me, right?
Yes, exactly. Yeah, thank you.
Okay, let me try to share my screen here. Let me see. Yeah, this should be it. Let me know if this is. So do you see my screen?
Yes, we do. Can you just move to the next slide, because sometimes we don't see it when you move? Okay, yeah, working. Yeah,
Good.
thank you. Yeah.
Lovely. Okay, perfect. Well, first of all, I'd like to thank the organizers for putting this together. This is great, and always lovely to see a bunch of colleagues from their own homes around the world. So today, so my name is Guillaume Lajoie. I'm a associate professor at the Math Department, University of Montreal, and also a core member at MILA, the Quebec AI Institute. And I'd like to talk a little bit about ongoing work trying to disentangle roles of recurrence versus attention in sort of memory augmented recurrent neural networks. Before, again, the details, I'd like to acknowledge people in support for this work before the end. It's always nice to put faces on what's happening. So this is joint work with a group of very talented students and with a collaborator of mine, Joshua Bengio, some of you might know, and a bunch of funding here below. So typically what I'm interested in this talk today is computations using deep learning on input streams and sequences. right? And so this is not new. You might all know that applications of this are, for example, natural language processing, video, navigation, reinforcement learning tasks that are episodic, that kind of stuff. And these types of processing, well, we know that our brains do it very well, right? And some of the ingredients, I think, that support these sort of temporal processing and computations in brain circuits are first recurrent and dynamics, right? And so, well, recurrent connectivity, which implies dynamics, right? So there's this idea of temporal evolution of neural activity. And another ingredient that I'll argue is important for these types of tasks moving forward in deep learning is the use of memory, and namely mechanisms of attention to address these memories to complement and guide computations that happen in recurrent networks. And so these two ingredients, AI researchers took note. First of all, with the introduction of recurrent neural networks, or otherwise known as RNNs, which are well studied and used in a variety of contexts. And more recently also with sort of memory augmented self-attentive systems. And I'll try to introduce a little bit what I mean by that. And for further detail, I have a long format talk that's uploaded on the YouTube channel of this workshop. And so these two ingredients are very much leading the charge for state-of-the-art systems when it comes to natural language processing and auto-sequential tasks. But there's sort of an outstanding question. So we have good understanding of gradient propagation in RNNs, but we don't necessarily have the same level of formalism for attention augmented systems, right? So when I talk about gradients, of course, I mean gradients that are used to train these networks, gradients of cost functions. And we also have a good variety of inductive biases for RNNs and other deep networks, but not necessarily for attentive systems. So I'd like to touch a little bit on these 2 points here and try to move the field a little bit further into a formal understanding of the role of attention in concert with recurrence in these modern deep neural networks. Okay. So just by the ways of a little introduction, well, recurrent network dynamics can be seen a little bit as feed-forward dynamics, where essentially one can unroll a recurrent network through time and think about a bunch of these layers as different time steps, and with the particularity that weights and parameters between all these layers are shared, right? So it's the same as saying network is recurrent or unrolling it through time like that. And the typical way to train these networks is to do back propagation through time. So essentially propagating gradient back up these sequences of compositions. So here on the left, I have just a typical vanilla-like neural net RNN, which is essentially a very simple dynamical system. And the name of the game is to minimize an error of the output of this network, whatever that may be, through gradient propagation through this unrolling. Okay. And sort of the main bottleneck in training these types of systems, and the same is true for very deep neural networks, is the problem of vanishing and exploding gradient problems. Now, this is not surprising for a dynamical systems audience here, that if you compose a bunch of maps together, and essentially if you compute the gradient that flows through these maps, it's essentially a product of a bunch of Jacobians, then what you'll end up with is either exponential explosion or vanishing. If you have a spectra that are different from unity, essentially. And why is this a problem in training these networks? Well, to spell it out, right, it's basically, it becomes very hard to use information about the past to learn proper adjustments of weights. So if there's information that resides way in the past that's important for the task at a particular time, backpropagating through all of the different steps that separate these times erodes the information of the system, and that becomes a problem. And just one of the issues is basically that you have these product of Jacobians and they don't necessarily commute. And so it's hard to play with them and to reorganize them to keep this signal alive. So this is very familiar, right? Like this is very similar to how one computes Lyapunov exponents and the challenges of computing Lyapunov spectra. And so there's some solutions to mitigate these types of gradient propagation. A few of these solutions, for example, there's the idea of gradient manipulation, right? One can do some gradient clipping, some regularization, all kinds of other tricks. There's also sort of structural tricks such as gated dynamics, long short-term memory systems, or gated recurrent unit systems where essentially you're promoting different propagation at every time based on the context. There's also parametrized connectivity. You know, by the ways of imposing some structure in the parameter space so that say the connectivity matrix remains sort of orthogonal, for example. That's a popular one. And I know Ben, the first speaker, talked about this a little bit. So these are all tricks that one can fit in one category that I'll call, for the purpose of this talk, as parametric memory tricks, right? So if one thinks about it, right, the idea is that you want to use the parameters of the system to encode information about the past, or information that's relevant to process sequential input. And so you're encoding memory in the parameters of the system, right? And so this is what I'll refer to as parametric memory systems. On the other hand, there's some non-parametric solutions to the gradient propagation problem. And basically the idea is to say, well, we don't need to backpropagate through the whole thing. If we know that there's important information at particular time steps in the past, let's just use some skip connections of some sort, right? But this, in a sense, requires one to hold information in some sort of an external memory, right? And it's the interaction between this external memory and the recurrent dynamics that becomes an important factor here, or a bottleneck into making these systems efficient, right? So here are a few examples of memory augmented systems that tackle these types of problems. But a question that remains is how to get guarantees and formulas into the mission of incorporating memory in these computations. So this is a field of research that's very active, both in applications and in theory. And I just want to cite here two very influential, somewhat recent results that very much changed the name of the game in terms of natural language processing and recurrent dynamics, or recurrent information processing, sequential rather. The first of which is the introduction of self-attentive system, which is attributable largely to this paper here from, I believe, 2015. And the second, which is currently the state-of-the-art architecture for these large NLP problems, are transformers, right? So this is a paper here that was called "Attention is All You Need." That's from a few years back as well. So these are very recent sort of leaps in performance in these types of deep networks. But there's still a bunch of questions as to how to combine or how to really manage attention systems or self-attentive systems, right? And so I want to quickly skip over this because I don't have much time. I thought I had ignored these slides. So these are sort of brief overview of as how self-attention works. I encourage you to go check the long format talk. But I want to take a step back and say, in terms of attentive systems, one can think about it as a spectrum, right? On one hand, you have these sort of non-parametric memory systems, which are essentially transformers that rely solely on these skip connections. They do without a recurrence at all. They say, like, why use recurrence? Why we can just attend to stuff in the past and just learn something from scratch. And the other end of the spectrum, you have completely parametric systems such as recurrent neural networks. And somewhere in the middle, you have these semi-parametric memory augmented system, which I think there's sort of Goldilocks that happens here. And here's like, in a nutshell, the advantages, the pros and cons of both ends of this spectrum, right? So on one end, non-parametric memory system have robust learning and strong gradients, because by design you're skipping away from the eroding parts of these gradient propagations. And on the other, and they scale poorly. Usually they scale with the order of quadratically with the sequence length. On the other hand, we have unstable gradient. It's hard to learn, but you have compact encoding. And so what's the trade-off? How can we tackle these ideas of trade-off? And so the idea of striking a balance between sparse attention and between attention and recurrence is a field of study that's very active. The idea of sparsifying attention is very popular. Here's an example from NeurIPS from a few years ago, where one thinks about attention as being sparsified in the sense that one can restrict the number of points in the past that one can attend to at any point in time, and also restricts the number of states that is committed to long-term memory for attention, right? And so this has been shown to be effective heuristics, but they're not formalized. This is very ad hoc principles. And the results I want to showcase today are essentially a first attempt at formalizing these things, right? Which is can be found in this preprint that we have online right now. So in a nutshell, we're able to derive some theorems for lower bounds on gradient norms for propagation in systems that have recurrence and self-attention. And there's a few cases that depend on the task structure. So in the case that we form uniformly relevant, we get this sort of bound. So these important terms that are part of the gradient propagations that are lower bounded by 1/t, which is the sequence length. And more importantly, we have the case of sparse relevancy in a task, say that there are some important events in the past that are peppered through a bunch of events that are irrelevant for the task. And in this case, with a bunch of definitions and some assumptions, we come up with a bound that depends on the sparsity of both of the task and the depth of the what we call causal dependency chains between the events of the task. And then there's a few lessons that can be learned from these theorems. And essentially what comes out of this is we propose a new family of screening methods to help sparsify self-attention and to optimize the use of memory. So the idea is to balance complexity that comes with attention and sort of compact representation of recurrence. And the proposition here is the following. The idea is that one needs to screen for events for relevancy, put them in long-term memory to attend to future states, and to optimize this game of putting stuff in memory for use, but making it as sparse as possible. So here's a little a little cartoon of what's happening. The idea is that you go along these hidden states. And then what we propose here is a very simple instantiation of this example of relevancy screening, but it's a larger family is what we're proposing. But imagine that you have a short-term buffer which you can attend to using full attention. But once this buffer exceeds a certain time, then you have to decide whether or not a certain state is going to be committed to long-term memory or not. And this can be done in different ways. One can look at the integral of the attention scores of that state over its life span in the short-term buffer and decide to commit it or not. And then as you go, you decide to commit over and over again. And so you have two sets of attention, one on the short-term buffer, which can be seen as a short-term memory, and and another set of attention scores on the long-term memory, that's sort of stuff that's kept forever. And what we find is that we can strike this balance between sort of good training properties and low complexity costs in terms of computation. So on the left here, this is plots of gradients for a stereotypical sequential task. It's called denoise task. And I'm showing here vanilla RNN and LSTMs, which are purely recurrent networks. The gradients here either explode or vanish. So you're failing to train on these tasks that are extending to about 1,000 time steps. These non-parametric memory systems, like transformers and memory augmented systems, have very good propagation of of gradients. But if you look at the complexity of computation, so the max GPU usage as a number of time step, two of these sort of naive attentive systems blow up quadratically as expected. But ours, which is this purple thing, grows linearly. And that's because we're controlling the use of memory and trading off recurrence and memory where it matters, right? And we're also finding very surprising advantages of these types of buffering in attentive system, namely that we have surprisingly better generalization that their counterpart without this sparsity built into them. So this is some sort of these are results in terms of testing on reinforcement learning algorithms, tasks rather, and rel LSTM here. This is our relevancy screening mechanism on top of a self-attentive LSTMs, and we see that we generalize better than many other, than other sort of like baseline systems here. Okay, so I think I'm out of time here. Key contribution, just to summarize, is that we provide a set of theorems that are, we believe, the first formal treatment of gradient propagation in the presence of attention and recurrence. And these reveal some trade-off between attention and recurrence that we can exploit to propose a family of methods, namely that we call relevancy screening methods, that aims to streamline attention complexity and that surprisingly show some very good generalization properties that we're currently studying further. And so an outlook for future work in this direction: first of all, we need to come up with better relevancy screening. So the assumption that something that was well attended to in a short-term buffer is going to be well attended to later is not necessarily true for a number of tasks. Sometimes the predictive power or the surprising nature of an event could be used to screen for relevancy. And also, we need to understand better ways to store and address memory in these self-attentive systems. So instead of keeping past state as is in memory and attending to it, maybe there's some consolidation that can be done here, which is likely what the brain does in hippocampus dynamics. Okay, so with that, I thank you. I encourage you to go see the long format talk if you're interested, and I will relinquish my screen here.
All right, thank you very much. So next speaker is George Wynne. Are you there, George?
Yes, I'm here. Hold on.
Oh, yeah, yeah, all right.
Hello.
Okay. Yeah, go ahead. Thank you.
Okay, can you see the slides?
Yes, we do. Can you move to the next slide just in case? Sometimes they get stuck in the first page. Yeah, it's working. Yeah, thank you.
Okay, great. Thank you very much. So my name's George. This is joint work with Andrew Duncan, who's also at Imperial College like me. I'm a PhD student. And before I start, I want to say thanks to the organizers. I really like this format of conference where we can have these talks online. So I've got a larger version of this talk that's on the YouTube channel. So for this, I know there's a break coming up. I don't want to stand between people and their coffee. So I'm going to keep this short and sweet and quite general, and offer some perspectives on this kind of topic, how it interacts with dynamical systems. So the title of this talk is a kernel two-sample test for functional data. So hopefully I'm going to be able to talk what is a two-sample test, what is functional data, and what do kernels have to do with it. So first of all, a two-sample test, you have some set and you look at probability measures over the set and call two potentially different measures, P and Q. And you've got some samples, some Xi's from P, some samples Yi's from Q, and you want to do a statistical test with some controlled error to tell the difference whether P equals Q or is different from Q. So this is a really classically studied problem in finite dimensions on RD, and with some methods, these go back decades and decades. And now I'm going to be talking mostly about functional data though. So in this setup, our space curly X is going to be a function space. So each individual Xi and Yi is going to be a function. And for example, the trajectory of an SDE or some other dynamical system. In practice, as we're in the real world and we observe data discretely and store data discretely, the Xi's and Yi's will have some discretization scheme. And it could potentially be different for each sample, this discretization scheme. So you have inputs and outputs at different locations. So let's say you've got time series on 0, 1. You could be lucky and you could be observing a process uniformly or 100 different points, or they could be randomly sampled different input points. And if they are densely sampled, then whatever numerical computation you want to do with them, you can just put them in and you don't have to worry about it. But if they're more sparsely sampled, then the common technique is to fit curves to these data and then use those curves later down the line in your computations. So any algorithm which uses functional data has to take into consideration both the infinite dimensional nature of X and things we know about function spaces, and the statistical impact of fitting curves. So some existing approaches from the functional data analysis community often involve projecting one way or another to some finite dimensional representation, and then using a test based on this finite dimensional representation. So either you can project using functional principal component analysis, which is FPCA, and then use a genuine finite dimensional test, something like the Anderson-Darling test. Or another method is common, is you form statistics based on the function space, but those statistics will often involve infinite sums of your principal components. So then you truncate those infinite sums and use those statistics then. Another method is using empirical characteristic functions. So I'll touch upon this later. And again, this will involve some sort of discretization and some finite dimensional representation. So most of the existing methods within the functional data analysis community involve computing principal components somehow. So we're now going to move on to where do kernel methods fit into this picture here. So kernel methods, and we've been talking about MMD quite a lot in this conference so far, so I'm not going to talk about it too much, but in particular for testing. So this became very successful in the late 2000s and early 2010s with the work of Arthur Gretton, Alex Smoller, Bernhard Schulkopf, and collaborators. And the idea is you will take some kernel, and then you will use the kernel to induce a map from the space of probability measures into the RKHS of the kernel. And then you will use the distance between those embeddings, what's called the maximum mean discrepancy, and use that as a test statistic. And you form a statistic around this distance. Idea is if P and Q are different, then this distance is going to be positive, and you can somehow tell the difference in a test. And the reason that this is actually practical and useful is because the MMD can be represented as these double integrals of your kernels, which can be easily approximated using Monte Carlo methods. So the test statistic, just for kind of completeness, will look something like this. And the standard one has cost n cubed, where n is the number of samples. And this is important, it's the number of functional samples, not the number of observations per sample. So number of function samples is the dominating factor here as to what causes the slowdown in computational complexity. And there is a linear time estimator as well. But the key thing to realize in all of this is that informing the MMD, informing the estimator, and making sure it has the right null distribution when using something like Bootstrap, etc., none of that actually depends on the space that the kernel acts on. So commonly it's used in RD. So if some modern uses that it's seen in machine learning is training generative adversarial networks. So there you've got your image and you count the image as being in some high but finite dimensional space. So you can actually do these things, have kernels over different spaces. So what's interesting is now considering using kernels over function spaces, because nowhere in this computation would it require you to compute principal components. And the principal component computation part is the hang up in current functional data analysis methods, because that's actually what increases the variance of the test and kind of hurts test power. So using kernels presents a way that you don't have to make this extra computation in your test. So it promises potentially better testing power. The main thing though, the catch, is that for the test to be valid, you need a kernel to be what's called characteristic, meaning that this embedding is injective. So there's numerous examples of this for kernels over RD, for example, the Gauss kernel and the Matern kernel. But one of the issues is most of the proofs of characteristicness require X to be at least locally compact. And that's not going to be the space if X is an infinite dimensional Hilbert space, for example, L2 or a Sobolev space, which is a common setting for functional data. And one of the reasons for this is a lot of characteristics proofs are based around a similar concept or related concept called universality of a kernel, which is more about a kernel's approximating properties. And this dates back to when people would use kernel ridge regression or SVMs as the dominating, most performing method in machine learning. So there's lots of theory done about this in the early 2000s and some landmark textbooks by, for example, Steinvart and John Shaw-Taylor. But this doesn't allow such easy adaptation of the proofs to infinite dimensional spaces. So this has been the main hang-up. So our contributions in our work is we circumvent this hang-up by noticing a version of a proof technique for characteristicness which can be generalized to infinite dimensional spaces. So that makes the MMD a genuine distance metric on probability measures over these infinite dimensional spaces, for example, L2. And we can then look at this theoretical properties of MMD as it is now a metric. And for example, what topology does it induce? And does it have closed forms? So it actually doesn't have closed forms for Gaussian processes when you use a Gaussian type kernel, which I'll talk about in just a second. And also, what's nice about MMD is that as it's based on kernels, and kernels can be nice functions, for example, lots of kernels are Lipschitz continuous, you can use that to show that even if you observe your functional samples discretely and not really densely, and you have fit curves to them, that can actually, as long as your curve fitting is good enough, which we discuss in a more concrete way in the paper and the online extended talk, it will alleviate the statistical impact and you'll actually still get the same kind of performance you would have if you had the true samples. So the rough idea, and I don't have much time left, so I'm going to try and skim through this pretty fast, of where we get these kernels over infinite dimensional spaces from is as follows. There's a quite well-known theorem called Bochner's theorem, which lets you write kernel, K, as the Fourier transform, also known as the characteristic function, of a measure mu. So typical examples are for a Gauss kernel on Rd, which I showed earlier, mu will be a centered Gaussian distribution. And you can write MMD as a weighted integral between the L2 distance between the characteristic functions of P and Q. So if your measures are over infinite dimensional spaces, particularly an infinite dimensional Hilbert space, the characteristic function equation looks exactly the same as on Rd. You replace the Rd inner product with your Hilbert space inner product. And a result which was proven by Bharath Chaparambada and colleagues back in about 2010 was that if mu has full support, then your MMD being 0 means that P hat and Q hat is 0. And as the Fourier transforms are injective, that means P and Q are the same. So if you've got some measure on some space that has full support, if you know what its characteristic function is, and as long as it's a proper kernel, then that kernel will be characteristic. So luckily enough, we do have infinite dimensional generalizations of Gaussian distributions on Rd. These are Gaussian measures, which are essentially Gaussian processes, really. So we can use that, and we have closed forms for these things. And we can actually use these to build a solid theory about what kind of kernels then be characteristic. So if you take a Gaussian measure on some infinite dimensional Hilbert space, the characteristic function will look something like this, where C is going to be a trace class linear operator. And it's a standard result in Gaussian measure theory that this guy will have full support if and only if your C is injective. And it's really easy to actually come up with examples like this. For example, you can take the kernel integral operator for some other kernel K0, which will be acting on the base space which your functions are defined on. So this will be the main theorem of our paper, which establishes a very wide family of kernels for these kind of problems. And I'll skip now because the break's coming up. Other things we talk about are if you do treat your functional data as pointwise, then these kernels will naturally evaluate from a limit. And we develop a nice framework to construct kernels to incorporate knowledge about the signals. For example, periodicity, certain strengths of the Fourier transform, and certain smoothnesses. You can bake these in to this T map here. That's a hyperparameter in your kernel. And we do a numerical comparison against the existing methods mentioned at the start of the talk to show that we end up getting better power in most cases. And we believe the main reason for this is not having to compute these functional principal components. So a quick note on perspective. We think that the intersection of statistical kernel methods and functional data analysis is really at its infancy. And functional data analysis is related to dynamical systems because you can view trajectories of your dynamical systems as functional data. And we think that there's a lot more work that can be done to merge these two fields, really. And in particular, statistical kernel methods are quite more of a modern thing as opposed to more classic machine learning kernel methods such as classifiers and regressors. So main three things are testing, which is what I talked about here, but also independence testing can be done using kernels. Parameter inference can be done using MMD as a distance metric over your parameterized model P versus some unknown model. And approximation, again, can be used with these kernels over function spaces. So with that, I'll show you the references which I mentioned earlier. And I want to say thank you very much for listening. And I'll stop sharing my screen now and we can go for the break.
Hello, everybody. My name is Alex Terenin. I'm a PhD student at Imperial College London, and I'd like to talk to you today about efficiently sampling functions from Gaussian process posteriors. This is joint work with James Wilson, Vyacheslav Borovitsky, Peter Mostovsky, and Mark Dyson-Roth at UCL. This work won honorable mention for the outstanding paper award at the International Conference of Machine Learning. And with that said, let's get started. So first, I would like to consider a simple two-dimensional Gaussian. If you write F1 and F2 jointly to be random variables whose distributions follows said Gaussian, then the conditional distribution of F1 given F2 equals U is also going to be Gaussian with a certain mean and a certain covariance matrix. This is a classical result. This is, in fact, how we usually think about conditioning. We write down the conditional distribution, and then if we want to, for example, extract some kind of information from it, we might simulate from it or simply calculate what its moments are and work with those. However, a pathwise expression also holds. One can show that F1 given F2 equals to U is equal in distribution to the random variable F1 plus the difference between U and F2 times an expression involving the kernel matrices. And so let me illustrate the latter point of view. Here, we sample a random vector A comma B jointly from a bivariate Gaussian. And to obtain our conditional distribution A given B equals beta, we transform A comma B into A given B equals beta by calculating the residual and applying the update term. This expression lifts to a pathwise rather than distributional characterization of posterior Gaussian processes. That characterization looks like this. It says that the posterior as a function, well, as a random function more precisely, is equal in distribution to the prior plus an update term. In this work, we use this idea to design an approximation scheme whose complexity for a Gaussian process that has already been trained is linear in the number of points you wish to evaluate in, which is what we call linear in test time. In particular, to achieve this, we discretize the prior term with a random Fourier feature technique and the data term with sparse Gaussian process methods. That yields an approximation to the posterior that looks like this. Here we have a random Fourier finite dimensional approximate basis to represent the stationary prior. And we have a canonical basis using the kernel function to represent the sparse update. In the canonical basis, the weights depend on the values for the prior basis through the form that I've written here. Let's visualize this. Here, we start with the prior, which is the orange dashed curve. We approximately represent the prior using a random Fourier feature technique through basis functions shown on the bottom. We then look at the data we want to condition this Gaussian process on, calculate the residual between the prior and the data, and add the canonical basis functions from the update term shown at the bottom on the right to obtain our posterior draw. The notable thing about this approximation is that it yields an actual function rather than simply the values of the posterior distribution on some grid that's fixed in advance, which is how Gaussian processes are typically worked with. Because it is an actual function, once we have obtained the weights W and the weights V, we can evaluate it anywhere at linear time cost as opposed to cubic cost. Now I'd like to tell you about some applications of this technique. The first of them is Bayesian optimization. Here, we wish to use a Gaussian process to minimize an unknown function. And to do so, with as few evaluations as possible, we place a Gaussian prior on it and use the posterior to try to test the most promising points first when we minimize this function. When we look at the regret values, which measure performance, here lower being better, we find that our method in sufficiently high dimension outperforms all previous linear time methods that we considered, here in particular, a random Fourier feature approximation to the posterior rather than the prior. Unless the hyperparameter that controls the random feature approximation is raised to be sufficiently large, in which case it becomes very expensive and our method is much faster. We also note that and it's not pictured here, but this is in our paper, that if you're willing to pay a large enough cost and simply work with grids, we either match or exceed performance depending on how much computational cost you pay. And so overall, we find that this technique yields improved performance owing to smaller error. I'd also like to show you a showcase of using this technique to simulate unknown dynamical systems which are learned from data. Here, we consider learning a Fitzhugh-Nagumo model neuron dynamical system from data by placing a Gaussian process prior on the right-hand side of the differential equation that defines the system. The orange is a standard Gaussian process using a grid, essentially, where to simulate forward in time, you need to iteratively recondition the process at cubic cost. The blue is our method. The computational cost for the orange case is cubic, and for ours is linear. And we find that the approximation error introduced by our technique is small enough that it yields essentially the same qualitative behavior. In particular, we also consider the Wasserstein distances between the distributions compared to a expensive ground truth simulation. And we find that these are, in spite of us being substantially cheaper than the standard approach, we find that the error is essentially comparable. And in total, this technique enables accurate time stepping with linear rather than cubic cost into the number of time steps simulated forward. And this is actually all that I have for today. So I want to thank you for your attention. I want to maybe also draw a little bit of attention to some additional results that are in the paper, but I didn't put them into my slides because of concerns about time. And it appears, based on the clock that I'm looking at, that I'm actually severely under the time limit. So wow, that went a lot quicker than I expected. The additional results we have in our paper is a little bit of simple error analysis. In particular, we proved that with this approximation, the approximation error in the posterior is controlled by essentially all of the individual terms that we make an approximation in. So because our technique works by approximating the prior, in particular, we show that the approximation error in the posterior is controlled through the approximation error in the prior. And we spell out all the constants in that inequality and these kind of thing. This is done both in Wasserstein distance and in, I believe, supremum norm of the kernels, if I remember correctly. So there's a little bit more mathematical content in there as well. And yeah, I'm happy to take any questions that anybody might have. Thank you very much for your attention.
All right, thanks a lot. Yeah, so there's probably 5 minutes. Actually, 3 minutes.
So
yeah,
I apologize for the slight. Usually, I'm worried about being overtime, and I think this might be the first example that I can think of as recent memory where I ended up severely under time. So I'm happy to take any questions that somebody might have.
No, that's very good. Thank you, because it's good to have people finishing early than later. Yeah. Yeah, okay, if there are no questions, Nicolas, are you here? Can you start sharing your screen?
Yes, I can.
All right, thank you.
Thank you.
Yeah, all right, then so our next speaker is Nicolas Nelson from Caltech, and he'll be talking about the random feature model for input-output maps between function spaces. Yeah, thank you. You can go ahead, start. Thank you.
Okay, yes, thank you for the introduction. This is joint work with my advisor, Andrew Stewart at Caltech. And my talk today will essentially summarize a recent preprint that we have on the archive, whose code you can find here right on the title. So let's get started. So I will now describe the problem setup that we're interested in today. We are interested in approximating potentially nonlinear operators, say F dagger, that map between spaces X and Y, where X and Y are infinite dimensional spaces. Such operators appear a lot in applications. One popular example is shown in green here. And it is an example of an elliptic PDE solution operator, which arises in uncertainty quantification, for one example. This example operator, F dagger, it maps A, which is a function, in particular the coefficient appearing in this PDE, to the solution of the PDE itself. So U, the solution, is a function, can be viewed as a function of A, the coefficient field. Now, from a numerical perspective, this is essentially a high-dimensional function approximation problem. If you say you discretize your input and output spaces with, say, a finite element discretization, you would obtain a mapping capital Fn, which maps from Rn to Rn, two finite dimensional Euclidean spaces. Now, these days, machine learning is a great tool that is been shown to be very successful in approximating such high dimensional functions. However, these tools currently do not really take into account the fact that these Euclidean spaces actually came from infinite dimensional spaces to begin with. So I'll try to explain why we want to take that perspective first. So again, our motivation in this work is these many query applications where you have some, say, black box or expensive computer model that requires many evaluations at different particular parameter points. So this could be any outer loop applications such as inverse problems or control or optimization and design. So the idea of this work is, can we use data to build a non-intrusive, essentially black box emulator for that mapping F dagger? And really the key to the success of our framework is to first design our emulator of this operator as an object in function space. So on the function space level, and only then discretize. This is as opposed to starting with the discretized formulation of a map between two finite dimensional Euclidean spaces and designing architectures there. So let me show what happens if you do the latter. So this is an example from the paper of Zhu and Zabaris, where for the same elliptic PDE problem that I showed on the previous slide, they are using a very nice novel convolutional neural network architecture to approximate the discrete solution operator that map from Rn to Rn. And it works very well on the grid size that they designed. So on that grid size, they get less than 2% relative error at that resolution. However, because their architecture implicitly depends on that resolution parameter n, say the number of finite element degrees of freedom, as the resolution of the model that they have is increased, the error you can see kind of increases in this unbounded way, even though you can retrain at each resolution. So our work, by taking the function space perspective, we design a model that is independent of any resolution parameter. So in that sense, we obtain a consistent approximation, which essentially flattens this curve down so that at all resolutions, the approximation error is constant. The essential backbone to the methodology is simple. We're just using supervised learning. So we have some input and output spaces. We have a data set. And we also choose a parametric model class. Now in this work, we're using the random feature model class, which I will get into pretty soon. So we want to find some parameter that controls the parametric model class. We want to find an optimal parameter such that our model is a good approximation to the target operator, f dagger here, where of course we only have point evaluations of f dagger through the data set, and we don't have access to it. To train the model, we simply minimize the empirical risk as is standard by averaging over the L2 error over the training data set. We're interested in regression here, so we choose L2 error, but for more general classification problems, you would choose a different loss function. All right, so now on to the model class. We are using the random feature methodology. So essentially, the random feature models are really just linear expansions in random, in this case, operators. So to define one, you need to have one, a mapping varphi, which is called a random feature map, and it's deterministic. And you also need a measure mu on the space theta here. Theta enters in the definition. And so for a random draw from mu of a parameter theta j, varphi then defines a mapping from x to y that's random. So you have this expansion in these random operators. And this is really our model class where the parameters are these alpha j's. Okay. One can take a neural network perspective by choosing these varphis to be simply like a hidden neuron family. So an activation function applied to an affine linear combination of the input A here. The difference though between random features and shallow neural networks such as this is how you train it. The only parameters that are tunable for random features are the expansion coefficients, alpha j. Whereas for the neural network, not only would you have to learn alpha j, but also the wj's and the bj's, the weights and the biases. Right? So in this sense, random features are simpler, but that's essentially, we argue its strength in that we obtain convex optimization problems when it comes to training time. So let me get into that a little bit. This slide is a bit busy. I apologize for that, but let me just try to hit the main points here. So although the random features may seem a bit unmotivated, there is a lot of theory connecting it to kernel methods in particular and reproducing kernel Hilbert space. So what you need to know is that a random feature map induces an operator valued kernel, which takes a value in the space of linear operators from the function space y to the function space y. And it's defined by this formula on the left side of the slide. And in particular, the associated RKHS, which is a space of operators mapping x to y, is essentially has elements as functions that can be written as the expectation over the random feature mappings, like this. So these are essentially integral representations of operators. Now, a natural regression problem to solve in this setting is the standard kernel ridge regression problem, where you minimize this cost functional over the RKHS, where the cost functional is really your data misfit plus an RKHS regularizer. However, by the representative theorem, we know this is actually quite hard when the space Y is high or even infinite dimensional, because it leads to block linear operator equations where you must solve for n different functions instead of n different numbers or scalars. So to go around this, the random feature idea really just takes a parametric approximation to this. So instead of having the expectation in the kernel, the random feature model replaces the expectation essentially with the m-point empirical approximation, so that this kernel becomes Km here, and this new kernel Km leads to its own RKHS, HKM, which is a finite dimensional RKHS, which is explicitly given here. And we show that by simply optimizing the random feature model with linear regression using the supervised learning framework that I previously introduced, the model as a function is exactly the minimizer of the functional J lambda, with K mu replaced by Km and optimized over this finite dimensional RKHS. So in some sense, it's really an approximation of the non-parametric problem. Great, so we know now how to use this model, how to train it with linear regression, and it's convex, so it's very easy to do computationally. So let's see how this works for a high dimensional problem, or in fact, infinite dimensional problem. So here I'm showing a target mapping defined by the viscous-Burgers equation. This mapping is the equation's evolution operator or time one flow map. So the mapping F dagger sends the initial condition of the equation A here, which is a function, to the solution of the equation, which is a nonlinear PDE, at some fixed time t. Okay. So to kind of visualize what this is doing, let's take a look at the left figure. So suppose we draw some random function a and call that our initial condition. That's what I'm plotting in the black dotted line here. And then the response under the mapping F dagger of a is the red dashed line. That is the truth from a high fidelity solver. And we trained a random feature model here. If you want to see the details on the design of those mappings, I will refer you to the paper. But once we trained it using the linear regression framework on the previous slide, we obtain the model, and the model, when evaluated at this initial condition, gives us the blue test curve. And so you can see they're right on top of the truth. So it's a very good approximation here. Now, repeating this process many times, we can form a test set and compute the error between the test and the truth. And that's what we're showing on the right figure. So I'm plotting the averaged relative test error over the test set versus the resolution that we use to train the model. So because we have this function space viewpoint, we actually can now see from this figure some nice properties emerge. One is that for a fixed color on this plot, you can see that the error remains constant as the testing resolution increases, which is exactly what we wanted, because we wanted a consistent level of approximation so that in the limit of infinite resolution, we still have a controlled constant error. So that's why these curves are flat. But each of these colors indicates a different training resolution. Because the model is defined on function space, there's no notion of resolution. So you can pick to train the model on, say, a low resolution data set, and then evaluate it at arbitrarily high resolutions, which is in some sense a super resolution ability. And so you can see the effect of the different training resolutions, whether it's low, 65 grid points, or higher, 1025 grid points. The error isn't really affected much by the training resolution, which again indicates that we're truly capturing a mapping between spaces of functions instead of spaces that are Euclidean spaces. Okay. So to summarize, And again, I want to refer you to the paper for more details, but we have developed this random features methodology for the data-driven approximation of input-output mappings between function spaces. Really the key to have these nice properties is to first formulate our architecture in the continuum level, and only discretize at the end when we want to compute things numerically. We gained flexibility through mesh transferring and super resolution, consistency in the approximation, so in the sense that the error is consistent as the resolution gets arbitrarily high. And of course, it's practical. So this is a fast, low-cost method that by design scales very well to high-dimensional inputs and outputs that arise in practical science and engineering applications. And with that, I'd like to thank you for your attention.
All right, thank you very much. So I think next speaker is Ofir. Are you here? Can you share your screen?
Yeah.
Oh, yeah, okay.
Hey. Okay, is my screen visible?
Yes, yes. Can you move to the next page? Because when you put it full screen, usually it doesn't work. Ah, yeah, it's working, yeah. All right, good, yeah. So our next speaker is Ofir Lindenbaum, who will be talking about local conformal autoencoder. Yeah, thank you.
Thank you. Okay, so this is a joint work with Erez, Felix, Tom, Matan, Yanis, and Ronald Koifman. And I'm from Yale University, but we're all pretty diverse in terms of affiliation. And I'm going to talk about our work in local conformal autoencoder. So the setting that we're tackling is a very general setting, I think. And that is that we have observed some physical system, and we have some measurement device that is allowing us to learn some properties of this physical system. And then we're going to try to learn to use data science to extract those properties from the physical system. For the physical system, we're going to consider it to be a path-connected latent manifold that I'm going to denote by X. And this X is a subset of our lowercase d. So in this cartoonish example, you can think of a coronavirus moving on a surface of a cell, and we want to learn the properties of the surface of a cell by measuring some indirect properties of the coronavirus. So for the measurement device, we're modeling this as a diffeomorphism. So this is going to be a function f from lowercase d to capital D. And importantly, this function is invertible in this case. So let's illustrate an example and define our goal. So we want to be able to recover X given observations from Y. So we're looking at discrete samples from Y, which are samples from the latent space X. This is the physical system that we can't really access. That's pushed forward through F. And given those observations, we want to recover X. So in this example, X is just a square. It's just a samples uniformly spread on a square. And that's pushed forward through F, which is just placing the square on the unit sphere. So this function is invertible. And now my first question is, given these samples on the right, can we recover X on the left? So in this current setting, this is clearly still impossible. Perhaps we can do this using some prior on F or some prior on X, but without these priors, this is impossible. However, we can try to embed the data in the lower dimension D using some dimensionality reduction methods. And there's a special example. If F was linear, then using PCA, this process would work and we would get something which is a good representation of X. There's many methods for dimensionality reductions. We can, there's linear methods like PCA, MDS, or kernel methods like Laplacian eigenmaps or diffusion maps, and also differentiable methods. And in this example, I want to illustrate that using different methods, we can get different results by embedding the data, this three-dimensional data in two-dimensional space. They all preserve different properties of the data. And the key problem in this case is that they're actually trying to preserve properties of Y and not properties of X. And we want to try to develop a method that will preserve properties of X. Towards this goal, we're going to use something which is called a burst sampling scheme. You can, after I'll explain this, you can think of this as sort of a prior on X, but it's applicable for any type of X, so any type of physical system. And the idea was suggested by Singer and Koifman in 2009, was to model points in the latent space in the physical system as bursts. Those are small random walks around different states of the system. And we're going to measure M realizations of these bursts in the observation space Y. So we can think of the random variable X, which is placed around the specific states of a system Xi, can be thought of as a small coronavirus just moving on a cell. And we're observing this using the nonlinear function, observation function, as a random variable Y, capital Yi. And we're going to observe realization from this variable. What Koifman and Lafon did is they used this sampling scheme to define the following procedure. That is, they take the pseudo inverse of the random variable Y, the empirical, using the empirical covariance. And then they define the anisotropic diffusion kernel that uses a local Mahalanobis distance. And then this local Mahalanobis distance is correcting the deformations locally. And by looking at the eigenvectors of the normalized Laplacian, they get a global embedding, which provides the dimensionality reduction in this case. And you can see here the result on the previous example, which is much more coherent with the actual square, but suffers from some deformations on the boundary and sparseness in the middle of the shape. So at this point, you can probably ask, well, when is this burst sampling scheme realistic? Or what are the applications of this sampling scheme? So I want to point out some examples of people that use this for practical applications. So both Singer in the original paper and De Silva used this for sampling, for learning dynamical systems. This was also used for single site localization by Talmon and Schwartz, and also for reconstruction of cracks. And both the last two applications were done using audio signals or Wi-Fi signals, and the bursts were obtained by just using a sensor array. So the sensor array is a modeling the sort of a random walk around a specific state. So our goal, going back to our goal, are going to build a method for an isometric embedding. That is a metric embedding that will be isometric to the original space X. There have been methods that attempted to do isometric embeddings, but again, they're trying to embed to find an embedding that is isometric to Y, the observed samples, not to X, the latent physical system. Let's define our goal. So in the Euclidean setting, what we want is that samples observed in Y push forward through our embedding function. The distance between all pairs of points in the push forwards representation is going to be exactly equal to the Euclidean distance in the original space, latent space X. What we can do is we can apply Taylor expansion to the left side. And by neglecting higher order term, we get this following objective, which is on the Jacobian of the desired function rho, composed with the unknown function f. So this is a different objective, but in fact, both of these objectives we can't really use because we don't have access to samples in the latent space X. However, at this point, we can use the burst sampling scheme and the following lemma, which tells us that if we have a function that is injective, then for random Gaussian variable X, if we look at the covariance of the push forward random variable, that is X push forward through F and rho, if you look at that covariance and divide it by the original standard deviation of the Gaussian, then that would be that will allow us to approximate the Jacobian multiplied by the Jacobian transpose of rho composed with F. And if sigma is a small number, if the covariance is very small, then this could be a good proxy of the Jacobian. And if we embed the data in a dimension k, which is equal to the dimension of the latent system d, then we can get the following objective, which is that the covariance of rho applied to y divided by sigma squared should be equal to the identity matrix. And now we have an objective which is realizable in the sense that we can evaluate rho without having access to samples in the latent space X. And we define this following objective, which is what we call a whitening loss. It's an objective on all of the observed bursts, and it is the Frobenius norm between the empirical covariance divided by sigma squared minus the identity matrix. And we add to this another objective, which stems from the fact that if F is invertible, then rho should also, if rho would be the inverse of F, then rho should also be invertible. So we define an additional objective, which is in fact the reconstruction loss. That is that there should be another function rho that is able to invert gamma that should be inverts rho. And both of these losses together can be formulated as a special type of autoencoder, which we call local conformal autoencoder. And this autoencoder is both trying to reconstruct the original samples. And in this cartoon example, you can see that a burst, which is an ellipse in the observed space, is corrected to being a circle in the embedding space, and then corrected to being a ellipse again in the reconstruction space. So training both of these together is what we call local conformal autoencoder, and the embedding space should be isometric to the original space X if we have infinite samples. So let's see examples. We start with the square on the left. We push it forward to the observation space using a what we call a mushroom function. So this is an invertible function. We use the training set, which is between the green and black squares. And we train the local conformal autoencoder to attempt to correct the small burst. And in this slide, you can see on the left the corrected or embedding space, which is or a result for correcting the mushroom. And you can see both the training set, which is between the black and green squares, and the extrapolation, which is outside of the black square, and interpolation, which is within the green square. On the right, we're evaluating the isometric properties of the result by comparing the distances in the embedding space to distances in the original space, latent space X. And we were showing them both for interpolation and extrapolation and within the training frame. The next result is a semi-realistic result. Here we printed out a page with tiny bursts, which are just small Gaussians. We deformed this square just by sticking the page on a table. We take a picture. So we have a 2D observation of this structure. And then we estimate the burst using a clustering procedure. And we train the local conformal autoencoder to try to recover the inaccessible latent space, which in this case is just a square. In this slide, we can see on the left the observations, which are this deformed structure, reconstruction, which should be close to the observation. And on the right, we can see the latent space, which we did not use for training, and the recovered space, which is the embedding in this case, which was registered using a orthogonal transformation just for visualization to see where we've managed to correct the deformation when we got deformation on the top right and bottom left corners. In the next example, we've used the floor plan of one floor in MIT, and we've simulated 17 Wi-Fi transmitters by randomly placing them across the floor plan. And we've simulated an exponentially decaying Wi-Fi signal that is measured across the floor plan at different locations using a circular 6 antenna Wi-Fi array, sensor array. And then using this 6-dimensional observation samples, we try to embed them in 2-dimensional space. And on the right, we're showing the actual floor plan overlaid by the embedded floor plan to demonstrate that in this case, again, we're able to embed the 6-dimensional observation in the true representation that correspond to the physical system, which is the floor plan in this case. As a last example, I'll show a Lorentz system. Here we use a Lorentz system, a stochastic Lorentz system. That is, we have a Brownian motion added to each coordinate. This is a isotropic Brownian motion, so the coefficients in all coordinates are the same. And we're going to apply a nonlinear transformation to this Lorentz system to get the observation space. So on the left, we're illustrating the Lorentz system. On the right, we have the observation space. In this case, it's 10-dimensional, obtained using this function that's written in the bottom. So we have a linear part and a nonlinear part, which multiplied by the Legendre polynomials. And using these observations on the right, we're going to apply the local conformal autoencoder and observe the embedding space and see if it corresponds to the true parameters, which are the parameters of the Lorentz system. So here on the left, I'm showing the embedding space, again, after correcting using a orthogonal transformation. And on the right, we can see the isometric property of the embedding, that is comparing the distances in the embedding space to distances in the latent space X. To conclude, I think the key part of this work is to motivate the burst sampling scheme, and that is that this work is showing that if we can design experiment where a burst sampling scheme is practical, then using this type of autoencoder would allow us to get a good representation of the data. And the second part was to show that the neural network ansatz that we use was a good ansatz for interpolation and extrapolation. And in the future, we're going to try to look at multi-scale extensions of this procedure, namely that using different Gaussians or different random walk schemes at different locations, and also for estimating the scale of the Gaussians at the different states of this physical system. All right, thank you for your time, and I'll be happy to take questions.
Yeah, all right, thanks a lot. Yeah, so there is time for, 1 minute for questions, if there is anyone. Yeah, all right. Yeah, so yeah, if you have questions in the meanwhile, you can just write them on the chat or on the Zulip channel for later on, yeah. Okay, thanks again, thank you.
Thank you.
Yeah, so Marco, are you here?
Yes, I'm here.
All right, good, thank you, yeah. I think you can start sharing your screen. Yeah.
Okay, let's see if we can manage. So desktop, hang on a second. I need to allow Zoom to do stuff on my computer. Okay, I need to restart Zoom. Sorry for sharing permissions. Just a second.
Yeah, all right, yeah.
Okay, so host disable attendee screen sharing.
Yes, yes, where are you exactly? Sorry, I don't see you. Okay, now I see you. Okay. So I'm going to give you a co-host status.
Okay.
Yeah, okay, now you should be able to share your screen.
Yeah, I think so. So let's see if I put this on full screen. Let's see. Can you still see it in full screen?
Yeah, issue with full screen is that we usually when it moves from your side, it doesn't move from here. Can you change to the next slide? Sorry.
Okay. So let's see.
Okay, yeah, it's working. Yeah. All right.
Yeah, but now I think you see other stuff that you don't want to see, like the Zoom. So maybe now it's fine.
Yeah, now it's working with because we had some. Yeah. All right, okay, go ahead. Yeah, thank you.
Okay, thank you very much for inviting me, guys, and for organizing this. I am Marco Gallieri. I'm a senior researcher at Nascence. We are a company that works at the intersection between artificial intelligence and process control. And today I will present you a summary of recent research activities that we've been doing for the past 2 years, almost 3 actually. At Nascence, some of them are already going into production into some of our products, and others are more open-ended research areas. All of them cover the topic of safety, which is the main topic of my research team. Okay, so why safety, right? So we know that the industry is heavily regulated. There are many standards to be met. There are often hard constraints, for instance, constraints on human-machine interaction, constraints for processes that do precision manufacturing, for instance, glass manufacturing. We work with Schott, is one of the world leaders in glass manufacturing, and also, of course, repeatability. So how do we bring artificial intelligence, reinforcement learning, deep learning into the picture? Well, first of all, repeatability, and constraints, they are something that need to be addressed. And perhaps we can learn something from control theory, for instance. So I studied model predictive control many years ago, and there has been a lot of effort in recent years to work at the intersection of machine learning and tools like model predictive control. For instance, we can frame the problem of safe decision-making in terms of respecting the constraints of the environment, in terms of remaining controllable. So this means the ability to return to the initial state if we started from a safe state, and more in general, the ability to continue to work. So imagine a production line where you want to do artificial intelligence. Maybe you want to learn on the production line, but if you do so, you still want to be able to continue to work. You don't want to restart the system all the time because you lose money. And that's where the safety really comes in. So what do we do in this work, in this research area? We basically looked into neural network models and using them for robust control by means of tools from formal verification. So we present a few papers. So we published 4 papers in this area in several conferences, including ICML and NeurIPS and iClear. And then I will also discuss 2 newer papers. One is a workshop paper, and then the other one is still in progress. It's unpublished, but we kind of made it public on arXiv as it's kind of becoming standard practice these days. So let's start from the first one. I'll just give you a brief overview of each of the papers, and I will recommend you to look at the talk that is on YouTube, of course, which should cover more details of this. And of course, we can discuss as we go and during the coffee break. So when I joined NASANS, we started to work on the following problem. This is a classification problem that we want to solve by means of an unrolled architecture. So what does it mean? It means we are developing a neural network that is actually a deep neural network, but it's made from the unroll of an RNN or several RNNs. In this case, I don't know if you can see my pointer, but in our architecture, we'll have several blocks. Each of them is a particular type of RNN. We chose the residual layers because of their similarities to dynamical systems, in particular to the Euler discretization method. So each block is a different residual with a different state dimension, a different input dimension. And in between, we put a batch normalization layer, or we put a dimensionality reduction layer with some normalization, for instance, weight normalization. But in this entire block, we don't do any normalization. We just unroll the dynamical system. So what kind of properties do we want from this dynamical system? We would like to be able to do adaptive computation. We would like to be able to change the amount of layers or depth that is required depending on the data, so that the machine is smart enough to understand where it can stop, where the inference is satisfactory enough, and it can also have the ability to run forever potentially, or up to a maximum number of iterations, but we want to do this safely. What does it mean? Well, many of you will be familiar with the problem of exploding gradients, for instance, and vanishing gradients. So when you train over a very long sequence, you basically can often have your gradient descent algorithm not converging because the gradients are badly behaved. One example of this is gradients that disappear after many iterations, or gradients that explode or do crazy stuff after many iterations. And this is typical when you apply the same function many, many times, as in RNNs or as in these architectures. This, of course, is related to what we call stability of the dynamical system that the RNN induces, right? So if the dynamical system is unstable, we can actually show that there is an exploding gradient problem if we propagate for long sequences. If it is highly stable, then you could get a vanishing gradient problem, but this is less of a problem than the exploding gradient. The exploding gradient can also mean that the gradient changes sign very abruptly, and you cannot really learn. So the effects of stability can be seen here on the right, where we have our architecture that we call NASNet, which is basically an extension of the residual network, which is on internal state. So it's like a residual RNN fundamentally, but it will have a special property on the weights of the recurrency that I will describe in a second. So if we look at this type of architecture, right, if we don't have any formal guarantees of stability on the architecture, you can see how the activation for a single neuron NASNet progresses over time. So the colors indicate different time iterations of the recurrence. And we basically plot the output as a function of the input for this, right? And so you can see that after 100 iteration, you almost get an infinite slope. And so basically this means that the whole thing is unstable, you will get exploding gradients. If we use ReLU as an activation function, you can see that the slope is also basically going to infinity. So what we did is that we devised a reprojection of the weights in the recurrent part of the network. So this matrix A, we project the matrix A into the unit circle shifted with the center of -1 in the eigenvalue space in the, let's say, in the complex plane, basically. What does it mean? It means that we are basically projecting the weights into the manifold that gives you asymptotic stability of the dynamical system. That means that the trajectory of this network will eventually converge for a constant input, right? So here you can see at the bottom figure that with our stability projection, you can apply the same input for 100 of iterations, and then at some point, the network just converges in both cases. We also noticed that by the choice of reprojection that we did, the network actually simplifies in activation the more you go ahead. So at the beginning is more nonlinear, and then it tends to a linear for the case of tan H, and then it tends, of course, always to a ReLU for the case of ReLU. So this is quite interesting. How do we do this? We basically take the Jacobian of the network. So we consider the activation function. Since the activation functions are simple, then we can easily do the projection on the weights. And we have a projection for fully connected and also one for convolutional layers. The convolutional layer is quite nice and neat because the convolutional layer can be seen as a Toeplitz matrix, of course, but we never computed the Toeplitz matrix. We managed to move all the eigenvalues of the Toeplitz matrix just by moving the coefficients of the kernel without actually computing the Toeplitz. So we tried this on a few problems, on Cypher 10, for example, and we noticed that actually the network also learned through a stopping criteria to distinguish between images with different texture and to give different processing depth. So it will unroll more for frogs, for example, with a very simple background, and it will unroll less for a more dense background, which is quite interesting. So this was the first work, and it opened up a lot of things because we linked basically dynamical system with deep neural networks, and it opened up to a series of investigations that we did. The second one that was presented at the IFAC World Congress, it's a collaboration with the Polytechnic of Milano. It's more to do with control systems. So then we wanted to answer the question, can we actually bring the insight that we gained from NaseNet back into the world of control systems? So we devised a new type of neural network that we call TastinNet. Basically, this TastinNet is similar to a residual network, but it's a second order dynamical system, and it has a second order discretization in the velocity integration. So what we do, okay, we have a feed-forward neural network that predicts accelerations, right? We predict second order derivatives fundamentally. Then we integrate them using the Tastin second order integral, numerical integration, and then we obtain a set of velocities. Finally, we obtain a set of positions by integrating again, just with Euler in this case. Basically, we have a neural network that has even more skip connections than usual. And we know the skip connections are actually good because they help with gradient flow. Then the whole thing is reconnected on itself and the network is unrolled like an RNN, where the only hidden state is basically the velocity. So we tried this for a problem in control. We wanted to do adaptive control of a robotic arm in 2D, which is like a double pendulum with two actuators. So what we did, okay, we learned in batch with standard, a truncated backprop through time. Then we tested this with an adaptive model predictive control. So we wanted to simulate the fact that when we develop a control system and we bring it to the real world is slightly different from the simulation that you had, and probably you can have a distributional shift in your outputs. So what we do is that we use this model within a model predictive controller, So we plan over a finite horizon, and we decide what is the best torque to take to stabilize the double pendulum to the upright position. But since in practice we change the physical properties of the pendulum when we test it, we change the mass and we change the damping, then we use an adaptive scheme to re-estimate part of the model. So we focus on re-estimating only the very last layer of the MLP here. That was also interesting because it reduces the dimensionality quite a lot. And we did that using the unscented Kalman filter. So the ones who don't know what it is, I suggest to look it up. The unscented Kalman filter is similar to a particle filter. It's a sampling-based filter, but it has a deterministic sampling methodology, and it has a finite number of samples that scales linearly with the number of variables that you need to estimate. So we use this, and we kind of demonstrated that if you don't have adaptation, even with a perfect model, you can go very easily unstable when you change. But then we demonstrated that with our adaptive strategy, we can actually recover stability, and we can manage to swing up this double pendulum, even with a significant difference in the physical parameters from what we initially thought. Right, so this was the second work. Then we went on to investigate the use of continuous time models and the learning of continuous time models with a continuous time formulation. So the model that I presented before is actually suitable for continuous time data, but it has a discretization. It has an Euler step, and it also has a Tastin step. You can still learn sequences that have irregular sampling with it, but of course the discretization can cause numerical trouble. And this is often the case, especially for things like neural ODEs. So neural ODEs have been recently introduced. They've been used for several things. We decided to use them for system identification of basically in a car scenario, as you will see in a minute. We want to identify the model of a car fundamentally, or of many cars that interact with each other. Right, so what did we do? So we noticed that when you try to learn an ODE, if you discretize it with Euler, of course, you always introduce an error. So if you want to learn a model that captures long-term dynamics and short-term dynamics, you need to do a lot of iterations, and eventually your model could get unstable, the gradients could explode. So usual story, right? Some people propose to use the adjoint method from optimal control. This is a method from the 70s. It also has the same problems, actually. So it is more memory efficient, but it still has the same problem, because instead of using the integrator in the forward pass, you use the integrator in the backward pass. So you use Euler or whatever integrator to compute the gradients, to solve the adjoint. And this can still run into problems. You can still get an exploding gradient. We devised the method to learn a differential equation for a simplified case where you measure all the states, or where the states that you don't measure are derivatives of the things that you measure. How do we do this? Well, we split the problem into two. We take the problem and we remove the dynamic constraint through the solver, but we instead penalize the residual on the continuous time derivative estimation error. Right, so we basically split this into a series of one-step prediction problems, and we learn a surrogate of the trajectory through Legendre polynomials. This is quite nice, results in an alternate learning method where we basically alternate the learning of a representation of the trajectory through a Legendre polynomial, which is nice. It's infinitely differentiable, and it has a lot of nice properties. Then we fix the polynomial and we use it to generate targets to our one-step derivative prediction, and we optimize through Adam. We alternate this all the time, and we basically have a method now that works incredibly faster than backpropagation through time or the adjoint method. As you can see on the right, it's orders of magnitude faster, and it's also 1 order of magnitude more accurate at test time. Interestingly, we tried a couple of problems. In these problems, we have an obstacle avoidance type of scenario with 10 vehicles that try to avoid each other. And we noticed that if we change the gains of the obstacle avoidance control law that is used to generate the data, we can make the vehicles unstable. So all the vehicles try to avoid each other and it becomes like chaotic. Well, all other methods are not able to learn the vehicle dynamics in this chaotic scenario, but only our methods are basically doing exactly the same and are basically able to learn with the same accuracy, while the Euler and all the other methods failed. This is an interesting paper as well. I suggest you check it out. The fourth work is about model predictive control. So this was published again in iClear as well as the previous work, where recently some people looked at differentiable model predictive control. So if a model predictive controller can be solved, you can linearize the KKT conditions of this finite horizon optimization problem and backpropagate through them. So you can include that as a layer of a neural network, or you can, learn some parameters of the predictive controller cost function with gradient descent, right? Unfortunately, if you do that, there are no guarantees that the thing that you learn is stable or safe. So how do we fix that? We basically impose as its standard in MPC that the terminal cost is the solution of a simpler optimal control problem with infinite horizon. So the optimal control problem without constraints, and we focus on the linear case, so the LQR. So what we basically did is that we appended an LQR at the end of the horizon. We differentiate through the solution of the LQR in a closed form. So this was done for the first time in our paper for the discrete time version. So then we have a differentiable MPC, which has infinite horizon, and it also has stability guarantees. So you can, for a long enough horizon, you will basically get zero error from a demonstrator that is like an infinite horizon optimal controller, basically. So we tested this on a multi-vehicle problem where we basically wanted to learn the cost function of an MPC that controls the vehicles. And we noticed that if you have a prediction horizon of 20 already, you basically reach infinite horizon with our method. And the one that we used to generate the data had an horizon of 200. So these are the main 4 papers. I don't know how we're doing with time. There are 2 more works, but they are more to do with closed loop safe interaction.
Yeah, you can go ahead. We are having just a break right now, but you can just continue if you need to.
Yeah, if you want, I can continue a few more minutes. Yeah. I don't like running out of time. I suggest the guys to look at the presentation where you find many more details, and perhaps if you have any questions, you can also ping me.
Yeah, it's up to you. Yes,
yeah, I will just continue for a few more minutes to give you an overview of these 2 works, which are perhaps the most complete and the most interesting works, but they are still in progress. Of course, the first one was presented at the Safe Learning Workshop in NeurIPS 2019. The idea here is to safely continue to collect data, to update your existing model, and to continue to control the system. So it's similar to some work that was done before, but it was generally done with Gaussian processes. So very few people were doing this with neural networks. It's a little bit tricky. Now it's an emerging field. And so we looked at this in 2019, and we basically want to learn a certificate for stability given a neural network model. So we basically want to learn a Lyapunov function. This Lyapunov function, I won't explain you what it is because you probably heard about this before and we don't have time. Basically, this Lyapunov function is a certificate for convergence, at least to a local set. And any set of this Lyapunov function that satisfies the Lyapunov properties is an invariant set. So it's a safe set, right? So the idea is that we learn a particular type of neural network that can be a Lyapunov function. So it has some intrinsic properties. For instance, it's positive definite. We use a piecewise quadratic approach, and we will impose that in closed loop with our controller, this function needs to decrease over time. So we devised a special cost function to do this without examples. It just learns on itself. So you have a model, you have a controller, it generates its own labels with one-step transitions only, it learns the Lyapunov function. And this was done for the first time in this paper. Before it was done with very long sequences. It was done, the sequences were labeled as safe, but then you need to simulate for hundreds of steps. Instead, with our method, for the first time, it was done by just simulating one step. So we did that in this workshop paper. I'm sorry you cannot see the rendering of the figure at the top, but then we use the Bayesian RNN. The Bayesian RNN is able to quantify uncertainty on your model wherever you did not observe any data. It does it in a conservative way such that you can use robust control. Then in this paper, I approximated a min-max robust control and do another alternate learning to learn a Lyapunov function and update a linear controller. I tested this on a pendulum because I mainly focused on a linear policy to do that. And basically, we devised the method such that the more you collect data, the more the model updates from the previous one. This is not trivial for neural networks, so you need to do a few things that are indicated in the paper, such that the uncertainty that you see at the top decreases as you collect data up to a certain limit, and the size of the safe set that you see in the middle keeps increasing because the uncertainty decreases. Of course, this is still a little bit conservative, and it's all learned in batches. Then you can use this with MPC to do safe exploration. You can say, okay, stay within the blue set, but do as more random actions that you can, providing that you stay in the safe set at the next step, for example. Or you can use the uncertainty and the entropy maximization as we did in the paper. And we actually show that this exploration is safer and it's better than just doing a semi-random exploration and switching back to the stabilizing policy. Now, in this other paper, we do the same, but instead of training a policy, we just use an MPC. So we say, okay, I learn a Lyapunov function. I start from an initial controller, demonstrator, and then I learn a scaling factor, alpha, for this Lyapunov function into the formulation of an MPC. Now, if we have a theorem that says that if the scaling factor is large enough, then the MPC is stable, basically, given a perfect Lyapunov function and a perfect model. Then we relax that to an imperfect model with a bounded uncertainty, and we can show that there is a margin of robustness to uncertainty, and there is a local invariance property into our controller. Therefore, we will focus on a deterministic model. We don't do Bayesian neural networks anymore. In this, we just use an RNN, but we say, okay, we have a bound if the error is limited because we have a proof. All right, so this is the proof. You can look into it. Then we also have a proof on the suboptimality of this with respect to an optimal controller, where you actually learn the value function, and the value function is given perfectly. Well, in this case, we replace the value function with the Lyapunov function, which is not optimal, but it decreases all the time, which is what we want. So we developed a new algorithm in which we alternate the learning of the Lyapunov function, the learning of the MPC scaling. We just do a line search for the MPC. Of course, we have a surrogate model, but we learn this a priori. We don't learn this online. So it's like an offline reinforcement learning method. We tested this on inverted pendulum and on a vehicle kinematics. The inverted pendulum is very simple, but it was a good sanity check. So especially in the search for the scaling factor, you can see that the scaling factor cannot be taken as big as you want because it decreases the numerical accuracy of the MPC solver because the conditioning gets worse. So it's actually worth to use a cost function on the stability to optimize this as well. So what we basically do is that we have a cost function that measures the stability in a statistical way, and we use the cost function to learn the Lyapunov function, then to learn this alpha. So if the MPC crashes, it gets a very bad score and you keep the alpha that you had before, fundamentally. And we do this twice for the pendulum. We also count how many points verify and how many points do not verify stability in the whole state space. And this is the shape of the Lyapunov function. For the car, the shape of the Lyapunov function is a little bit nicer. It reminds me of one of those, you know, Japanese video game stuff. For the ones that are in their mid-30s will probably remember the shapes. But the nice thing is that our approach beats the demonstrator when you switch to an imperfect model. So let's say you have a long horizon MPC, an MPC with horizon 5, and you have a perfect model, then you can control everything, right? So this is the case of the one before the rightmost figure, where the Lyapunov function decreases all the time, and its derivative is also always negative, and everything is converging to the origin of the XY plane. Well, if you remove that and you use a neural network forward model with an horizon of 5, then a lot of trajectories do not converge anymore. This is figure B, MPC demonstrator using surrogate. With a surrogate, a lot of Lyapunov functions don't converge anymore and the vehicles don't reach, because in horizon 5, the uncertainty in the model is propagated so much that the MPC degrades. So what we did is that by learning the Lyapunov function, we can reduce the horizon up to 1. So then we don't propagate the uncertainty anymore. We have an MPC with horizon 1. So the Lyapunov MPC using surrogate is as good as the demonstrator, if not even better. So we basically reduced an infinite horizon problem to an horizon 1 problem, once again, with benefits on the propagation of uncertainty that it's reduced. And we can show that if you use horizon 1 without the Lyapunov function in figure A, the MPC just doesn't work. So ours is actually better than just doing the trivial thing. Okay, thanks. So this concludes my talk. I ran slightly out of time. Thank you very much for your attention. If there are any questions, I'm happy to take them here or offline.
Yeah, all right. Yeah, thank you very much. So if there are any questions for the speakers, so it's time.
Oops.
I don't see anything on the chat, so I'm not sure.
Okay, great.
Yeah, okay, yeah, so I think we'll just resume in about 20 minutes, yeah.
I saw something in the chat.
There's something? Okay.
Okay, there's a question for Nick.
Yeah, sure, yeah, go ahead. Is Nick here?
Yeah, hey, Matt.
Yeah, okay.
Hey, Nick. So I wanted to ask about the first figure that you showed where the neural network was trained to map a discretization to another discretization. And so the test error gets worse with improved resolution. Just wanted to clarify what that means. That means that the actual testing truth changes because the resolution of your truth changes. And so the prediction is the same at each of those resolution points. Was that right?
Well, I mean, the testing set doesn't change. It's just, so I mean, yes, like if you view the test set as vectors, then they change because their dimension increases, but they are representing functions. So the actual functions in the test set do not change as that figure moved from left to right across the horizontal axis. And so what was the second part of your question?
Well, I guess I was a bit confused if there was only one neural network that was trained in that initial example where you were.
Yeah, so maybe I didn't make that clear. So at each resolution, it was the network was retrained for each resolution.
Oh. So does that mean that it was really the architecture that was kind of deficient, that it was tuned for one resolution and not for others?
Yeah, essentially. The architecture was tuned. So if you retune everything, not if you retrained the network to get new weights and biases, but also retuned all of the other things like the hyperparameters or the design of, the expansion and the contraction in the network for the other resolution, then you would hope to get a consistent error, but that wasn't done for that figure. Yeah.
Got it. Cool. Thanks.
Yeah.
All right, then, so our next speaker is Krithika Manohar from Caltech, and she'll be talking about kernel methods for multi-scale problems. Yeah, thank you.
Thank you. So you can see my slide, yes?
Yes, yes.
And the previous one?
Yes.
Next one? Okay.
Yeah, that's working. Yeah, thank you.
Sorry, 1 second. Hello, everyone. First off, I would like to thank the organizers for arranging this remote venue and a fantastic set of talks today. I'll be presenting kernel analog forecasting for multi-scale problems. This is a data-driven method for forecasting based on partial observations of multi-scale dynamical systems. which is the target application we will consider. This work was done with my collaborators, Dmitry Burov, Dmitris Giannakis, who spoke earlier today, and Andrew Stewart at Caltech. And for more information, please see the preprint and video online on YouTube. So I'll begin with some of the challenges in data-driven prediction that I'm sure some of you are familiar with. In the settings, in general, the governing models are partially to completely unknown. The data tend to be partially observed from a larger underlying dynamical system. For example, the data in climate often comes from satellite measurements, and we do not have any knowledge of, in this example, subsurface temperature, currents, and atmospheric influences. And yet we would like to predict things such as the El Nino index, which is one of the target applications that my collaborators will consider. The idea is to try to predict this index, which measures the deviation from the mean temperature of this band of water and has been implicated in major global climate and weather events. Even if the challenges with this problem is that even if the data are fully observed, the governing model is nonlinear, chaotic, and can be multi-scale. And the snapshots of satellite measurements are only resolved weekly. So we kind of miss the dynamics that occur on microscopic timescales. So the goal is to find a data-driven methodology for prediction from partial observations with some sense of accuracy bounds on our prediction. And that is particularly important when you have partial observations of a system. So the methodology we will use is kernel analog forecasting, or KAF, which was developed by Dmitris Giannakis and collaborators. The idea is that given time-ordered pairs of observations and response data, where the observations are can be, for example, these satellite measurements, and we have time-shifted response data corresponding to the value which we'd like to predict, for instance, the El Nino index. KAF predicts the response forward by time tau from a given initial condition X. We assume that this lead time tau is an integer multiple of the sampling data sampling time interval of our system. And we assume that we have Q time steps forward values of the response data in the training. Now, the method looks like this, where we basically it reports the weighted sum of all the training response data, where this weighting kernel is constructed from these special features, which I will describe shortly. And a major benefit of using this methodology is that it has an operator theoretic interpretation in terms of the Koopman operator and the underlying dynamical system, some of which was mentioned in an earlier talk. And this result was proven by Alexander and Giannakis. The features of Fij that we will use are related to diffusion maps introduced by Koifman and Lafon, and they have this interpretation of geometric harmonics over the manifold from which the data is sampled. So they resolve increasingly finer spatial frequencies in a manifold. So first, quick background introduction on the Koopman operator. Given an ergodic flow in state space that can be, with a flow map that can be nonlinear, with an invariant measure mu, the Koopman operator u tau advances square integrable observables over this measure forward by time tau. And the way it acts on these observables is by composing them with the flow map, essentially advancing them forward in time. So here's the overall picture we are looking at. We have the state space omega in which the flow is nonlinear. We have these observables from which we collect responses, these Fs. And however, by mapping to this space of observables in L2, the action of the Koopman operator is linear, so we can exploit the tools of linear analysis. And secondly, we have this unknown observation map that is mapping into our partial observations. And we would like to construct a map from this observation space to U tau f, which gives us a notion of a perfect prediction. So in order to interpret this in terms of the Koopman operator, we can rewrite the KAF prediction in terms of a projection, or this expansion in terms of these basis functions, where the predictor is formed by projecting U tau f onto these data-driven basis functions. And we can evaluate this inner products to get the coefficients that depend on time by exploiting ergodicity and approximating U tau f in this integral by the time-shifted values of the response data. Now there's a consistency limit that was proved by, as I mentioned earlier, by Alexander and Giannakis, that under the limit of a large data and large number of features, this predictor provably converges to the conditional expectation of the perfect forecast conditioned on the observations. However, we don't need to know this observation map, only access to the data. Now these Phi-J's are eigenvectors of a kernel matrix populated by a variable bandwidth RBF kernel evaluated on the data points, where the standard squared exponential kernel is scaled by this scalar bandwidth parameter and this data dependent sampling density, estimate of the sampling density of the data that can be automatically tuned. Now, these Phi-J's have this interpretation, as mentioned in one of these earlier talks, as kernel PCA eigenvectors, or kernel principal components. These CJ's are simply the Phi-J's interpolated at the out of sample points, which gives us the ability to evaluate this predictor pointwise, also known as Nystrom extensions or RKHS basis functions. We can also predict the conditional variance, or which gives us an accuracy bound for our prediction by using a new observable once we've computed Z tau, and substituting instead of U tau f in this expansion, we can substitute U tau f minus the prediction at the training points squared to estimate, to predict essentially the conditional variance. This you get basically for free once you compute these Phi-J's. So the idea now is to predict these observations, predict X from given only X in multi-scale dynamical systems of this form, where epsilon is parameterizes the characteristic timescale separation between the X dynamics and the Y dynamics. And this V naught can be, for example, nonlinear. And as the timescale separation between X and Y becomes large, we get these limiting behaviors of the X dynamics from which gives us a standpoint to analyze the KAF predictions. As in the small epsilon limit, when the Y dynamics are decoupled from X and are ergodic, and given these values of these exponents of epsilon, the X dynamics converge to an SDE limit driven by Brownian motion. And this was proven by Stewart and collaborators. This is known as the homogenization regime. Alternatively, when epsilon goes to 0 and the Y dynamics are coupled to the X dynamics, and this term acts as an averaging term on the Y dynamics, we get a deterministic limit of the X dynamics, where the little x variables behave like this capital X dynamical system. However, this closure term, V of X, is unknown, and we would like to predict despite not knowing that. So this gives us a standpoint from which to analyze this forecasting method. Under homogenization, this conditional expectation actually should converge to the mean of this stochastic process, the limiting stochastic process. Under averaging, the expectation disappears because the system is deterministic, And we should actually be able to track the trajectory based on partial observations. Now we will assume for the next two examples that the data and the response are the X variables sampled at a macroscopic timescale. So the first example we will consider is that of homogenization, where this X is driven by these nonlinear dynamics and this fast Lorentz variable, where the Y dynamics are given by this fast Lorentz 63 system. And you can see that the X trajectory sampled at a macroscopic timescale essentially looks like a process driven by Brownian motion, because the Y dynamics are decorrelated by this term here. We know its limiting behavior from the previous slide is the stochastic process. And we can see that the empirical distribution of the X trajectory actually matches the invariant measure of the SDE process. Now the KAF prediction, which is shown by this blue line here and initialized at X0 is -1, is compared to the moments of the stochastic process computed via Monte Carlo. So the black line is the mean of the stochastic process and the red line approximate the variance. And you can see that even at long lead times, the KAF prediction is stable and provably converges to the moments of the stochastic process, which gives us a good confirmation of the methodology. Second, we're going to look at the features. The features phi j computed from the data-driven kernel eigendecomposition. And because this is a one-dimensional stochastic process, we can explicitly analytically compute these diffusion eigenfunctions, which are cosines of the CDF of this invariant measure. And you can see that the agreement is quite close. These are the 2nd through the 7th eigenfunctions. So which is a good confirmation that both of these, the behaviors of little x and capital X are quite similar, and we can analyze the prediction by comparing the two. Next, we're going to look at KAF prediction under averaging. Here we have a multi-scale Lorentz 96 with 9 slow variables xk, each coupled to 8 fast variables yj. Now we don't observe the yj, we only observe the 9xk. So in reality, we have an 81-dimensional state space, but we are only observing 9 variables. And here the closure given by this averaging term is of course unknown. We look at predicting x1 coordinate for 3 different parameter regimes under which the closure appears periodic, quasi-periodic, and chaotic. And these are phase portraits of the first 3 slow variables. So this is a comparison of what we can expect on under a deterministic closure. In the periodic case, the KAF prediction is perfect even for extremely long time. And you can see that the conditional variance is on the order of 10 to the negative 5, although you cannot see it here. And you can see that even in the quasi-periodic regime, KAF remains in phase with the periodic behavior. In the chaotic regime, you can observe a short-term prediction with consistent with the Lyapunov timescale of this dynamical system. However, under long time, the uncertainty starts growing, and for mixing systems, as tau goes to infinity, this converges to a constant, and this is predicted by the theory. So this is the expected behavior and confirms that the method is stable with respect to its limiting behavior. We can also compare this with GP Gaussian process regression learned closure of the closure term. So the GP trains on the pairs xk and the averages yk. So in reality, it has more information than what is available to KAF. And we simulate the closure model starting at the same initial condition as what we're trying to predict with KAF. So this is a model data-driven closure. And we can see that the GP closure struggles to stay in phase with the periodic behavior, whereas the KAF predictor perfectly overlaps the true trajectory, the ground truth forecast. They are comparable in the quasi-periodic regime. However, you can notice that the GP prediction grows out of phase, whereas KAF stays in phase. And in the chaotic regime, the GP in general is able to perform better in the short term, but really both of them share the short-term predictable behavior. And of course, we don't get an estimate of the uncertainty associated with this model data-driven closure, which we do get with KAF. So to summarize, KAF gives a data-driven forecasting framework for partially observed multi-scale systems, which is a forecast that is interpretable with respect to the underlying dynamical system in terms of the Koopman operator. One of the benefits of this method is that the eigendecomposition and deriving the features is only computed once. There is no inversion of this n by n kernel matrix, which would be very expensive. And we can predict the uncertainty or accuracy bounds and other observables such as indicator functions on the responses and other probable events essentially for free once we've computed this eigendecomposition. To apply this methodology to more complex examples in climate, we are currently looking at extending this to accommodate parametric dependencies and also to combine with filtering. So as more observations come in, we can correct the forecast in the long term. And this would be particularly useful in applications in climate and so on. So I'll conclude my talk here, and for more information, please see the archive preprint or the YouTube video. Thank you.
All right, thank you very much. Yeah, okay, so yeah, sorry, I had some issue with the, yeah, okay, so yeah, so today's talk is somehow like a short summary of a longer talk that I was planning to pre-record, but I didn't get a chance to pre-record yet. So it's yeah, it's joint work between the following authors. So the main motivation is to illustrate that machine learning and dynamical systems, I mean, they meet, mathematically speaking, in particular kind of spaces which are called reproducing Kernel spaces. So I think we heard a lot already about reproducing Kernel spaces. So so the context is that we want to combine between tools from dynamical system theory and machine learning in view of data-based qualitative theory of dynamical systems for analysis, prediction of nonlinear systems and control. And the approach is to construct reproducing Kernel space from measurements where the analysis become simpler. And the motivation is that working in RKHS allows to find a nonlinear version of algorithms that can be expressed in terms of inner products. So the outline of the longer talk is as follows. So there will be a little review of function approximation and probability measures in reproducing Kernel spaces. Then, yeah, talking about recent work with Houman Owhadi on kernel flows for learning chaotic dynamical systems, and this is what I'm going to talk about today. And the other parts are going to be covered in the longer part, which are detection of critical transitions for some slow, fast SDEs, approximation of nonlinear control systems in RKHS, estimation of the stationary solution of the Fokker-Planck equation of nonlinear SDEs, construction of Lyapunov functions in RKHS, approximation of central manifolds in RKHS, kernel-based approximation of the Koopman generator and the Schrödinger operator. So here, Stefan Kloos already uploaded the pre-recorded talk about this. And the last part would be about dimensionality reduction of complex metastable systems via kernel embeddings of transition manifolds. And I think that Christoph Schulte next week will talk a little bit about this in his talk. So as I mentioned with the summary of the approach, that we assume that there is a phi that takes from Rn into H that maps the ambient variable into Z, where H is an RKHS, so that we can perform an analysis in general, but not necessarily a linear analysis in H, then come back to Rn. The transformation phi is obtained from the measurements and the kernel that defines the RKHS. So in general, it has this following representation. And the measurements and data are used to construct the Hilbert space where computations become simpler. Yes, since we heard a lot about RKHS today, so I'm just going to go quickly about this. So they appeared in the 30s as an answer to a question: when is it possible to embed a metric space into a Hilbert space? And then under center conditions, this is possible, and this particular kind of Hilbert spaces are called RKHS. So they are essentially a Hilbert space with the reproducing kernel whose span is dense in H. And they are used in approximation theory, where the goal is that if we have random samples from an unknown function, by minimizing the following functional, which is the integral form, one could get an approximation. One could get a regression function that minimizes that functional. But in practice, one minimizes the following discretization of this error, which is the sum of fxi minus yi square over m, plus regularization term. And yeah, once we minimize that functional, one gets a linear combination of the phi-j's that are coming from the kernel, and this would be an approximation of the original function. And the c-j's are themselves solutions of a linear system of equations. And what we call learning is the process of approximating the unknown function f from random samples. And so we look in a little bit, we'll see how to choose the kernel through the method of kernel flows, and then we'll see how to generalize this approach to learning some prototypical chaotic dynamical systems. The other thing about RKHS is that they can be also applied to probability measures. I mean, as we saw in the previous talk by George Wynne and I think Alexander as well. So where there was a discussion about embedding probability metrics in probability measures in an RKHS, and then the MMD, which is the maximum mean discrepancy, which is the kernel mean embedding of P, and the MMD being the distance between two such mappings. So, so now we are going to go to consider the problem of approximating an unknown function from random samples, but from a different point of view, to the point of view of optimal recovery, where this problem can be turned into a well-posed problem by restricting candidates for you to belong to a Banach space. And then one would be interested in solving the following min-max problem, which is the minimum over V and maximum over U of this relative error, the norm of U minus V square, divided by the norm of U square, where U is the original function and B is the optimal recovery. So here we have this constraint that we would like to that V and U to be matching at the sample points. So this problem can be stated as a game between players 1 and 2, and can be represented as the following in the following diagram. And the optimal solution of this problem has an explicit form, which is given by the following formula. So the method of kernel flows is based on the premise that a kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. So this led to the introduction of this law, where, as I mentioned before, it's a relative error between V star, which is the optimal recovery of U star based on the full data set, and Vs is the optimal recovery of both U star and V star based on half of the data set. And then this So VS is admits the following representation that was described earlier. So how does it work? So the method itself works as follows. So given a family of kernels, I mean, it has two versions. I mean, the parametric version and non-parametric version. So the parametric version is where you have a kernel that is parameterized by a set of parameters, and then we want to update the parameters. So the kernel flow algorithm can then be described as follows. So we select a random subvector xb and yb of x and y, and then we select also random subvectors of xc and yc from the vectors that we got in step 1. And then we define the relative error as follows. So here it can be written explicitly using the samples and the subsamples. And then we perform gradient descent, the gradient descent of row, or update the parameters theta according to the following update. And then we repeat until we get convergence in the parameters. Yeah, so here, I mean, yeah, so there is a talk of my student who talks a little bit more about this, Mathieu Darcy, who gave this a nice introduction to kernel flows, and also you can look at Yifen Chen for theoretical results about kernel flows. So what we want to do now is to apply this method to learning chaotic dynamical systems. So we have a time series x1 to xk and in RD, and then our goal is to forecast xn plus 1 given observation x1 to xn. So we work under the assumption that this time series can be approximated by a solution of dynamical system of the form zk plus 1 is f dagger zk to zk minus tau dagger plus 1, and so f dagger is maybe n now, and then we would like to approximate f dagger from the observables. So here we're just going to apply the method that we saw before, but function approximation, and combine it with kernel flows in order to do an emulation of the dynamics of some prototypical chaotic dynamics. So so as mentioned before, I mean, here f of x is going to have the following form. So if it's not invertible, then we just get we're just going to add a regularization term in here. So we get kxx plus lambda I minus 1, and then so the emulation will be f hat will be kxx k plus lambda I minus 1 lambda y. So one of the things that we are going to use is that we are going to use the classical kernel flows in some sense, and so perform gradient descent based on the following of the following row. But we also introduced two variants of kernel flows that seem to be more adapted to dynamics. So the first one is especially chaotic dynamics. The first one is that since in chaotic dynamical systems, I mean, a good way to understand the long-term behavior is by looking at the Lyapunov exponents. So it makes sense to consider a variant of kernel flows based on Lyapunov exponents, where we would say that a kernel is good if the estimate of the Lyapunov exponent obtained from the kernel approximation of the dynamics does not change if half of the data is used. So we are going to perform gradient descent over rho L that is defined as the following one. So here these are can be different methods to estimate the Lyapunov exponents. And the other variant of kernel flows that we introduced in that work with Houman that we can find on the archive is the one that is associated to the maximum mean discrepancy, and the assumption that since we are having the same dynamical system, then they are coming from the same probability distribution that is defined by the Frobenius-Perron operator. And then here we are going to also perform gradient descent over the rho MMD. And then we are going to, so in the examples we had in this preprint is that we use this following kernel. And then we performed prediction using this kind of, on this example. So the first one is the Bernoulli map, which is a prototypical model for chaotic dynamics. So which is xk plus 1 is equal to 2xk mod 1. So we use this kernel. We perform kernel flows, and then we see that for the unlearned. So here we have the learned dynamics using the learned kernel, and then on the red one is with the unlearned kernel. So you see that the learned kernel improved the prediction of the dynamics. Yeah, on the right one, so here it was an irrational, so the left figure was the irrational initial condition, and the right figure is for rational initial condition. So here, blue is learned, red is true, and green is the initial kernel. So you could see that using the learned kernel, using kernel flows, helped with the prediction. And so that was the prediction in the case of time series. And then for the case of the Lorentz system, we applied the same kind of methods. So we see that the time series generated by the true dynamics and the approximation using the learned kernels versus the initial kernel in this figure. So the learned kernel also is having good predictive properties. And the other nice thing about this is that, these are the errors for the different metrics, so that you can also look at them in the preprint. So the other nice thing is that we are able also to reconstruct attractors, which are like good representatives of the long-term behavior of the dynamics. So it's not only about reconstructing or predicting the time series, but also being able to have a qualitative understanding of the dynamics through reconstructing the attractors. And then here we see that the attractors are well reconstructed in the case of a learned kernel, but in the case of the initial kernel, you see that there is a little gap between the true attractor and the reconstruction. So these are the projections, and this is the 3D representation. So yes, and then so you can look at more details in the following preprint, and these are just a list of other papers that are related to this to this presentation that I'm hoping to record at some point in the next few days. All right. Thank you. So I think next speaker is
myself.
Good. Thank you. Can you take over, please? Because I'm getting mixed up with the.
No, it's fine.
I'm having some technical problem. Yes, if you can take over, it would be nice.
Good. So just let me know, is this better? Or is this better?
Which one?
Okay, I'll keep the headphones.
Okay. All right.
All right. Let me share screen. All right. Can you see the PowerPoint?
Yes. Can you move to the next one, to the next slide? Because sometimes we don't see the other one.
That's not a bad idea.
Okay, good. It's working.
Okay. Let me take the laser pointer. All right. Should I start?
Yeah, please. Thank you.
All right. So thank you for for organizing this whole workshop. It's quite remarkable, really, the size, the scope, the lineup of people. So thanks for giving me this option. I'll talk today about a work that I've done with Ofir, who spoke earlier in the session, and also Gal Mishneh from UC San Diego and Ronen Talmon from the Technion. And if you don't remember anything from my talk, please just look at the archive. This is the most important slide, right? This is where the real stuff is. Okay. Before I tell you exactly what the problem that we solved and how we solved it and why I think it's interesting, I want to motivate it with an example that most of you would recognize from your own studies. So either in late high school, early undergraduate studies, you're given a pendulum, so a string, a bob, and a nail on the wall, and you are asked to use this apparatus to somehow measure the gravitational free acceleration, little g. And you don't know much, but what you do and what you can use is the fact that you know how the pendulum evolve in time. You have the ODE, the harmonic oscillator ODE. So you do the following. you observe the pendulum as it oscillates. Because it oscillates periodically, if you have a clock and an eye, basically, you can say, what is the frequency of oscillation? If you have a measuring tape, you can measure the length of the string, and from that, you can extract G. So that's an easy experiment. Okay. Now, suppose you want to go slightly further and say, well, maybe a double pendulum is even better than a single pendulum. Maybe it's an even easier setting. Then you would say, why not? Because I can measure the length of the strings. I can measure the weight of the weights. I have a model. Sure, it's a bit hairier, but I have an ODE, a system of ODE that I can solve. And then I can do the same spiel. I can observe the experiment. I can compare it to the model, and from that extract G. But the truth be told, and let's see if this will work without a pointer. Okay, I think the video for the Zoom is too much. The truth be told, the movement of the pendulum is quite a problem. So here is a video I took from YouTube of 2 double pendulums. And as you'll see, for example, it is very hard because they move very fast. It's very hard to extract the angles. There are reflections on the window, on the table, and there's no obvious way to compare the model to the chaotic trajectory because there is no simple omega, okay? There's no simple frequency. So while the scheme looks similar, something here is broken and we can't apply the same ideas that we did for a simple experiment. So what did we have here? We had certain parameters of a system that we don't know. So here I'm pretending as if I don't know all of them, or maybe I just don't know some of them. There is a known ODE. So even though I can't write down by hand the solutions, I can certainly run it on a computer. Had I known the parameters, I would have the coordinates, but generally speaking, I don't have the coordinates. But I don't observe the coordinates. Rather, I observe a movie frame. And the function by which the coordinates are pushed to the movie frame is unknown to me. So this will be the general problem that I want to introduce here today. So again, just to fix notation, there is some omega star in capital omegas, or a space of possible parameters, but there is one that is true to the system that I'm measuring. I know the model that pushes parameters to coordinates or to models, but I never observe the model. I only observe some high dimensional, nonlinear, unknown map of it, possibly noisy. So think of noise as a way to really encompass any kind of uncertainty that you might have about the model or about the observation. So even if the talk would have ended here, I would claim that, that something new has been said here and something new has been learned, because I think this is a new problem. So I want to emphasize some of the unique characteristics of this problem. First of all, there is a dynamic experiment, but there's only a single dynamical experiment, okay? So think about the double pendulum example. As long as we're on Earth, G is always the same number, right? And so we were doing a single experiment. It's a long one, but it's a single experiment. So a priori, it's not so clear that this is a learning problem. We can generate X for every parameter. So if you give me an hypothesis, I can create X of T and omega star, of omega, apologies. And so it is not precisely model discovery because we have the model. Okay. Does someone want to ask a question?
So we only need the moments up to the fact that they imply these 2 nice analytic properties. One is the hyperconductivity.
I think someone should.
Yeah. Sorry. So I think it's there's no time for questions. Yeah. Sorry about this.
Okay. Okay. Yeah. Fantastic. So this doesn't look like a.
Yeah. So can you just unmute yourself? Sorry.
Is it good now?
Yeah. It's good. Yeah. Sorry.
All right. So as I said, it's not obvious because we only have one experiment. It's not obvious that it's a learning problem. We don't discover the model. We only want to discover or learn or estimate the parameters. So it's a reduced version of model discovery, if you will. And we certainly use our knowledge of physics or knowledge of the observed phenomena. And the most tricky part here is that we don't know how we observe it. So you know that you observe a certain system, but you don't specify all that well that is the experiment design as a physicist would have it. So unlike standard inverse problem, when you have a full forward map, here we only have quote unquote half of the forward map. Okay. Good. So I'll tell you in the remaining time about the approach. I'll derive it very, very shortly. I'll show two algorithms that solve the problem, and I'll show results on the double pendulum and hint on results on the Lorentz system. And there is a longer video online. So here's the general strategy. The general strategy is we have a matrix of the data. That's the capital Y. So that's columns of every frame of the movie. For every hypothesis that we have, every omega parameter that we think might be the true parameter, we can generate by solving the ODE a model matrix. That's capital X of omega. And now we want to be able to give a score to how similar are those two matrices. How similar is the data to the hypothesis model. Now, easier said than done, because this is really an apples to oranges problem, right? They don't live in the same space, they don't look the same, and it's not at all obvious how do you compare X's and Y's. One thing that we won't do, and it's an asterisk here, but it's actually quite important, we won't try to reconstruct the observation function. It doesn't seem feasible since we only have one movie. Okay. So here's an idea. Whenever we have a hard problem, we replace it with a simpler problem, right? So suppose the problem was linear. So we don't know the observation function, but we know it's a matrix, A. Then, because it's still a finite number of parameters, at least in principle, we can employ a maximum likelihood approach. We're asking, given the data, what are the parameters and the transformations that would make the data most likely? And if you work out the details, so this yellow arrow is nothing but arithmetic, you finally get this nice expression with the Frobenius inner products and norms. Okay. Of course, this is an easy problem, and it's not our problem. So there's a derivation that one can do, and I'm skipping for the benefit of time, to say, okay, well, G is unknown, it's nonlinear, but at least we know that G exists. So in general, there exist two feature maps. So this is a kernel method session, so this shouldn't be a mystery to most of you. But there are two nonlinear general feature maps that make this problem linear dependent. So we can take what we did here and just plug in phi and psi, those two feature maps. If you've done it, then now you see, well, how can I move forward? I see, for example, that the terms in the denominator can be rephrased in terms of kernels, okay, of those gram matrices. And now we employ the kernel trick. We say we don't know the feature maps, but we do expect, if we have a nice kernel, an expressive kernel with all the properties that were mentioned in some of the previous talks of universality and expressivity and so on. And this will express our intuition and heuristic of how to compare X's between times and Y between times, same as in those kernels. Once you've chosen a kernel, say a Gaussian kernel, then at least the denominator now becomes something that you can compute with those kernels. And the numerator, which can be thought of as a trace of the cross covariance, can be approximated, not computed directly, but approximated by the trace of the cross covariance square, which then gives you, by the works of Graton and Sholkov, again, a kernel expression. So even if you've not followed every step of the derivation, and I've certainly done it shortly, we start with the maximum likelihood approach, and then by the kernel trick and a sequence of approximations, we get to something here in the green box that we can completely compute. So now there are no more mysteries, nothing here that we can't compute from the X matrix and the Y matrix, the data in the model. And this is the algorithm. This is the simplest algorithm that we could have thought of. We set a grid of points in the parameter space. for every of those points, we solve the ODE. Remember, every point is a parameter. The ODE is well specified. We can solve it, compute the kernel matrix, and compute the score. And what do we return? We return the score, which maximizes the score. We return the parameter that maximizes the score.
So first of all, an anecdote. Use a single run.
Sorry.
With certain parameters.
Yeah, so let me just mute everyone. I'm not sure there is another issue.
Sorry.
Yeah, you need to unmute yourself as well after all. Yeah, unmute. We don't hear you. Yeah.
Let me share it directly from the PowerPoint. Sorry for the confusion. Do you see the PowerPoint now?
Yeah, we see you. Yeah, we're also running out of time. Yeah, I mean, I just have
okay. So I'll just say one last thing. It works quite well. It works well for the double pendulum. We are able to retrieve the coordinates quite well, even when we try to estimate 3 parameters. We get very good statistics for the accuracy, and we can even improve the accuracy and the efficiency of the algorithm by replacing this exhaustive grid search with an optimization scheme. And the optimization scheme does, in fact, improve.
Yes, I made a mistake. Actually, you still have time. I thought that you
oh,
yeah.
I thought so too. Okay. Yeah. So let me just say something about the optimization. So the optimization, there's no mystery to it. Certainly you can run it, and what you actually do is that you run an optimization scheme. First of all, for every guess of omega, you start the algorithm and you let, say, interior point algorithm run and find the maximizer of the score, and then you run it for a number of initialization points. And it does, in fact, give you, so you see the next slide, right?
Yes.
Yes. So it does, in fact, give you an improvement in both accuracy. So you see a factor 2, factor 3 improvement, and that's quite characteristic of the thing that we ran, but also an order of magnitude improvement in the efficiency. But what I want to say is that a priori, there is no guarantee that this would work, because this is a non-convex optimization problem. And the reason, the nice way, and I think this is a nice way where it relates to dynamical systems, the reason it's not convex is even if you, by chance, had a convex parameterization of the ODE, you could make another parameterization of the ODE, which would yield another score, and that score would probably not be convex. So a priori, given the classical textbook formalization, say, of the double pendulum equations, you wouldn't have a convex score. So that's an interesting problem, how to convexify it for any ODE, but just an open problem. I will hint finally that we have results for the Lorentz system as well. That works quite well. For the benefit of time, I will not go into it today, but again, we run the same kind of procedure, that we have an unknown observation map, and we're able to estimate quite well the parameters sigma, rho, and beta. And if you want to see more, and you want to see detailed and how it compares to oracle predictions and naive linear algorithms and so on and so forth, I invite you to either watch the movie online or read the paper or ask questions now. So thank you.
Cool. All right. So thank you very much for having me. I'm going to tell you about machine learning optimizers about meta learning optimizers for training machine learning models, and how many of the challenges of training these optimizers have to do with instability in dynamical systems. This is work done by many people. So let me start out by first crediting my collaborators. I should especially call out Luke Betts, who did by far the lion's share of the work on this project, but also Niru, Jeremy, and Daniel. So in this talk, due to time restrictions, I'm going to give you only a quite high level perspective on the work. So if you're interested in more details, you should check out the paper cited on the bottom. Also, we're going to have a pretty cool paper that should show up in tomorrow's archive, which you can also check out. So the structure of the talk is going to be as follows. I'm going to go over some motivation for why we should care about learned optimizers. I'll tell you about one specific problem we face meta-training them, which is intimately related to nested dynamical systems, and I'll propose one solution to this problem. And finally, I'll show you some experimental results showing that we can train task-specific optimizers that outperform tuned hand design optimizers on that same task. So moving into motivation setup, one perspective on the deep learning revolution that started in maybe 2012 is that it was driven by a transition from using hand design features to using learned features, especially in image classification tasks. I think we can view meta learning in this same perspective. We currently use hand design loss functions and hand design parameter update rules, and mostly hand design architectures. And these are typically mismatched to the objective that we actually care about. So as an example, maybe even for supervised classification, what we would typically care about is something like 0-1 accuracy on a test set, but we instead train on cross entropy on a training set. So what we are doing is already mismatched both in data set and loss function to what we care about. Meta learning is concerned with learning rather than hand designing these objectives, update rules, architectures, and etc. I believe it's going to prove to be just as transformative in machine learning as learned features have been. So this is maybe motivation for why we should care about meta learning of anything, but especially of optimizers. So in this work, as I mentioned, we're going to focus on meta learning of learning rules. So optimizers are completely critical to the success of every part of deep learning, but essentially all optimizers used today are still completely designed by hand. These are things like Atom or RMS prop or SGD. These all share the property that they are relatively simple functions that operate on gradients and produce parameter updates. So instead of hand designing these functions, the learned optimizer community is interested in learning these functions. So we're interested in defining flexible parametric optimizers and then optimizing the parameters of those optimizers so that they perform well on some task distribution over problems to optimize. The challenge here, which is perhaps why meta-learned optimizers are not yet widely used, is that outer training of learned optimizers is notoriously just like exceptionally difficult. It's extremely compute intensive since every step of the outer optimization problem involves performing an inner optimization, involves optimizing an inner problem. The methods used to derive outer gradients are also often biased, though I'm not going to talk about that here. And perhaps most challenging of all, the outer loss landscape is typically chaotic and almost impossible to navigate. And we're going to talk about that last one in some depth. So first, let's set up the system. We're going to consider training a neural network with parameters W, which are initialized randomly. To train for a single iteration, we can compute the gradients of some loss and apply SGD to W. We can do this over and over and over again until finally we are done training. At the end of training, we can then measure performance to see how well we did. This measure of performance could be something like training loss, or it could be something like validation loss. Now, meta-learning optimizers involve replacing this hand-designed fixed form function of SGD with a generic update function U, parameterized by some weights theta. To outer train, we use our measure of performance to update the weights of our learned optimizer U. This process, we can then do it over and over and over again to obtain better parameters for our learned optimizer. This process of updating the learned algorithm weights we refer to as outer optimization or meta optimization, and we refer to applying this learning rule as inner training. So this system corresponds to two nested dynamical systems. There's an inner dynamical system that updates W as a function of theta, and an outer dynamical system that updates theta in a way that depends on the output of the inner dynamical system. In general, this outer optimization problem, as I've hinted, is quite difficult. It is expensive to compute a single function evaluation because you have to run an entire inner problem. The function evaluations are often very noisy. The loss surface is quite chaotic or complex for the outer problem since it involves the output of iteratively applying a nonlinear function. This is the problem, the challenge that we're going to focus on here. And as a result of all these barriers, the success of meta-learning based approaches has so far been quite limited. And the few successes we have seen have required a variety of extremely fragile tricks to make them work effectively. There are two classes of approaches that people currently use to perform this outer optimization. One of those classes is black box methods, which include things like random search or evolution or reinforcement learning. Random search is the approach that's most commonly used for estimating the hyperparameter, choosing the hyperparameters of existing high-end designed optimizers. Unfortunately, though, random search tends to scale extremely badly to high dimensional tasks. And for this reason, almost all work on learned optimizers uses gradients. So we can think about the inner training problem as just recursively applying our update function. And if our update function is itself differentiable, then this recursive application of our update function is also differentiable. And we are free to take derivatives of our measure of performance with respect to the entire inner optimization problem. So basically we can compute gradients by backpropagating through the entire inner dynamical system. Cool, so now that I've set up the systems we're going to discuss, let's dive into some examples of how these systems are extremely challenging to work with. The major problem is that the inner dynamical system is often chaotic, making it extremely challenging to optimize the outer hyperparameters. In fact, it is very common that the best performing hyperparameters for an optimization task are on the edge of chaos. So it's not just that the inner problem can be chaotic, it's that optimizing for the best performance on the inner problem typically involves pushing it to the edge of chaotic dynamics. To build intuition, let's consider a simple 1D loss surface with two minima optimized with SGD plus momentum. With low values of momentum, the iterate will converge to the first of the two minima. With larger values of momentum, the momentum will carry us over the central hump and we will converge to the second minimum. We can visualize the trajectories taken as a function of momentum in the pane and the figure to the right. On the x-axis here, we show inner iterations of gradient descent, and on the y-axis, we show the parameter value after running the inner problem for that number of steps, where the color of the line indicates the value of the momentum being used in optimization. So as discussed, for low values of momentum shown in yellow, the iterate converges to the first minimum. Higher values oscillate but then eventually converge to the second minimum. And even higher values of the momentum oscillate back and forth many times before eventually converging to one of the two minimum. Despite being such a simple system, the resulting trajectories are already quite complex. So I want to highlight here that the y-axis in this right figure corresponds to a particular loss value. The first minimum has a loss of 5. The second minimum has a loss of 0, and the hump between the two has a loss of around 11. Here in this new rightmost pane, we plot the loss achieved after some number of unrolled gradient descent steps, where the number of steps unrolled is indicated by the color. For low numbers of steps, the loss surface is relatively smooth. But for higher numbers, it becomes more and more discontinuous and would prove harder and harder to optimize via gradient descent. To gain intuition for why this is, consider the spike that occurs where the red arrow is in the rightmost plot. At this point, the iterate either has enough momentum to make it over the central hump, or it does not. And which side of the central hump it falls to results in two very different loss values. For a small number of steps, this is a smooth function. But as we increase this, the loss surface becomes more and more discontinuous until after 100 steps of optimization, you have a nearly step function, depending on whether you made it over the hump or not. So imagine doing gradient descent in terms of the momentum parameter on the purple curve in this plot, which corresponds to unrolling for 100 steps of GD. As you can see, it would be very, very difficult to optimize this outer loss corresponding to the final achieved performance of the model after training it for 100 steps via gradient descent method. So this was a toy 1D problem, but we find that neural networks are also sensitive to parameters of the optimizer. And just another very cool visualization, here we're looking at a PCA projection of the parameters of an MLP as that MLP is trained with an ADAM optimizer. The different colors here correspond to different learning rates of the ADAM optimizer. I want to emphasize that these learning rates differ only in their third significant digit. So they are very, very similar to each other. At initialization, all the models are initialized identically, so they're all at the same point. After one step, all the MLPs we're training with ADAM follow a very similar trajectory and a very similar parameters. After 10 iterations, we start to see that some of the models split off and diverge, going to different regions of their parameter space or different regions of the loss landscape. We can continue to take iterations, and we find that the longer we train, the more and more models split away. So this shows that extremely small, like third or fourth digit changes in the ADAM learning rate can lead to ADAM optimizing or producing very different parameters in the neural network being trained. So this here just shows different trajectories, but the ending position of each one of these trajectories will have a slightly different loss, resulting in an outer loss landscape that looks a lot like the one in the toy example. So the types of learned optimizer we care about are more complex than just optimizing a single learning rate. We can follow prior work and parameterize our optimizer as a neural network and look at a 2D slice. So this here is a 2D slice of the outer loss landscape as a function of the parameters of our neural network driven optimizer. And we're once again going to look at what this outer loss landscape looks like as we increase the number of steps for which we run the inner problem. And here, the color, this is a heat map, so the color here indicates the actual value of the outer loss within this 2D slice through the outer loss landscape. So for a small number of unroll steps, the loss surface is smooth, but as we increase the number of unroll steps, the resulting surface looks more and more structured and eventually chaotic. And so here we're going to go all the way up to 50 unroll steps. I want to highlight that this is the loss surface that we are going to want to optimize via gradient-based methods when we train our learned optimizer. It's full of local minima and poorly conditioned, leading to exploding gradients. I don't know how well this comes across in the video, but after 50 training steps, the outer loss value is discontinuous on the scale of individual pixels. So this would be like an exceptionally difficult loss landscape to navigate by gradient descent. Okay, so now that I've talked about one of the core problems you run into when meta-optimizing parametric optimizers, which is that the inner optimization trajectories are chaotic. Let's talk about how to solve it. Specifically, to get around this crazy loss surface, we're going to look to variational optimization. So the core idea here is to define a distribution over parameters and optimize performance over this distribution. This effectively smooths out the high frequency structure from the loss surface. More specifically, this new outer loss corresponds to convolving the original outer loss with a Gaussian distribution. It effectively blurs out the high frequency structure and near discontinuities that made the loss so difficult to optimize. So doing gradient descent on this smooth outer loss is somewhat involved. And in the interest of time, I'm not going to tell you how we do it. I'm just going to say you should check out the paper. But I will say that we are able to do unbiased gradient descent on this outer loss. And we are able to do a reasonably good job controlling the variance of the outer gradients as we do it. So again, this outer loss corresponds effectively to convolving this image with a Gaussian. It corresponds to convolving the outer loss with a Gaussian distribution, or smoothing it with a Gaussian in terms of the parameters of the outer loss landscape. So with this understanding of one of the major blockages to meta training of learned optimizers, and with this proposed solution, we want to now see if we can meta train some optimizers. So the first step in training a learned optimizer is to pick the parameterization of the optimizer. You want something that has good inductive biases and that is also very fast to compute, so that it's competitive in terms of wall time. We chose a tiny per parameter MLP that takes as input various features like gradient and momentum values, and which then outputs a parameter update. So basically, for every single parameter scalar in the network, there is a tiny little MLP that takes in the gradients with respect to that parameter scalar and outputs a delta W, which is the change in that parameter scalar. Finally, we need to decide what we're going to optimize our learned optimizer to do. We need to figure out some measure of the performance of our optimizer. Traditionally, optimizers are designed, at least, to minimize some training loss. But in reality, what people care about is generalization performance. So in this work, we're actually going to train two optimizers. We're going to train one optimizer, which is outer trained to perform well on the inner training loss. And we're going to train another optimizer, which is outer trained to perform well on the inner validation loss. So in that second case, the optimizer itself will still only have access to the gradients of the training data, but we are adjusting the parameters of the optimizer as we train it in order that applying it to gradients from the training data leads to better validation performance. This is actually, I think, something that's exceptionally cool in that via meta training, we can target a measure that we actually care about more than we care about the training loss. So we can, for instance, directly target generalization in our optimization of the learning algorithm. So to summarize, all that is left is to solve an optimization problem. We seek to optimize the weights of our optimizer theta. We do this via variational optimization, and we do this optimization over a distribution of tasks. In our case, it's a 10-way classification of tasks sampled from ImageNet. We then optimize an outer objective, which is either training loss or validation loss, and this loss is computed over inner training or applying our learned optimizer to the given task. I think I am now running out of time, so I'm just going to show this one last plot. So here we're plotting both training and test curves for a number of optimizers. We have learning rate tuned ADAM and RMS prop, as well as a extensively hyperparameter tuned ADAM parameterization with like learning rate decay and stuff. And on the left, we're looking at the inner training curves. In red, we can see that our learned optimizer, outer trained to do well in the train objective, optimizes the training objective extremely quickly, outperforming all the other optimizers. But looking at test loss, we find that our learned optimizer does extremely well on the training loss, actually does extremely poorly and diverges in terms of test loss. The degree to which this happens is interesting, but maybe not completely unexpected, since our goal in machine learning is not normally to achieve zero training loss. However, if we outer train our learned optimizer and validation loss, shown in orange, then we find we're able to achieve a lower minimum than the other hand design optimizers. And x-axis here is wall clock time, not training steps. So this is actually a learned optimizer that does better on a specific task, which is a 3-layer content, than its hand design counterparts. Cool. So in summary, training learned optimizers involves nested dynamical systems. Chaos and exploding gradients cause problems in meta training. Variational outer loss allows us to smooth the otherwise chaotic outer loss landscape and have more stable meta training. And we have a task-specific learned optimizer that can outperform on wall clock time and tester validation accuracy on the specific task that it's outer trained to do well on. And for more details, check out this paper. Thank you very much.
All right, thank you very much.
Yeah, thank you so much for the invitation to this very interesting symposium on machine learning and dynamical systems. So I'm a professor with KU Leuven ESAT, also affiliated with New Leuven.ai Institute. So it's a pleasure to give this plenary talk in the session on deep learning and kernel methods. So I will be talking about the unifying picture for deep learning and kernel machines. So one of the main things I would like to illustrate in this talk is that we can possibly get a unifying insight through duality principles. So I will start very simple with linear regression and gradually go there to function estimation in different kinds of spaces. And I will emphasize the least square support vector machines as core models in supervised and unsupervised learning. So recently also in the context of deep learning, generative models are very important, like with GANs, deep Boltzmann machines and others. So I also explain how through other and new duality principles we can also make an unexpected connection between such kernel methods and then generative models. So we can also extend the setting substantially. We can also go from there towards deep learning. And if time permits, I will briefly say something about dynamical systems. So we come a long way with neural networks. It came in 2 waves. So already in the 90s, there were all applications of self-driving cars. But at that time, the neural network architectures were still rather basic. Everything was based on the universal approximation theorem. If you have at least one hidden layer like here, you can have a universal approximator and make or establish or realize a map from a high-dimensional input space to a high-dimensional output space. But now in recent years, one is doing end-to-end learning with deep learning architectures containing several million of interconnection weights. So these architectures are very impressive, and in this way you can do joint feature learning with estimating the fully interconnected part at the end of the architecture. So here is a picture of the initial architecture of convolutional neural networks. So initially with 8 layers, 5 convolutional, 3 fully connected. But over the years, more complicated architectures have been introduced with many more layers, like recently in residual networks, even beyond 100 layers. And it's also exciting to see that you can also view this as discretizations of PDEs. So that's also not only from the architectural point of view, but also towards mathematical foundations, there is interesting progress at that side. So historically speaking, the neural networks and deep learning came in 2 waves. So in the first wave in the 90s, universal approximation theorem was very motivating. In the second wave, exciting new architectures have been introduced with CNN, D. Boltzmann machines, stacked autoencoders, GANs, and others. So in between, there was the introduction of SVMs, support vector machines, which stimulated a lot also the research on kernel-based methods in learning and kernel machines in general, because one could reformulate classification and regression problems as convex optimization problems. So the question is, what next? What is the next big thing? Maybe one way one could go towards the future is try to realize new synergies and have the best of both worlds. So combine the flexibility of neural networks and deep learning architectures with the solid foundations of SVM's kernel methods, learning theory, optimization, and in this way maybe come to a unified and more powerful framework with solid mathematical foundations for the future. So in an ERC Advanced grant project that we currently have in our research group called eDuality, which is about exploring duality principles for future data-driven modeling. We take this setting here that you see, this framework, as a kind of starting point, but we hope in the next years we can also go beyond that and maybe we can discover whole new things. But the current broadest picture that we currently have is that you conceive a particular model with different representations. Primal representation is typically parametric. It can be simple linear polynomial, or it can even be a neural net or a deep neural net, finite or infinite dictionaries. And then through different duality principles, you can have an alternative representation, a dual representation, which you can typically express in terms of kernel functions. So the simplest situation there is as a standard support vector machine, where you use then the kernel trick with a positive definite kernel. But you can also extend this to indefinite kernels, even non-symmetric kernels and tensor kernels. I will not be able to explain the full picture, but I will explain some of the elements in this picture. So let's start very simple with a linear regression problem. So just given input-output observations and we estimate W and B, you may consider a least squares, simple least squares estimator, but let's also consider a regularization term. And without a bias term B, this is a rich regression estimator. So you can just immediately estimate W and B, and you could say, yeah, what is there more to tell about this? So you would be amazed what more there is to say about this. So let's conceive this as a constraint optimization problem. Let's make it more difficult. So you have then as many constraints as the number of data points. And why should you make the problem more complicated? Well, in this way, you be able to create a new representation for the model. You can express your model in terms of the Lagrange multipliers, alpha I, which are related to the constraints. So these Lagrange multipliers and the bias term, it follows them from a square linear system. And you recognize here the linear kernel function. So we have, in fact, therefore, a model which has two representations, the original representation, but also another representation in terms of the Lagrange multipliers. So why can this be interesting? Suppose you have a data mining problem with 1 million data points in relatively low dimensions. Well, then it's more convenient to estimate it in the primal, because the kernel matrix would be 1 million by 1 million. It's not very smart to solve it in the dual. However, when you have high dimensional input data, a few data in high dimensions, like with microarray data sets, to give one example, it's much better to do it in the dual, because the size of your kernel matrix is completely independent of the dimension of your input space. So you see, depending on the type of application that you have, you may choose a representation which is most suitable for the problem that you want to solve. So you can tailor your representations towards your problem at hand. So that's for the linear case. So in support vector machines, it was shown that if you replace X by a feature map that you apply to X, and you do then the linear regression in a high dimensional feature space, well, you may apply then the so-called kernel trick when you go to the dual representation. And you can read this equation, in fact, in two ways. You can read it from the right to the left, where you would choose a feature map. You may choose it, for example, to be the hidden layer of a neural network, or multiple hidden layers of a deep architecture. Or you may choose here at the left-hand side a kernel function, like a Gaussian kernel, for example, and in that case, the feature map would be infinite dimensional. So here we assume in this notation that it's finite dimensional, but you can also formulate this in a Hilbert space and then use an inner product notation. You can also work with finite dimensional approximations to the feature map through Nystrom approximation or random Fourier features, and then also start from a kernel function, but estimate the model in the primal. So we have shown, in fact, that you can use this as a methodology in a wide range of problems in supervised and unsupervised learning. In standard support vector machines, you work with inequality constraints and hinge loss, epsilon insensitive loss. Here you work with equality constraints and L2 loss. So both for classification regression problems, but also kernel PCA, kernel spectral clustering, CC analysis problems, but also much beyond that, also towards recurrent networks, semi-supervised learning problems, even problems like in quantum measurement, we have been formulating within such a setting. So the dual problems in this case, they boil down to solving linear systems or eigenvalue problems or generalized eigenvalue problems. A drawback is that you lose typically sparsity then. So in this primal dual picture, you have different sparsity mechanisms. So either you want to have sparsity in the primal through L1 regularization, or in the dual through the choice of a loss function like the epsilon insensitive loss to get a sparse representation. You may also lose robustness, but in that case, you can actually apply weighting schemes. You can do reweightings and then also obtain robust representations. Often people wonder, yeah, what is the difference between neural networks and support vector machines? My favorite answer there is that SVMs are more neural nets than the original neural nets because they have two neural network representations, one in the primal and one in the dual. So the number of hidden units in the primal equals the dimension of the feature space, while in the dual it equals the number of support vectors. And in this picture, you can also integrate insights both from parametric and non-parametric statistics in one and the same picture. So here you see three common types of kernel functions that you can use, but there is a much wider range of kernel functions that you can use, of course. And this is probably the picture where many of you are familiar with function estimation and reproducing kernel Hilbert space. So for a convex loss, you can, through the representer theorem, you obtain this as the optimal solution. That's for reproducing kernels, positive definite kernels, but you can also go beyond it towards indefinite kernels. So then we have a function estimation in the reproducing kernel Kranz space instead of Hilbert space. And in this LSSVM picture, it's really very simple to do the same thing. You just split up your function into two parts with two feature maps, each related to a positive definite kernel, and you subtract the kernels from each other, and you subtract the regularization terms from each other. And it leads to the same linear system as before, also for problems of kernel PCA. You can also go to problems of function estimation in reproducing kernel Banach spaces together with Saverio Salso. We have been showing that if you want to approximate an L1 regularization here in the primal, then it's possible to obtain a dual representation that you can formulate in terms of tensor kernels. So instead of having a kernel that you evaluate on a pair of data points, so in this case, it's a kernel function that you evaluate at multiple data points, and it's still related to convex optimization. So let us come now to generative models, because this first introductory part is the more classical work, I would say. So currently in deep learning, a lot of nice things have been done with GANs, for example, generative models and other generative types of models than GAN. So a GAN model, it's very interesting because there you just start from random noise and you learn a generator in companion with a discriminator in a zero-sum game. And in this way you can generate and obtain, for example, realistic looking images. Here you see an example for generating handwritten digits in this way. Another type of model which is very interesting in that sense, which I will be further relating to kernel-based models, is a restricted Boltzmann machine. So here you have two layers of neurons. On bottom you have visible units, on top hidden units. And the visibles, yeah, there you observe the world, and the hidden units, it's a hidden representation that you want to create. So it's called restricted because the top layer is only connected to the bottom neurons. There are no hidden to hidden connections. So this model is characterized by an energy function. And in this energy function, the most important term you see here in red, where the interconnection matrix W is sandwiched between your visibles and your hidden units. And this looks very simple, but it has a very powerful interpretation. In fact, the whole power of it comes, in fact, from the fact that you can read it in two ways. So either the visibles are given, your observations are given, and then you may look for W and H, which is correlated to that. But you can also read this equation in the other direction. and assume that you generate, for example, a new feature H, and then you may want to look for observations which are maximally correlating to that. So that is intrinsically related to conditioning this joint probability distribution either on V or on H. So that makes it powerful, and you can also do this for deep architecture. So like with the deep Boltzmann machine, you have then a probability distribution, not only in the visibles, but in terms of several sets of hidden features organized in a hierarchical way over several layers. So this is reflected also in a very interesting structure here for the energy function. So for the RBM, you have a simple form of the energy function. In the D Boltzmann machine, you have multiple interconnection matrices. So you have given a V, for example, and then you look first for a first set of features, H1, which is correlated to it. And then you look for a second set of features that is correlated to the previous one, and so on. So that's interesting from a conceptual point of view. So with such models, here you see an example of the RBM. You can also generate then new images. They look a bit noisy. In fact, with the deep architecture, a deep Boltzmann machine, you can generate very high quality images, similar like this one, but it's computationally quite expensive. You can also combine it then with convolutional layers. And it's interesting to see then that the first layer is doing some primitive form of feature selection, while the deeper layer go to more abstract features. So the question is now, how could we possibly make a connection between the things that I've been talking about at the beginning, like LSSVM kernel PCA, and on the other hand, restricted Boltzmann machines. So we want to create something in the middle, which we call them restricted kernel machines. So it shares features of both RBM and LSSVM and kernel PCA. And just like we go then from RBM to deep architectures and generative models, it's also possible for RKM to go to deep architectures and generative models. So this was first introduced in a paper that I published in Neural Computation. It's open source available. And it comes with a new duality principle that is called conjugate feature duality, which enables to create new unexpected connections between certain kernel-based models and restricted Boltzmann machines. So I will only illustrate it for kernel PCA. So in kernel PCA, you start from a kernel matrix and you do an eigenvalue decomposition on it, and you can use it, for example, like in this toy problem for denoising applications or for dimensionality reduction. So what we have shown in the past is that you can also cast this in the LSSVM setting and show that kernel PCA is a dual problem to the formulation that you see. So you can see this as a variational principle from which you obtain kernel PCA as the solution. The nice thing is that this is model-based. So you can see this as a function estimation approach where you represent a function through a feature map. And the nice thing is that you can do out-of-sample extensions. So if you evaluate this on the training data, you have the eigenvalue decomposition problem of the kernel matrix, but you can also evaluate it here at new data. So you also on validation data or test data. You can also play around and later on with the loss function to create sparse or robust versions of component analysis. We have also done that in previous work. So what I will show now is that you can start from this formulation and also create a new representation, which is very similar to restricted Boltzmann machines. So we start from the same objective function now in matrix notation. The only thing we need here is an inequality. So what you see here holds for every vector E and H. So in the context of Fenchel duality, it's also related to the Fenchel-Young inequality for quadratic forms. but we only need, in fact, an inequality to create a new representation. So you use this to create an upper bound on the original objective, and then you look for the stationary points. And then you can express the original model in terms of the new variables h. So this h, they played a similar role as the hidden units in the restricted Boltzmann machine neural network interpretation. So the top layer of that neural network. So here I show it in full. You start from the LSSVM representation formulation of kernel PCA. In blue, you introduce the inequality. And then you see that again, here you have a sandwich interpretation. And the W matrix is sandwiched between your visible, so your observations, and the hidden features that you're looking for. The other things here are regularization mechanisms to keep things bounded. As you know, reproducing kernel Hilbert spaces, there you also have bounded function evaluation. So therefore you also need here regularization mechanisms. You don't have that in RBMs because there you assume beforehand what the distribution is of the data. Well, when you look here at the stationary points, well, you obtain then kernel PCA as the optimal solution. So in this way, in this new picture, we also have primal and dual representations. And in this way, we can also go then to deep RKMs. Here is one example of a deep restricted kernel machine architecture. In this example, we consider two levels of kernel PCA followed by an LSSVM classifier or regressor. So the deep objective consists then of the objective functions for each of those three levels. We have then three feature maps. So each of those feature maps may be multi-layered by themselves. And you can also apply then the kernel trick 3 times. So you have 3 kernel functions then for each of those 3 levels. So it's a truly deep kernel architecture in that sense because you have the kernel trick multiple times. So here you see the objective function. The part in red is the most important part because here you see the sandwich interpretation. So for the first kernel PCA, the second kernel PCA, and the other one. So I cannot go into the full details here. I emphasize here the primal dual interpretations. So here you see the primal dual representations for a deep architecture. So you may want to use this framework for training deep neural network architectures. Then you just choose the feature maps to be hidden layers of neural networks architectures, and you can directly train it in the primal. Or you may want to use the framework in the dual, and then you may want to use different kind of kernel functions. So you may also use kernel functions, for example, with different invariance properties. So I think this is also a nice challenge for the future of deep kernel machines to study what kind of invariance properties could be interesting and symmetry properties of deep architectures, possibly also in relation to physics. I consider this as one of the major open problems at this moment. So we have also shown that when you do the learning process, you have obtained something like the light blue curve here in comparison to the black curve. So the black curve is an objective that you only specify a classification performance at the last layer of your architecture. But you see here with this framework, you can have faster convergence and also much better conditioning and avoiding bad local minima solutions. So let us now go then to the generative RKM. So in an RBM, that's a probabilistic setting. So the bias rule is ruling the game there. So in RKM, we have rather an optimization setting. So in this case, we consider a super objective function, which we can use both for training and generating. So here you see that super objective. So depending on which of the variables that you fix here, you may either want to use this common objective function either for training or generating new data. So a really nice thing then of this setting is that, for example, in the context of kernel PCA, here you see an example on MNIST where you would select 2 components. What you see here at the left is what you classically have. You have some given data and you have a discrete set of points in your reduced space. But now we can explore this as a full continuum. You may go everywhere here in this reduced space and then go back to the original input space and see what kind of input is corresponding to what you have indicated here in the reduced space. So you obtain them, for example, mixtures here between your different digits. It's also possible to use this framework in companion with tensors instead of matrices. So the W that you see here is a tensor in a tensor-based model, the same framework, RKM, in its original representation. So then you can do early fusion for multi-view learning in the picture that you see here at the right-hand side. And the dual problem is then also a kernel PCA problem, an eigenvalue decomposition problem, but you can extract, in fact, higher order correlations through this tensor approach. So which is not possible in a classical picture here with matrix-based models with late fusion, looking for a shared representation through late fusion. So we can also use this GenRKM, generative RKM, in a multi-view setting. Here you see it for 2 data sources for which you have a joint representation here that you look for. So for generating, yeah, you just fit in, for example, a Gaussian or a mixture model on the hidden features, and from there you generate new hidden features, and then you can see in the input space for the several data spaces what is corresponding to it. So this is an architecture that already comes a bit closer to our brain. Also for our brain we have several data sources, or eyes, nose, ears. There is fusion in our brain with a shared feature representation, and when we are dreaming, yeah, you can also generate new images, new speech. So it's not exactly the same thing, but conceptually it's already one step closer to it. So we can also use this whole setting either kernel based or, for example, with explicit feature maps. We can train this with convolutional feature maps in its primal representation with stabilization mechanisms to keep everything bounded, and with additional reconstruction errors that we take into account. So such models are competitive currently with advanced methods in variational autoencoders, for example, and finding disentangled representations. So here you see some examples of GenRKM for generating new data. You can also at the same time generate images and texts. It's also very interesting towards explainability. Here you see an example where you change one component, and then, for example, only the hair color of the person is changing. When you change another component, for example, the gender is changing. So you can give an interpretation to every individual neuron thanks to this new duality principle and the neural network interpretation of the RKM model. And in this way, yeah, we also think towards the future, we can possibly develop deep kernel machines where you can really say for every neuron in every layer what it's exactly doing. So there is a role for every individual neuron. So I think this is also very challenging, because in AI, explainability for the moment is very high on the agenda. So here you see another example of that. Just by doing very simple linear interpolation in the latent space, you can have a very nice generation. Only the 4 corner points here are related to given data. It's reconstructions of given images, and all the rest that you see here in the picture is just obtained through linear interpolation in the feature, in the latent space, in the hidden feature space. And the same you see here illustrated on images. So we're also working towards large-scale algorithms and advanced algorithms of manifold optimization, optimization on a Stiefel manifold, and disentangled representation learning. So also here you can disentangle then everything, so it leads to better interpretation of the model. So at the beginning, I also mentioned how you can use weightings in connection to LSSVM in a simple way to achieve robust results. It's also possible to do that for the RKM. So I've shown this inequality to create a new representation. So when you introduce an additional diagonal matrix, you can also do a weighting here, and in the latent space, make sure that your distribution of your latent variables is closer to Gaussian. So in this way, you can also obtain robust versions for generation. So at the left, you see what's happening with the variational autoencoder. It's not able to cope with it, unless maybe you use more advanced versions to also work in a robust setting. But here with robust GenRKM, you can do that in a simple and straightforward way, also for robust denoising and generation. So here you see related papers. There is also software available at our website at ERC project eDuality. So future challenges, I mentioned some of them are related, for example, to deep clustering, understanding invariance of these properties of kernel functions and architecture symmetry properties. Also principles of optimal transport. So also Monch-Kantorovich duality is something very important. And we also been working on extensions of Gaussian kernels with what we call Wasserstein exponential kernels that you can also use in such a context related to principles of optimal transport. So that brings me to the last part of the presentation, because the main scope of the symposium is also dynamical systems. So I will briefly say a few words about this. So at this symposium, there are several talks on time series analysis, also in systems and control theory and areas like nonlinear system identification. This is very important, and also towards several real-life applications that you see here. So often, yeah, you take then a particular approach, either with white box, gray box, or black box modeling, and you parameterize different models architectures, either in an input-output setting or state space modeling approach, or a more structured model. It is in fact challenging to still do the same things for a primal dual framework, and because only the primal is parametric, then you still need to preserve then the primal dual interpretations. So it is possible for some architectures like nonlinear ARX models or Hammerstein or Wynne architectures and some others, but it's more challenging than for classical model structures like in the book of Lennart Ljung, for example, that you can parameterize in a straightforward way. So what we have been doing is also applying then, for example, Nyström approximations. So in some other talks, we have also seen that you can consider a kernel integral equation. If you take a finite sample approximation to it, you get kernel PCA. And the eigenvectors, yeah, you can directly use to get an approximation to the feature map, and you can use it within this framework for estimation in the primal. So this is then fixed size LSSVM. We have been using this technique successfully, for example, in electricity load forecasting and many other applications. So also state space models, modeling, one can be done in relation to it. So in one particular important approach there is especially for linear models, the so-called subspace algorithms, and there are also connections proven with Kalman filtering. So the approach there is that you start from input-output observations and you first make estimates for your state factors. And once you have these, then you are going to estimate a parameterized model. So you can also do this for nonlinear systems through kernel CCA. So I've shown here at the beginning already the LSSVM formulation for kernel CCA, canonical correlation analysis. So you have then two data sources. First data source relates to the past of your time series, and the other one to the future of the time series. So the state factor sequence is related to the intersection of the past and the future of your time series. And you can also use kernel CCA to first estimate and the state factor sequence, and then finally estimate a nonlinear model, the state space model. So of course also stability issues are often important. Everyone is aware that even simple first order models with a single state variable can already lead to very complicated behavior. Like for example, the logistic map. It's not because an equation looks simple that the stability analysis is simple. So therefore, often also stability considerations are also the qualitative type of behavior of the system is also very important. So in previous work in the 90s, I've also introduced the stability theory, the first stability theory for multi-layer deep recurrent neural networks, as many layers as you like. It's called NLQ theory. It has also been used in combination with backpropagation at that time to estimate stable models. So it's a bit forgotten for the moment, but maybe it's again the time to look back into that theory. So it comes also with global asymptotic stability criteria, input-output stability, extensions on nonlinear H-infinity control, robust control theory, mu theory, and many others. So one of the challenging things we have been doing in recent years in our group is also black box weather forecasting, and because over the years, techniques in machine learning have become so powerful that you can wonder at some point, can we also compete with physical models? So at the beginning we thought, yeah, maybe this is too challenging, but yeah, in the end it turned out to be very successful. We have been applying methods of multitask learning, multi-view learning, more advanced methods of feature selection, and also transductive schemes for optimal prediction. So here you see an example of multi-view learning for that framework. So suppose you want to make a prediction of the temperature in Brussels. Yeah, you may conceive here an LSSVM framework with multiple views. So the view index in that case is related to the different locations around Brussels that you take into account. So you have as many views then as the number of locations. So the red term that you see here is then a coupling that you realize between the different views, and the dual representation is just a square linear system that you solve. So you can also use this for a huge amount of cities, because the size here of your linear system is independent of the dimension of your input space. So we have been compatible with sometimes even better than predictions of weather underground, especially for the minimal temperature prediction. For the maximal temperature, it's a bit unclear why this is the case, but there it seems to be more difficult. So sometimes we are better, but sometimes also worse. So that brings me to the conclusions of the talk. So I tried to explain the role of duality principles, prime and dual model representations, to get some unified view on neural networks, deep learning, and kernel-based model approaches. I've also shown that you can even go towards generative models, and through duality principles you can realize new links, new connections between models which seem at first sight to be completely unrelated to each other, like kernel PCA and RBMs, for example, LSSVMs and neural networks. And also, yeah, it may lead to new insights on deep kernel machines, also promising towards explainability of models. And finally, I would like to thank many co-workers in our team and a lot of people for joint work, and especially the European Research Council for awarding 2 ERC advanced grants, and especially also for the last one, e-duality, which is about exploring duality for future data-driven modeling. So I hope, yeah, starting from this picture, we can also possibly obtain entirely new views or maybe entirely new models, and further explore new duality principles and set solid mathematical foundations that can be applied then in a generic way to a very wide range of different application fields. I thank you for your attention.
Yeah, thank you very much.
Do ideas have shape? What does have to do with deep learning? And how do we know that these are all dogs? Well, according to Plato, the world can be divided into 2 worlds: the visible and the intelligible. We grasp the visible world with our senses. The intelligible world we can only grasp with our mind. It is the world of abstractions or ideas. These ideas have an actual shape, which Plato called forms, and particular entities are simply shadows or imperfect projections of these forms. So according to Plato, we know that these are all dogs because there is an abstraction or ideal form called dog, and the particular dogs are imperfect projections of that form. What does that have to do with deep learning? Well, the main message of this talk is that artificial neural networks are essentially discretized solvers for a generalization of image registration variational problems. In this generalization, images are replaced by high-dimensional reproducing kernel Hilbert spaces, and while image registration seeks to align 2 images by matching material points via transformations of their coordinate systems, this generalization seeks to align RKHS spaces by matching data points. This identification allows us to initiate a theoretical understanding of deep learning from the perspective of shape analysis with images replaced by high-dimensional RKHS spaces, which Plato would have called forms. We will describe this theoretical framework by addressing the supervised learning problem of recovering an unknown function f dagger given f dagger of x equals y. We will assume that the input and output spaces are finite dimensional Hilbert spaces. We write x and y for the n-dimensional input-output vectors whose entries are the input-output data points, and we write f dagger of x for the n-dimensional vector whose entries are the images of the input data points under f dagger. The artificial neural network solution is to approximate the target function with the composition of nonlinear functions which we write f1, fd. To define these functions, write x1 for the input space x, xd plus 1 for the output space y, and sandwich the spaces x2, xk, xk plus 1, etc. between the input space x and the output space y. and let fk be the function mapping the space xk to the space xk plus 1. For artificial neural networks, fk is typically the composition of a nonlinear activation function, which we write a here, with an affine function, which we write wkx plus bk plus 1. This activation function is typically an element-wise nonlinearity, such as ReLU, CeLU, or the hyperbolic tangent. The affine function is represented by the linear operator wk, mapping xk to xk plus 1, and the vector bk plus 1 of xk plus 1. So wk and bk plus 1 represent the weights and biases of the kth layer of the network, and these weights and biases are typically identified by minimizing some empirical loss defined as some distance between f of x and y via stochastic gradient descent. In this talk, we will focus on the variants of ANNs, achieving the state-of-the-art in industrial applications. These are the residual neural networks, known as ResNets, introduced by her and others to facilitate the training of very deep networks. The ResNet solution to our original problem is to approximate the target function f dagger with the composition of d functions, which we write capital F1, capital Fd. Each capital Fk, which we will call a ResNet block, is the composition of the function fk, mapping the space xk to the space xk plus 1, with the composition of lk functions, mapping xk to xk. Each lowercase fk is, as before, the composition of an activation function with an affine function, and each one of these lk functions is the sum of the identity operator and a function vk mapping xk to xk, obtained as the composition of the activation function with an affine function. And, as before, the weights and biases of all these functions are identified by minimizing the following empirical loss, which is a quadratic loss on the mismatch between f of x and y. As observed by Haber and others, the following function, appearing in each ResNet block, can be interpreted as a discrete approximation of the solution of the following ordinary differential equation / dynamical system, defined by the activation function A and some time-dependent weights and biases to be identified as before by minimizing some empirical loss on the mismatch between f of x and y. This interpretation opens the possibility of using ODE integration techniques for designing the underlying ANN. Now, to describe the image registration interpretation of ANNs and ResNets, I will first give a reminder of kernel-based solutions to our original approximation problem. Since the output space of the target function is not the real line but a vector space, we will need to employ vector-valued or operator-valued kernels. So our next step will be a reminder of operator-valued kernels. Operator-valued kernels were introduced by Kadri and others as a generalization of vector-valued kernels introduced by Alvarez and others. To describe these operator-valued kernels, let x and y be separable Hilbert spaces, and let L of y be the set of bounded linear operators on y. We say that a function mapping x times x onto the set of bounded linear operators on y is an operator-valued kernel if k of x, x prime is self-adjoint with respect to the inner product on y for all x and x prime, and if the following positivity condition is satisfied for all xi in x and all yi in y. We say that this operator valid kernel is scalar if it can be written as the product of a scalar valued kernel little k and the identity operator on y. So this little k is a mapping from x times x onto the real line, and it is a scalar valued kernel. This operator valued kernel defines a reproducing kernel Hilbert space of continuous functions mapping the space x to the space y, defined as the closure of the span of the following functions, where the span is taken over all x and y in x times y, and the closure is defined with respect to the following RKHS norm, defined by the following reproducing identity. And we will use the following notations for the RKHS norm defined by the kernel K. Let F be a separable Hilbert space and psi be a function mapping the space X onto the space of bounded linear operators from the space Y to the space F. We say that F and psi are a feature space and a feature map for the kernel K if the following identity is satisfied for all x, x prime, and y, y prime, where this is the inner product in the space F. We summarize this identity by writing the following identity, where psi transpose is the function mapping the space X to the space of bounded linear operators from the space F to the space Y, and this psi transpose is defined by the following identity, where this is the inner product on the space F and this is the inner product on the space Y. Then we have the following theorem, which states that the RKHS space defined by the kernel K is the linear span of psi transpose alpha over alphas in the feature space F. And we also have the following Parseval-like identity, which states that the RKHS norm of psi transpose alpha is equal to the F norm of alpha. The ridge regression solution to our original problem is to approximate the target function with the minimizer f of the following variational problem, which admits the following representer formula. In that formula, k of capital X is the n by n block matrix with the following blocks. K of little x capital X is the 1 by n block vector with the following blocks, and this is a multiple of the identity matrix known as a nugget. Motivated by the structure of ResNets, let us now consider the variant of ridge regression in which we approximate the target function with the composition of a function f mapping the space x onto the space y, and a deformation of the input space mapping x to x, which can be written as the composition of L functions, each one of them being written as the sum of the identity operator, and a displacement mapping the space x to the space x. This function f and these displacements vs are then identified as minimizers of the following optimization problem, where these are the RKHS norms defined by the operator valued kernels k and gamma, where K allows us to regress functions mapping the space X to the space Y, and gamma allows us to regress functions mapping the space X to the space X. If we call this approach mechanical regression, then let us now show that ResNets are a particular case of mechanical regression with a carefully chosen kernel gamma and a carefully chosen kernel K. To see this, let gamma and K be scalar operator-valued kernels defined by the scalar kernel little k, having feature space the direct sum between X and the real line, and feature map var phi. Therefore, our scalar-valued kernel little k is of this form. In that case, we can see that F composed with phi L is of the following form, where this W tilde is a linear operator mapping the direct sum between the space X and the real line to the space Y, and this WS are linear operators mapping the direct sum between the space X and the real line to the space X. If this feature map var phi is of the following form, where 1 is the constant function 1, which we can interpret as an always active neuron, and A is an activation function mapping the space X to the space X, which can be an element-wise nonlinearity, then this regressor F composed with phi L has the structure of one ResNet block, and these parameters W tilde and WS are essentially the weights and biases of that ResNet block. To summarize, if the kernels gamma and K are of the following forms, where I of X is the identity operator on the space X, and I of Y is the identity operator on the space Y, and var phi is a feature map of the following form, where A is an activation function mapping the space X to itself, then F composed with phi L has the structure of one ResNet block, and mechanical regression is equivalent to regressing the data with one ResNet block with L2 regularization on the weights and biases of that block. Now let us return to our original mechanical regression solution, which is to approximate the target function with the composition of some function f mapping the input space X to the output space Y, with the formation of the input space represented using L displacements mapping the input space to itself. And F and these L displacements are identified as minimizers of the following optimization problem, in which the RKHS norm of F and the RKHS norm of these displacements are defined using arbitrary operator-valued kernels K and gamma. Now we have the following theorem. As L goes to infinity, so recall that L is the depth of the network or the number of displacements defining the deformation of the input space. So as L goes to infinity, the adherence values of the mechanical regressor F composed with phi L are F composed with phi V, where phi V is the solution of the dynamical system with vector field V, and this F and this vector field V are minimizers of the following optimization problem, which looks like an image registration / computational anatomy versional problem. The kind of question that you try to answer in image registration, which is a branch of computational anatomy, is how to best align an image I with an image I prime. And this is typically done by deforming the coordinate system of the first image to align it with the second image. This deformation is identified by minimizing the following variational problem, in which the first term is enforcing the smoothness of the vector field driving the deformation of the first image, and the second term is an L2 distance between the deformed first image and the second image. Now, there is a variant of image registration known as landmark matching, in which the L2 distance between the deformed first image and the second image is replaced by an L2 distance between material or landmark points on the first image displaced by the deformation and material points or landmark points on the second image. The variational problem that we have obtained as a limit of mechanical regression looks like an image registration variational problem with landmark matching, with a few differences. The support of the images I and I prime is no longer the unit square, but it is the input space X for the image I and the output space Y for the image I prime. And those images are replaced by abstractions. The landmark or material points Xi and Yi are no longer points in the unit square, but they are data points living in the input space X for the input data points Xi and the output space Y for the output data points Yi. We are no longer deforming the unit square or an underlying image mapping the unit square to the real line, but the input space, which could be high dimensional, and an underlying implicit image mapping the input space X to the output space Y, which could both be high dimensional, and is typically an element of an underlying RKHS space. So therefore, we are implicitly deforming an underlying RKHS space. Let us call ID registration this generalization of image registration in which we deform the input space with phi and then map that deformation to the output space with the function f. Let us call ID registration block the composition of the function f with that deformation phi. Then we can evidently compose these ID registration blocks by mapping the input space to a sequence of spaces layered between the input and output spaces. So in this figure, we first map the input space x to the space x2 with the function f1. The space x2 is deformed with the flow phi2 and mapped to a space x3 with the function f2, which is itself deformed, etc., until we reach the output space y. If we call ID formation this composition of ID registration blocks, then we can show that INNs and ResNets are essentially discretized solvers for ID formation problems, and CNNs are discretized solvers for ID formation problems with a particular choice of kernels for gamma and k, which we call REM kernels. These results are obtained from the fact that ID registration is the limit of mechanical regression, and one resident block is a particular case of mechanical regression. We will now focus the presentation on ID registration, i.e. the following optimization problem, its minimizers, and the corresponding regressor of the target function. The Bayesian interpretation of this regressor is that it is a map estimator for the following stochastic process given the following information, where Xi is a centered Gaussian process with covariance function k. Phi is the solution of the following dynamical system in which the vector field is a centered Gaussian process defined by the following norm. This centered Gaussian process is independent from Xi, and Z is a centered Gaussian vector independent from zeta and Xi with ID N0 identity entries, and this is the identity operator on the space Y. Now, if this kernel gamma has feature map psi and feature space f, so this psi is a function mapping the input space x to the space of bounded linear operators mapping the space y to the feature space f, then this center GP defined by the following norm has the following representation, where the EI form an orthonormal basis of f, and this BI of t are IID one-dimensional Brownian motions. Therefore, their derivatives are IID white noise. Let us call deep residual Gaussian process the solution of the corresponding dynamical system with vector field zeta. Then this deep residual Gaussian process is essentially a continuous variant of the deep Gaussian processes introduced by Damiano and Lorentz, and it is closely related to the Brownian motion in the diffeomorphism group introduced by Baxendale and to the stochastic flows covered by Kunita. Now, ID registration is essentially ridge regression with a word kernel learned from data. And this can be seen by observing that the following two regressors are equal. The first one is the ID registration regressor, obtained as the composition of F with Phi. The second one is a ridge regression regressor, obtained with a kernel KV that is equal to the composition of the kernel K appearing in ID registration with the flow map of the vector field V minimizing this ID registration variational problem. Another perspective on what we have learned so far is that ID registration is Gaussian process regression with a prior learned from data. This identification provides a mechanism for the extreme lack of robustness of ANNs with respect to data poisoning or adversarial noise. This mechanism is that of the extreme lack of robustness of Bayesian inference with respect to perturbations in the prior. Another cause of the extreme lack of robustness of ANNs is the fact that the flow map Phi is driven by a chaotic dynamical system, which is something that we will cover later on. I also refer to the recent work by Hansen and others on why instability is inherent to deep learning. So, an important question is, can we fix this lack of robustness? The answer is not without giving up some accuracy, because robustness and accuracy are conflicting requirements. So how do we fix it? Well, the image registration strategy, which we generalize to ID registration, is to simply add a nugget that is a multiple of the identity matrix to the kernels gamma and k. This regularization strategy is also the one that is commonly employed in geostatistics to regularize kriging. Adding this nugget does not change the functional form of the regressor, but it does change how F and V are identified at training time. The impact of these nuggets is to modify the ID registration variational problem so that the propagation of the training data does not follow exactly the dynamical system with vector field V. This is done for the kernel gamma by adding the trajectory of the input data set to the ID registration variational problem and penalizing the difference between Q dot and V of Q. Similarly, a nugget is added to the kernel K by introducing the variable Y prime and penalizing the difference between F of Q1 and Y prime. The same strategy can be employed for the regularization of mechanical regression and therefore for the regularization of ANNs. In the setting of the training of one ResNet block, this regularization strategy does not change the functional form of the ResNet block at training time, but it changes how weights and biases are identified at training time by introducing penalized errors on how the input data propagates through the layers of the network. And this regularization strategy leads to a network that is provably robust in the sense that the regressor is continuous in all variables, those variables being the training data and the input data. Therefore, this strategy provides a principled and rigorous alternative to dropout that is the natural extension of how kriging and Gaussian process regression are regularized in spatial statistics. We will now characterize the minimizers of mechanical regression and ID registration variational problems. Starting with mechanical regression, we have the following theorem. The minimizer V of the following mechanical regression variational problem admits the following representation formula. In that formula, QS is a trajectory in data space formed by the transformation of the input training data as it propagates through the layers of the network. Gamma of QS is the n times n block matrix with the following blocks. Gamma dot of Qx is the 1 times n block matrix with the following blocks. Q1 is equal to the input training data x, and the trajectory formed by the states Q1, Q2, QL plus 1 is a minimizer of the following discrete list action principle. Once we have identified a discrete list action principle, we can apply classical results from discrete mechanics. First, introducing the following momentum variables PS, we obtain that the trajectory of QSPS follows the following discrete Hamiltonian dynamic. This implies that F and the VS are uniquely determined by the initial momentum of this discrete Hamiltonian system. In particular, the weights and biases of L2 regularized ANNs are uniquely determined by the initial momentum of this discrete dynamical system. Therefore, as in image registration, one could use geodesic shooting to train the weights and biases of an artificial neural network. Furthermore, as a corollary, the near energy preservation of the minimizer of the discrete least action principle implies that the norms of the minimizers Vs or the norms of the weights and biases of one ResNet block after training with L2 regularization fluctuate by at most 1/L across the layers of the network, where L is the number of layers in that network. We have similar results in the continuous time setting. First, a minimizer V of the following ID registration problems admits the following representation formula, where Q is a trajectory in input data space Xn, starting from the value X and minimizing the following least action principle. Therefore, if we introduce the following momentum variables, then V is proportional to that momentum, and the position and momentum pair QP follows the flow of the following Hamiltonian. This implies that V and F are uniquely determined by the initial value of that momentum P0, and the RKHS norm of V is constant over the time interval 0, 1. If psi is a feature map for the operator valued kernel gamma, and if we rescale the momentum variables by the number of data points, then the previous Hamiltonian dynamical system is equivalent to the following one, in which alpha is a trajectory in feature space that is amenable to mean field limit analysis. Note that the representation of a minimizer V of the ID registration variational problem separates into a product of a function depending only on X and a function depending only on time. The function depending only on X is the transpose of the feature map, and the function depending only on time is this function alpha of t, defining a trajectory in feature space. And we have the following theorem characterizing the hydrodynamic limit of the empirical distribution defined by position and momentum variables. These results are different from the ensemble analysis of gradient descent of May, Rotzko, and Van den Eyden in the sense that we are not characterizing how weights and biases evolve when minimizing an empirical risk via gradient descent, but what the minimizers of that empirical risk are when we add L2 regularization in the weights and biases. To finish, the following list of references is relevant to this presentation, which is based on the following publication. And to conclude, let's go back to our original question: do IDs have shape? Well, the etymology of the word ID is mental image or picture, because it can be traced back to Plato's view that IDs have a form or a shape. In that sense, it is quite intriguing that ANNs can be interpreted as image registration algorithms trying to align high-dimensional shapes, which we could call forms.
Yeah, it works well. Yeah, thank you. Any questions? Or? Yeah, okay. Yeah, I see Ard Louis here. Yeah, thank you for coming. So maybe you can start now if you want.
Should I start now? Great.
Yes. Yeah.
I will do that. Let me just start my presentation. So thank you very much for the invitation. It's a great pleasure for me to speak to you today. Let me just get to the beginning of my talk. Just a second. There we go. I'll do this again. So I'll start the timer now. So it's I want to talk to you about a problem which I've been thinking about for a number of years now, which is why do neural networks generalize in the overparameterized regime? And this is a very big picture talk. I'm going to cover a lot of different fine-grained topics. And this question can be sharpened a little bit in the following set of arguments. So what is the conundrum I'm trying to explain? So we know that modern neural networks, the ones that work so well, are typically over-parameterized. In that over-parameterized regime, we also have a number of different theorems that tell us that these are extremely highly expressive. We also know that, say, in a typical supervised learning system, that an exponentially large number of functions can fit a typical data set. And the vast majority of those functions will not generalize well. Since DNNs are highly expressive, they can, in principle, express all those functions. So in order to generalize well, DNNs must have a very strong inductive bias to a tiny subset of the functions, which are those that generalize well. And the question that I really want to look at today is, what is this inductive bias like and what causes it? It has to be there. The question simply is, what does it look like and what causes it? And I'll give you the answer away. The answer I'm going to tell you today is that this inductive bias arises because neural networks are intrinsically biased towards functions with low Kernel growth complexity. And this inductive bias is good because most of the data that we look at is structured and therefore actually has relatively low Kernel growth complexity. What causes this bias? I'm going to argue that it's not, for example, the type of optimizer you use, SGD or other optimizers. Rather, it's an intrinsic bias in the parameter to function map that causes the bias. And this, I will argue, is true for a vast majority of the neural networks used in the literature today. Let me give you another example of this question, another way of formulating it. Why do neural networks not overfit? Let's say I give you a classic kind of textbook problem. I give you a number of data points. I ask you to fit a polynomial to it with a simple regression. Well, if you fit a low order polynomial, you will have some bias, but not too much variance. You fit a higher order polynomial, you'll fit all data points exactly. It's 20 order polynomial will do that, but you have huge variance in your results. You won't generalize well, you won't predict well in between. That's just something you normally expect. You have more parameters than your data points, you should overfit. Now, what you're seeing here as well in the same picture is a number of small fully connected networks with a few thousand parameters that I've used to fit this data. You see, they all give you very smooth functions. Because neural networks are highly expressive, they should also be able to produce every single one of these functions, including this polynomial that I showed you. And so the question, another way of formulating, is why does a neural network pick these relatively smooth functions? Why did it not pick this function, which it also can express? What is the bias, or what regularizes it? I'm going to start with a model problem that I think is very useful because it's simple. It's a bit like the Ising model in physics. So let's say I want to learn a Boolean function. So here's an example of a Boolean function. It's a doctor's decision table to send you to hospital or not for COVID-19. So if you go to the hospital, if you come to the doctor, you've got fever, cough, loss of sense of smell, you're old, and you have a number of comorbidities, then you're going to go to the hospital. If on the hand you're younger, but you have comorbidities, you might go to the hospital as well. On the other hand, if you have a number of symptoms, you're young and have no comorbidities, the doctor may simply say, go home, mate. I'm sorry, there's not enough room in the ICU. And so the question would be, if I look at a problem like this, can I give a number of examples of a doctor's response to send you to the hospital or not? And can an artificial intelligence system like a neural network learn from this and then generalize on unseen answers? Well, the nice thing about this Boolean problem is I can count very easily the number of possible answers. So for these 7 questions, there are 2 to the 728 possible answers, but there are 2 to the 128 different functions that this thing could learn. So there's a very large number, on the order of 10 to the 38 different functions that even the simple system could represent. So what's amazing is that in a typical situation, I can give you a small number of these possible answers, and a neural network will generally do a pretty good job of predicting the rest of the answers. That's hugely surprising because the number of functions that it could use is hyper-astronomically large. So I'm going to study a particular property of a neural network. Here's a classic kind of food for thought neural network. And I'm going to define a map, which we define in this paper as well, which is a map from the parameters to the functions. So in this case of the Boolean system, it's easy to see what these functions are. In the case of the functions are a bit more complex, but a neural network is always effectively a function approximator. So my map is defined, as you see in this definition below. It's basically mapped as the set of parameters, set of weights that I have to the outputs given the set of all possible inputs. That defines the function. And the parameter function map is not from inputs to outputs, but from parameters to outputs. And the reason that's interesting is because I can ask questions such as, what happens if I randomly pick weights in my neural network? What functions will it pick? Will it pick this function I just showed you, or will it pick a different function? What function has a high probability of appearing upon random sampling? And so with my very brilliant student Guillermo, I reworked on this, and what we found is something that might be surprising at first sight. So here I show you the probability of getting a particular function ranked for the first, oops, just a second, for the first 10 to the 8 possible functions. And so what you see here is that you get a number of functions here, very high probability, and it drops down quite rapidly with rank. What's perhaps even more interesting is I can organize these functions by their complexity. In this case, I used a compression measure to measure how complex a function is. And I see that the functions that are highly likely to appear on random sampling of parameters are the simple ones. In fact, the most likely function to appear is the simplest function of all, which is send everybody to the hospital or send nobody to the hospital, all zeros or all ones. And as you go down, these functions become more and more likely. And you might ask yourself, how surprising is this? Well, given that there are 10 to the 38 possible functions, on average, the probability of getting a particular function is extremely low. It's 10 to the minus, slightly less than 10 to the minus 38. So the fact that I'm getting functions with probabilities of 10 to the minus 2, 10 to the minus 3 is highly surprising. And the fact that I can tell you in advance which functions they are, that they are the simple functions, might also a priori seem very surprising. And so this is a kind of what we call simplicity bias, that these systems have an extremely strong bias towards a teeny fraction of the whole space of functions. These 10 to the 8 functions found here are only 1 in 10 to the 30th of all the possible functions the system can express. And here I've got a bound here that I'm going to derive for you in just a minute, which gives you actually a bound on the probability of getting a function, which is bounded by 2 to the minus a times the measure of the Kolmogorov complexity of the function. So why does this help with generalization? Well, it helps generalization in the following sense. If I do, say, a typical supervised learning system, so I pick a target function, so I take a particular set of answers to the question of whether I send you to the hospital or not, that can have different complexities. So these are simple functions at low complexity and complex functions with high complexity. And then I train my neural network on half of the functions, half of the inputs, pardon me. And then I look at how well it produces, it predicts the function of the other half of the inputs. I see that as I make my target more complex, my neural network generalizes less and less well. What's interesting is if I compare my neural network to, say, a random learner, that's a learner that picks a function that exactly gives 0 training error on the training sets, but is not constrained at all on the test sets, then I find that on average, the random learner basically makes a 50% error, which is exactly random. And the reason for that is that, say that I've got half of my inputs fixed. On the other half, I still have 2 to the number of inputs of my test set possible functions. That's an extremely large number of functions, the vast majority of which do not generalize well. So this neural network is extremely strongly biased towards a tiny subset of functions, which are the simple functions. You can see that here as well. I run this system many different times from different starting points. And what you see is that the neural network typically finds low generalization, low complexity functions. This is the target, this blue line here. Whereas the random learner just finds random functions because most functions are random. Whereas if I give the neural network a complex thing to learn, it typically only finds complex function, doesn't generalize very well. So neural networks, I'm claiming, have an inbuilt Occam's razor that works well on structured data. Why is this, you may ask? Why is this? And I'll tell you why in just a minute. I'll just tell you that we can also do some analytic calculations. We can prove a number of different theorems about this. We can't quite prove this bias law that I'll derive for you in just a minute. We can prove some subsidiary calculations that we've done in this paper here if you're interested in some more mathematical proofs. All of them basically show you that these systems are highly biased towards simple functions. So why the simplicity bias? What's the general argument for it, and why did I expect to find it? Well, it really comes from an intuition which goes as follows. This is the monkey intuition. So if a monkey types on a typewriter, for example, how likely is it the monkey to type an output like pi? Well, if there's n keys on a typewriter, there's a 1 over n chance of getting a particular number correct. So it's 1 over n to the n plus 1, because the number has to get 3.14. And the probability is equally likely for any other string of that length. If, however, the monkey is typing into a program like C, for example, then there is this very short program that generates pi, the one that I show you right here. And if he randomly picks this by typing, which has 133 characters, so 1 over n to the 133 is the probability, then pi will appear. And what the intuition tells you is that in a system that's running on an algorithm of some kind or the other, the probability of getting a particular output is much higher for those outputs that have short description, that short codes. And this whole kind of monkey intuition has been formalized in the field of algorithmic information theory in the concept of Kolmogorov-Chaitin complexity. So basically the argument that Kolmogorov and Chaitin and others made is that the fundamental complexity of a string like this is much lower than a string like that, which has no pattern. This string has a pattern, print 0, 1, 50 times. This string has, as far as I know, no pattern, except in the shortest code is print itself. And this gives us a number of new intuitions, like a random number is a number whose Kolmogorov complexity is equal to itself or larger, and the complexity of a set can be less than the individual units of the set. For the simple reason, if I say to you, give me all numbers from 1 to Googleplex, then that is a short description, simple description, but there may be individual numbers that are very complex. And so we use this argument to make the following derivation with my very brilliant student of mine, Kamal Dingle. And we basically, what you do is you have a map from inputs to outputs, so from parameters to functions, for example, but it could be any kind of map. You can therefore find all possible outputs by simply counting over all possible inputs as a short Kolmogorov description. You can then encode those outputs by how frequently they appear. The most efficient way to do that is a Shannon-Fano alias code. And this gives a way of describing any outputs. And so this is a bound on the Kolmogorov complexity. And with a few more stipulations, the most important, which is the map is simple, the map doesn't grow quickly with the size of this complexity, doesn't grow quickly with the size of the system, we can derive this effective bound. This is the probability of getting an output for an input-output map has lower bounded by 2 to the minus a times, this is some k squiggles, an approximation of the Kolmogorov complexity, and some offset which picks up to these very famous order 1 terms. So does this work? Well, we tried this for a wide range of different maps. Here's the RNA sequence structure map. It predicts pretty accurately what are going to be simple structures come up very frequently, complex structures more rarely. Here I look at L systems, very famous system for computer graphics, or comes originally from botany to look at trees, tree shapes, plant shapes. And again, by randomly looking at these codes, what you find is that simple things are much more likely to appear than complex things. So the intuition is, when you've got an algorithmic process, which is effectively what's happening when you have a neural network, you've got parameters that are then turned into functions, then you should expect upon random sampling to be heavily exponentially biased towards simple outputs. We see this for more complicated neural networks. It's obviously much harder to do direct sampling, but we use Gaussian processes here, for example, on a CNN on C410, and you see it's the same, that highly likely functions have low complexity. This is CSR is a type of complexity measure, critical sample ratio, and complex functions with low probability. So the argument, therefore, so far is that, well, neural networks have this intrinsic bias towards low complexity solutions, which is good because we think that most data is effectively low Kolmogorov complexity compared to the maximum complexity you can have. Now, the difficulty you may raise is that this is not how we train our neural networks. We don't randomly sample parameters. Rather, we use something like stochastic gradient descent, which follows gradients on some very extremely complicated loss function. And this is the language that a lot of people have used to try to understand why neural networks generalize well. And I have a kind of different intuition that comes from our experience with evolutionary theory, which is that when you've got a system with a very strong bias, so some basins are much larger than other basins, then even if you have a loss function on top of that, the basin of attraction, as it were, the set of parameters that will give you this particular function, function 1 as opposed to function 2, function 3, If that function has a large basin itself, so many parameters mapping to it, its Bayesian attraction is also going to be large, and so you're much more likely to fall into it. And therefore, the argument would be we expect stochastic gradient descent to follow roughly this the same ordering of functions. And we tested this explicitly. So here we did the following calculations. On the y-axis, you have the probability of getting a particular function upon random sampling, and on the x-axis, you have the SGD probability of getting the function upon many random samplings of SGD. This is for MNIST with a binarized MNIST, a training set of 10,000, a test of just 100 images, so you can get the same function more than once. And for example, this function here is a particular function which gets one image wrong, and you see that it's the most likely both on random sampling parameters and on SGD. So SGD is basically finding the same functions as you would expect from random sampling of parameters. In this plot, we show the probability of getting a particular function on your training sets, given that you've, on your test set, pardon me, given that you've trained on your training sets for a wide range of errors. We look at all possible, or we sample over all of the 2 to the 100 different possible test functions you could get. And what you see is that this tiny little fraction of high probability functions, so what SGD finds are also the functions that are very likely to appear. So SGD basically follows the same bias as the as what we see in the parameter function map. And here you can see that as the error gets is smaller, the probability is higher and the complexity is lower. So all these things correlate with each other as expected. Now, the simplicity bias is a very crude thing. It just tells you there's going to be bias towards simplicity, but there can be differences. And here's an example of the kind of differences you might see. We call these second order effects. So here's a normal vanilla CNN. This is the lowest error function that you find, in this case, on a fashion MNIST data set. And what you see is both in the random sampling and the SGD, this function is relatively low. If I add max pooling to it, then both in the random sampling and SGD, the probability has gone up significantly. And this is a classic second order effect. You expect max pooling to work better on image data sets, and in fact it does, and the generalization error goes down. But the question here is the second order effect. The first order effect is that the vast majority of functions don't generalize well at all, and already the neural network has been biased towards this tiny subset of functions, this set right here in this little red box, which are the high probability, low error functions, and that is why neural networks generalize so well. And then finally, we've done a separate set of arguments where we use Pac-Bayes bounds. So Pac-Bayes is a set of ideas from David McAllister, which we've adapted a little bit to look at neural networks. And they work with this, they basically work with this probability, this probability of getting a function conditioned on a training set. So this posterior probability, or it actually works on slightly different marginal probability. And so what we're able to do is exactly calculate this for a whole series of neural networks. So here's, for example, a 4-layer convolution neural network, and on different data sets, so from MNIST all the way up to CFAR. And what we do is we do label corruption in the images. So we're basically corrupting the data. So the generalization error obviously gets worse. And what we see here on the bottom, these dashed lines are what SGD gives us generalization error, and the top line is what our bound does. We can similarly use this bound to look at, and I should point out that our bound is also very tight. So it's within a factor of 2 or 3 of the real generalization error. We can do the same here for different data complexities and different sizes of our training sets, so different learning curves. We get the same kind of trends that we see in SGD. And so the conclusion really is that there's an AIT coding theorem that predicts simplicity bias for neural networks. This intrinsic Occam's razor means they will generalize well on structured data, and this parameter function map is so strongly biased that it overcomes any further biases from SGD to first order. Second order, there are other effects, but the bias explains the generalization conundrum. And then finally, we've used the Pac-Bayes picture that gives you very tight bounds. And with that, I've come to the end of my 20 minutes, and I thank you very much for your attention.
Yeah, yeah. Did you see the chat? I mean,
yes, I see. Okay, Belka W. Yeah, no. Yes, okay, thank you. So the Delta W. So we've actually derived the double U curve using Gaussian processes in a different thing, but what I'm talking about is fundamentally not about the dynamics, but we've seen the double U curve, and we think we understand it. We're looking at the over-parameterized regime only. So that's just where you're basically at the far end of the double descent curve. And yeah, so I'm not so surprised by this double descent curve, right? So if you have fewer parameters in the data points, then you get a classic optimum for the for not having too many data points, not too many parameters, not having too few parameters, the classic bias variance trade-off. But then once you enter this over-parameterized regime where you can generate a very large number of possible functions, then it's a completely different story. So the classic bias variance trade-off story doesn't quite hold, and what you're seeing is essentially low generalization. So what you see in these double descent curves is just a restatement of the conundrum. What you see is in the over-parameterized regime, you generalize well. It's just a different way of saying exactly the same thing and saying, oh, by the way, in the under-parameterized regime, we have our usual bias variance trade-off, but we knew all that already. There's nothing new.
Okay, thanks.
Yeah, all right, thank you. Any other questions?
Yeah.
Yeah, okay, so now we can, yeah, sorry, we can move to Florian and Yifen. Yeah, sorry for the delay.
Okay,
yeah,
thank you very much.
Yeah, thank you again, thanks.
No worries. Hello. Let me share my screen. All right, I hope you can all hear me. Yeah, so it's my great pleasure to talk today about, yeah, it's my great pleasure today to talk to you about Cholesky factorization by KL minimization, which is joint work with Matthias Katzfuß and Houman Owhadi. And in a nutshell, what the goal of this work is to find sparse Cholesky factors of dense covariance matrices by minimizing the KL divergence between the target covariance matrix and the approximate covariance matrix implied by the sparse factor. And surprisingly, this problem has a closed form solution that can be computed embarrassingly parallel. And in the special case of Green's matrices of elliptic PDE, we in fact obtain the best known complexity for the inversion of these matrices in the literature. Finally, this algorithm is also fast in practice, and this allows us to invert like 1,000,000 times 1,000,000 covariance matrices arising in spatial statistics in just 10 seconds on a single core. So let me first describe the setting in which we are deriving our rigorous results. So we assume that we're given a domain omega and RD, so something like that, with a boundary that doesn't do anything crazy, an elliptic partial differential operator L of sufficiently high order. So for instance, in 2 dimensions, it could be something like a bilaplacian with some lower order terms. And then we remind ourselves that the Green's function is the inverse of this differential operator in the sense of convolution. So convolution with the Green's function inverts the differential operator. And here I've plotted this function g of x comma y for one particular x, the x in here, and for different y. And we see that it achieves its maximum when x equal to y, and then as y moves away from x to the boundary, it slowly decays. Now we assume that we are given a bunch of points in this domain, these points xi, such that are roughly uniformly distributed, in the sense that the ratio between the biggest sphere that doesn't contain any points and the smallest distance between a point and its nearest neighbor, or a point and the boundary, is uniformly bounded by this 1 over delta. And all asymptotic complexities and error estimates in this work will depend on this parameter delta. And then we plug in pairs of these points into the Green's matrix theta, into the Green's function to obtain the Green's matrix theta. Now, these Green's matrices theta are actually quite ubiquitous in applied mathematics. So the first place where they come up is in computational physics, where simply the physical laws governing the systems might be an elliptic partial differential equation, and therefore G, the Green's function, is the solution operator of these equations. So it basically describes the behavior of the physical object you would encounter in the real world. And then this Green's matrix can be thought of as a discretized version of the solution operator. Another application is in Gaussian process statistics, where we want to model an unknown or partially observed data as a realization of a Gaussian process. And so we want to choose a covariance matrix in order to encode prior assumption of how we believe the data to behave. And one very natural such prior assumption is a smoothness prior, whereby we say that we assume that nearby data points are strongly positively correlated, and as the points are moving away from each other, the correlation becomes weaker. And you see this when we draw samples from this Gaussian process. We see, again, the nearby points will have roughly similar values, whereas a more distant point will have more widely varying values. And in a very similar vein, these matrices also appear as kernels and kernel methods in machine learning to implicitly use a infinite dimensional feature transform. So in these applications, we're typically interested in computing matrix vector products, in solving systems of linear equations in these matrices, computing the log determinants, or in sampling from the associated Gaussian process. And the problem here is that these matrices are typically dense. And this, again, you can see from the fact that this Green's function only decays slowly as we're moving towards the boundary. So most of the entries of this Green's matrix will be non-negligible. And therefore, using naive dense linear algebra or Cholesky factorization, we end up with a quadratic or cubic complexity in N. And this is a major showstopper for many applications of these methods. And so it's basically, it has become its whole industry to try to come up with methods that more cleverly exploit the particular structure of this N to come up with cheap approximations. And that's roughly the game we're playing in this work. Okay, so we're proposing the following procedure. So we say that we first find a way to reorder the rows and columns of theta. We then select the sparsity pattern of only near linearly many entries of the matrix. And then we compute the Cholesky, the lower triangular factor L that minimize the scale divergence between the target covariance matrix theta and the sort of Gaussian process that is implied by using this L as an inverse, as a Cholesky factor of the inverse of theta, so a Cholesky factor of the precision. And we claim that in doing this, we can compute absolute approximate Cholesky factors in near linear complexity, with the complexity only scaling logarithmically in the target accuracy. And as far as we're aware, this is the best known computational complexity for inverting Green's matrices of elliptic PDE. Now, this method also has a number of practical advantages. First, it is fast in practice. As I said, you can invert million times a million matrices in 10 seconds on a single core in spatial statistics problems. The columns of L can be computed embarrassingly parallel. It is the optimality in K divergence makes sure the approximation is always positive definite, so we don't encounter zero pivots, so to speak. And finally, we can extend this approximation to sums of independent processes, which solves a major problem in spatial statistics, where we oftentimes want to treat an independent noise process. Finally, we only need X to pairwise distance of the Xi. So in particular, we can automatically exploit low dimensional structure in this in the data set. Now, so what does this algorithm look like? So let us first look at the this sparsity pattern and ordering. So the ordering that we're going to use is the maximum ordering, whereby we keep selecting the point that is furthest away from the points that we've already selected. And in particular, we're using the reverse maximum ordering, meaning that we are assigning the first point in this maximum ordering to the last row and column of the matrix and then move our way backwards. And our sparsity pattern will be such that we let each point, which is marked here in red, interact with the points in orange. So these are the points that are within a factor rho times the distance to this nearby, to the closest point that is already selected. And now we want to compute our Cholesky factor, and so we want to solve this KL minimization. And this is something that at first maybe looks a little unappealing, because this is a nonlinear program, and it seems maybe it doesn't seem obvious that this is actually can be compared with other fast linear algebra methods. However, and somewhat surprisingly, this problem has a closed form solution that I've given you here, where basically each column of this L can be computed independently by solving this problem, where this index set Sk basically corresponds to all the non-zero entries of the sparsity pattern of a given column, of the kth column. And so this update rule is not new. This has been discovered in 3 different communities independently. In spatial statistics, that's using this update rule is known as the vacuum approximation, however not known to come with any optimality properties. In factorized sparse approximate inverse, this typically applied to sparse as opposed to dense matrices and has been shown to be optimal in Capron condition number or satisfy this constraint optimality property. And finally, in the work on nonlinear transport maps, there have been people have been using nonlinear extension of this to sample from non-Gaussian processes. Now, the problem is that still the time complexity scales as n times rho to the 3D, where rho measures the size of these nearest neighbor interactions. And this is simply because this matrix here, this sk times sk matrix, so sk will have size of the order rho. So inverting this matrix using dense Cholesky factorization is scales as rho to the, will have size of order rho to the d. And so inverting this matrix will have complexity rho to the 3D. And we have to do this n times because we have to compute n columns of L. The solution to this is to observe that many of the sparsity patterns of different columns of the sparsity pattern actually are almost subsets of each other. And so what we can do is we can try to add just a little bit of additional entries to make them exactly subsets of each other. And then what we can do is we can just compute the Cholesky factor of the largest of these sparsity sets, or the largest of these columns. So for the theta sk of this column here, and then we can simply use submatrices of this bigger Cholesky factor as the Cholesky factors that we use to inverting the theta SKs for the other columns. So we compute only one Cholesky factor and use it to update multiple columns. And in the special case of the sort of geometric ordering and sparsity pattern that I described earlier, the way this works is that we pick a number of points that are sort of close to each other, and we simply declare this a supernode that consists of a number of parents. So columns that we want to update, these are depicted in orange, and we simply add all of the sort of non-zero entries that were part of at least one of these columns to the sparsity pattern. And observing that now each of these supernodes has of the order of rho to the d many members, so we only have n over rho to the d many supernodes, we can shave off another factor of rho to the d and obtain the computational complexity n times rho to the 2d. Now, so far it is maybe not clear why these matrices have these sparse Cholesky factors to begin with. And to understand this, it's important to remind ourselves of what is called the screening effect in spatial statistics, which simply means that if we have a smooth Gaussian process and we start conditioning it on sum of points, that conditionally the conditional correlations will start decaying very rapidly, simply because nearby points will give us much more information about this point than for more distant point. And one can quite easily convince oneself that basically the non-zero entries of this Cholesky factor L correspond to the zero entries of the Cholesky factor L correspond to conditionally independent of the Gaussian process. And that is what inspires this choice of ordering and sparsity pattern. And this can also be rigorously proven in the setting of Green's matrices of elliptic PDE. So now there, just to conclude with a few numerical examples. So one thing that, one other innovation of this paper is that we're able to deal with sums of Gaussian processes. For instance, here we have a theta, so some smooth Gaussian process, and we add an IID noise variable given by this identity. Now, typically adding IID noise will diminish the screening effect and therefore deteriorate this approximation, which is a big problem in spatial statistics. However, what we can do is we can factorize the matrix like such that we add the identity instead to the inverse of theta. Now, the inverse of theta is a partial differential operator, and so adding an identity simply corresponds to adding a zero-order term to a partial differential operator. So individually, both this matrix and this matrix will be covered by our theory, and this allows us to rigorously deal with this added noise variables. And here you see some examples that show that while naively applying this our technique to the noisy Gaussian process will greatly increase the divergence distance, with using this sort of two times factorization, we are able to accurately approximate the process throughout a wide range of possible noise values. We also have some numeric examples, more like spatial statistics flavored setting, where we have a million points in the plane, and we're trying to predict the values on these regions in orange, on these scalar points in red. And we see that already for relatively small values rho, we obtain very accurate results. And we can also see that, in fact, using this aggregation scheme that I described a few slides earlier, we can greatly decrease the time complexity for the same value of rho, even though it results in us having many more non-zero entries in this Cholesky factor, which then improves the accuracy. We also have some numerical examples in a boundary element method setting where we basically, when we're rephrasing using the single layer boundary element techniques as computing conditional distributions of a Gaussian process. And again, we see that even for relatively minor values of rho, we can very accurately sort of recapture the ground truth at a fraction of the required matrix entries. So in summary, the Kubrick light law minimization, supernodes, and screening effect improve the state-of-the-art conversion of dense kernel matrices. The resulting algorithm is embarrassingly parallel with minimal communication. And by combining it with the incomplete Cholesky factorization, so doing this double factorization, we are able to efficiently treat additive noise, which is, again, has been a big issue in spatial statistics. Thank you very much.
Yeah, thanks a lot. Yeah, our next speaker is Yifen. Yeah, thank you.
Hello, everyone. Can everybody see my screen?
Yes.
I'm Yifen. I'm the third-year graduate student at Caltech. First, I want to thank the organizer for setting up this meeting and for providing me the chance to present here. The title of my talk is Consistency of Hierarchical Parameter Learning, Empirical Bayes and Kernel Flow Approaches. And this is joint work with Andrew Stewart and Houman Owhadi at Caltech. And you can see the archive number on the top right of the slide. So to begin with, I will first show one page's overview of this talk. We are in the context of supervised learning, or in statistics language, we are doing non-parametric regression. To solve this problem, the approach we are considering is Gaussian process regression, or kernel methods. In this method, the question we're focusing on is how to select kernels based on data, because there will be many hierarchical parameters to this kernel. The algorithm we use to select the kernel are twofold. The first one is probabilistic approach, and the Bayesian approach. We especially focus on the empirical Bayes algorithm. Also, we consider another approximation theoretic algorithm, which is called kernel flow, proposed by Professor Houman Owhadi. The contribution of this work is theoretically we have some analysis for the consistency for some Boumediene class model in the large data limits, and this is what we will focus on in this talk. And we also have many experiments. You can look at the experiments in our paper or look at the longer video and longer pre-recorded video in the website. So to start, I will first give a reminder of Gaussian process regression. We are doing supervised learning or non-parametric regression or interpolation. So that is we want to recover a function udaiger from its pointwise value, which is yi equals udaiger xi, I from 1 to n. Here, to keep it simple, we assume a lowest-free scenario. To solve this problem, we have a very popular GPR solution or kernel methods. And we first give some notations here. The kernel k theta is a function defined from d times d to r. The theta is a hierarchical parameter to be inferred. We use a green capital X to denote the collection of all data points x1 to xn. Then udaiger x means udaiger applied component-wisely to elements in x. That means this one will be a vector of dimension n. Similarly, k theta xx will be a matrix of dimension n times n. In the same way, k theta dot x will be a collection of functions with entry k theta dot xi. And finally, the GPR solution, or the solution of kernel method, is given as u dot theta x. It has the following form. It can be interpreted as a conditional expectation of some Gaussian process. And it depends on three important things: the kernel k and the parameter theta in this kernel, the data set x, and the ground truth udaiger. And here we didn't have Lois, so we don't have the yi. We just have udaiger, the ground truth. So this is Gaussian process regression. And we know that in this Lois-free scenario, a very good property of the Gaussian process regression is that for any kernel, we will have an interpolated solution on X. That means our solution, U dot theta X, will agree with U dagger on the training data points. So that means the 0 training nodes in machine learning language. But in practice, people care more about the out of sample error or the so-called generalization error. So that requires us to pick some good data. This turns the problem of learning to be a model selection problem. We want to learn a hierarchical parameters data from data. And this is the background, and the following will be a roadmap of this talk. First, we present two approaches to solve this model selection problem, the Bayes approach and the approximation theoretic approach. Then we will compare their performance and especially their consistency as the number of data goes to infinity. We have some rigorous theory for the Martin class model on the torus. Let's start with the first part, the Bayes solution. Because we are doing the model selection on theta, and the Bayes philosophy is to put everything in a probabilistic way. So we put a prior on theta, and we assume U dagger is a Gaussian process drawn from this kernel family. Then under this probabilistic model, we can calculate the posterior. And if we adopt the empirical Bayes perspective and we use uninformative prior, then this procedure will produce a point estimator, the EB estimator given as the minimizer of the EB loss function. It has the following form. And it is a negative log likelihood of some Gaussian measure with covariance k theta xx. Essentially, it's doing maximum likelihood estimate under the probabilistic model. This is the Bayes solution. And in the Bayes solution, we assume theta U dagger to have a prior distribution. This assumption is very strong, and sometimes it will be brittle to model meet specification. And alternatively, we can also attack this problem from a different perspective, and this perspective is more straightforward. Suppose we set up a target cost, D, and we want our solution, our GPR solution, to be close to the ground truth in this cost. So in that sense, an ideal approach is to optimize theta of this loss function. But U dagger is not available, so our idea is to approximate it. For example, we can turn to optimize this loss function. It measures the distance between the GPR solution using the whole dataset X and the GPR solution using a fraction of the dataset. Here, pi is a subsampling operator, so that pi x will be a subset of X. This idea is very similar to cross-validation because we are using the information of the fraction of the dataset to infer the statistical property of the whole dataset. Especially here, we're mainly interested in a specific choice of D that is proposed by this work, kernel flow. And in 2018, Owhadi and Yu produced this kernel flow estimator. And in 2020, they have some follow works on using kernel flow to study the layer-wise training of neural networks. And also recently, Hamzi and Owhadi applied kernel flow to learn dynamic systems. The kernel flow loss function is as follows. So it measures the distance between the two GPR solutions using X and using pi x, using a very specific norm. This norm is the RKHS norm. And that means for kernel k theta, and the reproducing kernel Hilbert space theory implies there will be a RKHS space and there will be a norm on this space. So we use this space to characterize the distance between the two solutions. And we also normalize this distance by the RKHS norm of the first one. We can interpret this loss function as follows. A kernel is good under this criteria if subsampling data from X to pi x does not influence the GPR solution much in the sense of the RKHS norm. This is quite natural because a kernel is good, it won't change too much in the accuracy of an interpolation and by reducing some data points. Okay, so that is the Bayes solution and the kernel flow solution. And in the following, we will compare their performance on some models and to provide some theories for that. So we have two estimators. The first question, the very simple question we're going to ask is that how do the two estimators behave as the number of data goes to infinity? This is a consistency question. And in this work, we will answer this question for some specific model of U dagger, theta, and X. And to describe our theory, I will first specify the models we are considering. It is a very specific Martin class model, but it's not on Rn, so it's not the usual Martin class model. It's defined on a torus. We use d equals t to the d to be the d-dimensional torus. It's 0, 1 to the power of d, but with periodic boundary. And we assume the data comes from a lattice on this torus with step size 2 to minus q. That means we have 2 to q times d number of data on this torus, equally distributed. We also need to have a kernel family. Here we choose the Martin class with the regularity parameter to be inferred. The most general Martin class on the torus will have 3 parameters. Here you can have the amplitude sigma square, and here you can also have a length scale tau square I. And here in our theory, we focus on the recovery of regularity parameters, but we will investigate the other parameters in our experiments. Also, to define the kernel flow estimator, we need to define a subsampling operator. And here in our theory, we choose pi to be the subsampling from the Q level lattice to Q-1 level lattice. In numerical analysis, it's just one level great coarsening. Under the above setup, and the theory in our work says that if you have a model for your ground truth U dagger, if U dagger is drawn from a Gaussian process with mean 0 and covariance minus Laplace to the power minus s, then as the number of data goes to infinity, we have a very well-defined limit for both estimators. The empirical Bayes estimator will converge to s, while the kernel flow estimator will converge to a very interesting limit, s minus d over 2 over 2, that converges in improbability. And the idea we use to prove this theorem is based on multi-resolution decomposition, and also we use some probability, the uniform convergence of random series. And here I will not elaborate more about the theories, but I'm going to show you some experiments to explain how it works in practice. We consider a one-dimensional example here, and we assume s equals 2.5. The number of data is 2 to a line, and we use match size 2 to minus 10 to discretize the Laplace operator. Then, for a single realization of U dagger from that Gaussian process, we can just calculate the loss function both in the empirical Bayes and the kernel flow. The x-axis is the value of parameters, and the y-axis is the loss value. We can see that in the empirical Bayes loss function, the minimizer is 2.5 equals s, so that matches our theory. And also in kernel flow, the minimizer is 1. And note that the d equals 1, so s minus d over 2 will equal to 1. So this also matches our theory. And moreover, there are some patterns in the loss function. In the empirical Bayes algorithm, and there is a linear regime, and then it blows up very quickly. In the KF loss, it's more symmetric, and the message is that our theory in this paper can predict those behaviors. Okay, so hope I have convinced you the correctness of this theory. And then we're going to ask another question, which will be even more important and interesting. It is that we have 2 algorithms, right? But how are the limits that are converging special? We have 2 limits, 2.5 and 1. This question is related to the implicit bias of different algorithms in doing model selection. And to start this question, our strategy is to look at the L2 population errors of different parameters. And in our first experiments, we choose the number of data to be 2 to the q, and we vary the value of q. And we compute the generalization error or the population error averaged with respect to the U dagger from the Gaussian process. This is the L2 error between the ground truth and the GPR solution. And because we averaged over the U dagger, so this is the deterministic objective. The following is the figure for this objective function. The x-axis is the value of q, and the y-axis is this quantity. We plot this L2 error for different t. We can see that as the number of data increases, the generalization error will decrease for different t. And the interesting thing is that when t goes from 0.5 to 1, the slope becomes sharper. That means the convergence rate becomes better. However, as t passes 1, the slope rarely changes. That means t equals to 1 will be the minimum t that suffices for the fastest rate of L2 air. Remember that t equals to 1 will be the parameter that the kernel flow is selecting. So that indicates this is an implicit bias of kernel flow algorithms in selecting parameters of this model. We can also look at another experiment, but we still have the same setup, but we fix the Q equal to 9, and we mainly focus on the L2 generalization error with respect to the parameter t. And the x-axis is t, y-axis is this generalization error. We can see that in this figure, t equals 2.5 will correspond to the minimum L2 error in this averaged sense. So that means 2.5 is the t that achieves the minimum L2 error expectation, and this is the parameter that empirical Bayes will select. So that also indicates the selection bias of empirical Bayes algorithm. So to conclude, we theoretically study the Merton-like kernel on a torus, and we have two algorithms, empirical Bayes and kernel flow. We have well-defined large data limits as the number of data goes to infinity. They have some well-behaved behavior, and also they have very different selection bias. EB will select T that achieves the minimum L2 error in expectation, while KF will select the minimum T that suffices for the fastest rate of L2 error. And our paper characterizes those behaviors and provides some interpretations. There are more comparisons between the two algorithms in our paper and also in the longer pre-recorded video in the website. We estimate other parameters in the Merton class model and sigma and tau. And because we have two consistent estimators, we will compare their variance. And this is very natural and observable to compare. And also the important thing is that different criteria may have different robustness to model missimplification. As we know, it's often expected that there are some modeling errors, and we want our algorithms to also to be robust in these things. So we design some models, and we test the two algorithms and to say whether there are robustness to this model mismatch. We also have a very short discussion on computational cost. Generally, we are doing this hierarchical parameter learning, and there are two approaches, the Bayes perspective and the approximation theoretical perspective, and it's motivated by cross-validation. And they have very different behaviors in this Merton-like kernel model, but this is a very toy model, a theoretical model. And it's of interest to extend this kind of analysis to more complicated or practical machine learning tasks or inverse problems to explore more their advantages and disadvantages. With this, I'll conclude my talk, and thanks for your attention.
All right, thank you very much.